Alright guys, you are welcome to this live class lesson. In the course of today's class lesson, I'll be teaching on a very vital aspect in the subject chemistry, and what we'll be focusing on in the course of this class lesson is simply called organic chemistry. This is what I'll be discussing in the course of this live class lesson. So if you're online, do well to signify so we can start right away. If you're online, do well to signify so we can start right away. Organic chemistry. What does this aspect of chemistry talks about? We're going to learn everything we have to know about this aspect in the course of today's class. So you have to pay close attention in every, to every information I'll be giving in this class lesson on this aspect of chemistry called organic chemistry. All right, let us move further. Let us start now. Chemistry. Pay attention. What aspect are we going to deal with in the course of this live class lesson? It is simply this branch, I'll call it branch of chemistry called organic chemistry. So in this aspect of chemistry, what does this aspect of chemistry talks about? That's the question. That's the first question we ask ourselves. You've been hearing organic chemistry. What does this aspect talks about? Now pay attention. I'll be giving you clear explanation, and as we learn this topic, we are going to tackle past questions that have been asked on this aspect of chemistry, so get ready. So in organic chemistry, we study a very vital element, and that element is carbon. Please note what I just said. So we can simply say that organic chemistry is the study of the compounds of carbon. Pay attention. Except their carbides, except their sulfides, oxides, and carbonates. All these are, so in organic chemistry, we really don't study other compounds of carbons like the carbides, oxides, sulfides, and carbonate, but leave that alone. What did I just say now? In organic chemistry, we simply study carbon. Most importantly, guys, pay attention, and I believe, this is carbon. This is one of the vital elements you study in organic chemistry, carbon, and I believe that this element is symbolized as C. Alright, this element is symbolized as C. Another very important thing you should know about this aspect of chemistry is what we want to start right away, guys. Please pay attention. Now, carbon you are looking at here, it possesses some unique properties. I repeat, this carbon that we want to study in this topic possess unique properties. So in your note, you simply write uniqueness of carbon, or the unique properties of carbon. What are these special things that are seen in this element carbon? One of the unique properties of carbon is what I'm about saying. Unique properties. Pay attention. One of them is simply what we call this term called catenation. This is one special behavior or unique property of carbon as an element. So in chemistry, you ask yourself, what is catenation? Now, pay attention. Let me tell you something. I just made mention of that catenation is one unique or special property or feature for this element carbon. But bear this in mind that it is not only carbon in chemistry as an element that can undergo catenation. Are you listening? It is not only carbon. Other elements can also catenate. I will explain. So by definition, catenation, pay attention, is simply, pay attention guys, catenation is simply the ability of an element, not just carbon. It is simply the ability of an element, not just carbon, but carbon is one of them, one great element that undergoes this process. So it is the ability of an element to form long chains with itself. This is what we call catenation. Pay attention. So carbon is one of the elements in chemistry that can undergo catenation. Though other elements can undergo catenation, like the likes of phosphorus, like the likes of oxygen in ozone, I will explain. But carbon in chemistry is one of the greatest elements that can have the ability to form the longest of chains. Now let me show you what I mean by this one I just said, catenation. Now I'm going to use carbon as an example to explain what I mean by catenation, which is the ability of an element to form long chains with itself. These chains you are forming must be of yourself, identical. Pay attention. So this is carbon connecting with each other. Are you not seeing that all of these carbons are connecting with each other? So when carbon has the ability to connect with each other to form a long chain, what is that called? Catenation. Now let me explain something. This connection you are seeing, they call it bonds. What did I say? They call these bonds. You understand what I'm saying? So the point I'm trying to make here is that this carbon we're looking at here, they are forming bonds with their self. And for an element to catenate, that element basically will, form long chains with itself. Alright, that element will form long chains with itself. Alright, and pay attention, guys. It is not only carbon, as earlier said, that can catenate. Other elements can also catenate, like the likes of this element which is called phosphorus. Now, phosphorus you are looking at here exists as P4 in this case. You know, phosphorus is symbolized as P, but in what I'm about to explain right now, it is existing as P4. Telling us that we have 4 atoms of phosphorus. Pay attention, meaning we have 4 phosphorus. So when they bond with themselves, phosphorus bonding with another phosphorus bonding with another phosphorus. Are you not seeing what I'm saying right now? So the point I'm trying to make here is that these elements we are looking at right now also catenate. But carbon is the most extensive catenator in chemistry. It is the element that can form the longest of chains. Now, other elements can also catenate, like the likes of oxygen. Oxygen can also catenate, but oxygen existing as ozone. Ozone is O3. I've explained this on metals and non-metals. Yes. Now, looking at ozone right now, we have 3 atoms of oxygen here. So you know they'll bond with themselves, right? But now let me explain something to you. let me explain something to you. If you observe what I just did, you can see between these two carbons, there was a double bond. Yes. Let me explain. Now, there are reasons why all these are happening, but that is not what I'm explaining right now. What I'm explaining to you is for you to understand that oxygen also catenates. Oxygen existing in form of ozone O3. Hope you are aware about ozone. Alright? Which basically form the layer called ozone layer. We talked about depletion of the ozone layer, gases that can deplete the ozone layer in the topic metals, non-metals. But that is not what I'm interested in right now. What I'm interested in is catenation. So this should tell you that it is not just carbon that can catenate. Other elements in chemistry can also catenate, but carbon is the most extensive catenator in organic chemistry. Now let us move further. Pay attention, everybody. Now you can see what I'm doing right now. I want to basically connect carbons together. Now I want to draw another one. Carbon can catenate in different ways. Carbon can form long chains in different ways. Carbon can form long chains with single bonds. When they are standing alone as one I'll say they call them single bonds, or we say single bond. Carbon can also catenate with itself with double bond. Do you understand what I'm saying? So that is what I'm trying to explain. Relax, I will explain what I'm. Carbon, you also see here, can also catenate with triple bond. I can decide to put this triple bond anywhere. But as we go on in this class lesson, I am going to explain some vital informations to you. So you have to pay attention. So if you observe what I just drew, you can see I drew a double bond somewhere in the connections between the carbon. I also drew a triple bond somewhere. So the point you have to understand that catenation can be seen when carbon connect with itself with single bonds, double bond, or triple bond, as the case may be. So in summary, carbon catenates. Alright, in summary, carbon or catenates. That is for that. Because there are past questions on what I just said now. So that is for that. Let me go to the past question and search for questions based on what we have said so we can trash them. We are going to learn a lot in the course of this live class lesson. So let me get to your past question and then go find question. Let me start with organic chemistry part in the past question so we can trash questions on all of this, So let us move further. We are going to learn everything on this aspect. So pay attention, everybody. Pay attention. Alright, now let us move further. Now, there are other things we have to note. When we get to solving past questions, I will basically talk about that. Now, let me tell you guys something in chemistry. Listen and listen well. Another unique property of carbon is what we call hybridization. I will explain what this means. Pay attention. So I'm about wiping the board so I can start with hybridization. So let me wipe the board so I can move into that aspect called hybridization, which is the second unique property of carbon. Alright, the second unique property of carbon, guys. Pay attention, guys. Pay attention. As I teach, we'll trash questions. That's how we're going to go through these classes. Alright, as I teach, we are going to trash questions. So you have to listen and listen well. You have to listen and listen well, guys. Alright? So another unique property of carbon I'm talking about is what we call hybridization. What is hybridization? I'm about writing it on the board so you understand it properly. Hybridization. Hybridization in organic chemistry, chemistry in general, listen, is the mixing, pay attention, it is the mixing of pure orbitals. I will explain what I mean by these pure orbitals. Alright, it is a mixing of pure orbitals of different energy level, because this is a question that can be asked in your JAM chemistry exam and other related chemistry exam. So it is a mixing of pure orbitals of different energy level, pay attention, different energy level to form a new set, of equivalent orbital. To form a new set of what, guys? Equivalent orbital. To form a new set of equivalent orbital of the same energy level. Now let me explain this definition so you get to understand how this hybridization works. Everybody pay attention. So in carbon undergoes this a lot. Are you there? So in hybridization, what you have to picture in your head here is that it is the mixing of pure orbitals. When I taught us quantum number, I basically explained all of these orbitals. Remember, we have the s orbital, the p orbital, the d orbital, the f orbital. You looking at all of these orbitals, they are pure, meaning they are just on their own. S is not mixed with anything. So s orbital there is a pure orbital. Same applies to P, same applies to D, and same applies to F. Are you there? So in hybridization, we then mix these pure orbitals together. And when I took this quantum number, I told us that these orbitals standing like that, like this now, they have different energy. Like energy is greatest in the F orbital than in the S orbital. Yes, guys. So that is why the definition has different energy level. You are mixing orbitals of different energy to now form a new set of equivalent orbital of the same energy. Let me explain. In this explanation, guys, I'll be mixing two different orbitals, which are the s and the p orbital, or which are the s and the p orbital. Hope you guys are following me. So now, pay attention. So now, pure orbital. Let's write here pure orbital. Pure orbital. Pay attention. So what are the pure orbitals? You have the s orbital, the p orbital, the d orbital, and the f orbital. So then, what then happens? These are the pure orbitals. So for instance, I come here and take one s orbital and another p orbital and mixed them together. What becomes my product? I simply get an orbital called the sp orbital. In this case, this one we have brought together is now what we call an equivalent orbital. Equivalent is formed based on when you add things together. You understand? It's not called the equivalent orbital. You can see because I added one s and one p, that is why they form the sp orbital. Now let me explain something. In chemistry, they can also use the term unhybridized and hybridized. Pay attention. Unhybridized and hybridized, so that you guys will understand everything in the course of this class. Alright? Just pay attention. Pay attention, guys. Pay attention. So we can move further. So we can move further. All right. So we have what we call unhybridized and hybridized orbitals. The unhybridized orbitals are the orbitals that are pure. You have no hybrid, hybrid now, when you mix two different breed of dogs. They'll say, this one is an hybrid. Do you understand? So something hybrid is formed after you have mixed pure things together. Do you understand what I'm saying? So all these pure orbitals, they are the unhybridized orbital. And when they are mixed together, they form the hybridized orbital. And before they are mixed, their energy were different. But after you mix them together, they will now have the same energy, like husband and wife. Before they were different, when they come together, they become one. You understand what I'm saying? So that is for that. So these two, they are the unhybridized orbital forming the hybridized orbital. In this case right now, I want to mix one s with two p orbital to another p. So what do we form here? Pay attention guys. We form the sp2 orbital. Are you there? All these things are very easy. Now moving further, when we mix another s orbital with a p, another p, and another p orbital together, what do we form? We form the sp3 orbital. So what do we call them? Well, we simply call them the sp, sp2, sp3 hybridized orbitals. They are all hybridized in this case. Class, hope you are following. Or we're going to answer questions. So that is my consign, guys. That is my consign. That is my consign. All right. So pay attention. Pay attention. All right. So that is for that. Okay. Let us move further. Let us move further, everybody. All right. So let us move further to very vital information we need. All right, pay attention. Another point you should know about carbon, because I said that carbon undergoes, what do you call it now, catenation, another hybridization. Another vital information you have to know about carbon is that carbon is a tetravalent element. Hey guys, listen to what I just said. Listen, what did I just say? Carbon is a tetravalent element. I will explain to you what I mean by this. So I'll be wiping the board so I can move further about explaining that carbon is a tetravalent element. All right, so pay attention. Pay attention. Pay attention, guys. I'll be explaining to you what I mean by carbon is a tetravalent element. So listen and listen well. So guys, can I wipe the board now? Can I wipe the board now? Can I wipe the board? Let me know. All right, good. You guys are doing well. So I'm about wiping the board now. All right. Now, me telling you all that carbon is tetravalent, this is what I mean. I simply mean that when we draw carbon as an element, carbon is always expected to be surrounded by 4 straight lines, by 4 bonds. This is what I mean by carbon being a tetravalent element, guys. Alright, this is what I mean by carbon being a tetravalent element. It should be surrounded by 4 bonds. If a single carbon atom, because in this case it is a single carbon atom, if we are having something like this and it's surrounded by 3 bonds, it is not correct. Because me having 3 bonds, it means trivalent. And that is not what I told you. But the unique property of carbon, carbon is what? Tetravalent. And tetra simply means 4, meaning that it is 4 bonds that should surround carbon as an element. If 4 bond is not surrounding that carbon, there is a problem. Do you understand what I'm saying? So I want to wipe the board so we can move further. I want to wipe the board so we can move further, guys. Can I wipe the board now? Can I wipe the board? Can I wipe the board? Alright. For this other aspect, remember, when I taught you quantum numbers, a quantum number for the s orbital, how many boxes do we always draw? We draw 1 box. I have explained this, but if you don't know it from today. For s orbital, we draw 1 box. For p orbital, we draw 3 boxes. Hope you have not forgotten. For d orbital, we draw 5 boxes. 1, 2, 3, 4. 1, 2, 3, 4, 5. For this orbital, f orbital, we draw 7 boxes. 1, 2, 3, 4, 5, and 6. 5 and 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, and 7. Alright? So my point here is this. Note these things for your exam. For SPDF, these are the numbers of boxes we draw. That is why if you observe, I did not add another extra P here. If I have had, I added another extra P, shows that I don't know what I'm doing. Do you understand? Because I know what I'm doing, that is why I stopped at this, 3P. Because for the P orbital, we always draw 3, but I've proved these things to you guys in quantum number class. Yes, I've done it, guys. Okay, if you don't know it from today, guys. Know it from today. Alright, just know it from today. That is why, if for instance, I want to start with the d orbital, the next orbital to not draw is d orbital, I will not say, okay, s plus p. Now, why did I just only draw 1 s? Because for the s orbital, we only draw 1 box. That is how it works. That's how it works, guys. So this is under p. Then I will start from my d. So it will be s, p, 3, d. Class, are you there? All these are examples of hybridized orbitals. Guys, is this making sense to you? Guys, is the network okay now? Because somebody just said network. Please let me know in the comments if the network is okay. Please, this network should not disturb us tonight. Class, is the network okay, please? Class, is the network okay? Let me know in the comment. Let me know, please. Somebody just complain of network. Oh, thank God. Thank you, Jesus. So is your network at your end? You work it out. It's not a problem. All right? Thank you, Jesus. This is what I want. Because sometimes network is not, it's really frustrating. It's really, really frustrating. So, guys, you understand? So, what for the d orbital, then I can still add another one. It can be sp3d2. The maximum that I can add is 5. Because for the d, we draw 5. 1, 2, 3, 4, 5. So, it can be sp3d5, sp3d3. Relax. So relax, guys. They know how to relax. Alright? So that is for that. So let's move further to other vital informations based on what we have learned so far. That boxes I just explained is in quantum number. Leave that alone. We are not interested in this right now. Just pay attention, guys. pay attention. Anything I'm telling you, just memorize it. It will help you a lot. So I want to wipe the board right now so I can teach you guys all the things in organics. All these are the introductory aspect to this concept, to this aspect of chemistry, introduction to organic chemistry. And as we are going to introduce this course, introduce this topic, and we are going to trash it. We are going to trash it till the end. We are going to trash it till the end. So help us God. We are going to trash it to the end. So help us God. So, get ready. Alright, our board is clean now. So let me say something else. You know, there are other things we have to work on. There are other things we have to work on right now. So I want to basically talk about them. So pay attention though, guys. Pay attention, ensure you don't let that confuse you. Don't bother yourself. You know, I don't know. You guys should not bother yourself about things that are not important, all right? When I tell you something, note it. Because you don't expect me, that thing I just wrote on the board now, I can prove it, but we are not in that topic right now. Do you understand? Don't stress yourself when they tell you this. Note it, all right? So we can move further. All right, so we can move further. Relax. Coming, guys. I'm coming. I'm trying to find some things to teach you guys, like, you know, so I'll know where to continue from. All right. All right. Okay, I'm good now. Let us move further, everybody. I'm good now. Let us move further. I'm trying to find questions based on what I've taught you guys so far. That is why I am doing all of this. So just relax. When I see anyone on what I've taught you guys, they will answer. Ensure you like the live, guys. Ensure you like the live class. Then we'll move further. All right, no problem. Let us move further, everybody. No problem. Let us move further. Now, after learning about what we have learned so far, then let us talk about something very, very important in the course of this class lesson. And we call them, they are groups of compounds in organic chemistry. They are like very, very important groups of compounds in organic chemistry. And they are called, look at their names. They are called hydrocarbons. Guys, pay attention. These groups of compounds, what are they called? Guys, what did I just call them? I said that they are called hydrocarbons. Who are hydrocarbons? Let me remove S and just say hydrocarbon. An hydrocarbon is a compound. It is not an element. Remember, hydro and carbon, two vital elements are together. and they are carbon and hydrogen. I can literally start with hydrogen and carbon as the case may be. It is my choice, alright? So by definition, these compounds, because they are compounds, when I talk to you guys, elements, compounds, and mixtures, I explain to you guys that compounds are formed when elements combine together chemically. But when some certain element comes together physically, we form mixtures. I explain these things to us. I use metallic mixtures to dwell on all of these things like likes of bronze, brass, duralumin, nickel, permalloy, soft solder, all the types of steel. You understand what I'm saying? So now, hydrocarbon by definition are compounds. They are compounds because they are made up of two elements in this case. A substance that is made up of two or more elements is a compound. So these are compounds. Now, there is a breakdown we must know about hydrocarbon, guys. There is a breakdown we must know about these guys. And that is what I'm about explaining right now. Hydrocarbons. Who are these hydrocarbons? Hydrocarbons, I've defined them. They are broadly divided into two groups. Guys, open your ears and listen. Hydrocarbons are broadly divided into two groups. And what are they? That's the question you asked me. Hydrocarbons are broadly divided into two groups. And what are they? They are what we call the aliphatic hydrocarbons and also what we call the aromatic hydrocarbons. Relax, relax, and relax. I will explain everything. Me just saying aliphatic, aromatic, I have to define them. Relax, guys. Relax, they are all easy. So the question you asked me, what are aliphatic hydrocarbons and also what are aromatic hydrocarbons? We're going to work on them right now with detailed explanation to every single information. All right? So just pay attention. Pay attention, guys. All right? Pay attention. Listen and listen well. All right. Now, before I define, let me explain further. Aliphatic hydrocarbons, they are broadly divided into two groups. Everybody listen to what I'm saying. These aliphatic hydrocarbons, they are broadly divided into these two groups, which the first group they call them Cyclic, aliphatic hydrocarbons. And these guys, they are the acyclic. Guys, listen and listen well. So these guys are the acyclic aliphatic hydro. I will explain. Guys, just listen well. All right? So, moving further, the question you asked me, who are the aromatic hydrocarbons? But before I even do all of that, I think I have to start with the definition. So I'm going to start with this aliphatic hydrocarbon, right? Who are these compounds? Who are this set of who are they? Who are these guys? Let's work on them right now. By definition, aliphatic hydrocarbons are hydrocarbons that that have open chains. Relax. They are what, everybody? Hydrocarbons that have open chain. It's not a big word. It's not a big word. Do you know a chain? When a chain is open, do you know how it will look like? Relax. So these guys, they have what now? Open chains. They generally, we call them the aliphatic hydrocarbons. So aliphatic hydrocarbons are hydrocarbons with what now? Open chains. And I will explain. Relax. Relax. So everybody, listen. Let us go back to where we started from. I believe everybody right now can relate to this. I believe you can relate to why, this is me showing you that carbon is catenating, right? Carbon is forming long chain with itself. Oh, I just said carbon is forming long chain. Oh my God. So this should tell us right now that, this one I wrote aliphatic. By definition, I told us that they are hydrocarbons with open chain. Looking at this thing, looking at this chain, is a chain. Is it opened or closed? Everybody tell me in the comment section. Looking at this chain, is it looking like, guys, tell me, is it closed or it is open? Tell me, guys. Tell me in the thank you. This thing I just showed us is open though, is open. So me telling us right now that this particular structure, which I'm going to elaborate on in the course of this explanation, is what, and it has an open chain. So without wasting time, tell me also in the comment section. So why would you classify this compound? That's my question, though we are going to build on all of this knowledge. Where do we, though I'm not going to define aromatic, but now I'm asking you, relax. Where do we classify this? Is this compound aliphatic or aromatic? Tell me, is this thing drawn? Is it aliphatic or it is aliphatic? Because we already seen that it has an open chain. In as much you have an open chain, you are aliphatic in nature. And I will explain further. Good. I'm proud of you guys. You guys are doing well. Alright? So that is for that. Let us move further. I am not done with the definition of aliphatic. I think you wrote the aliphatic hydrocarbons are hydrocarbons with open chain. Full stop. Continuation. Aliphatic hydrocarbons are of two types. Aliphatic hydrocarbons are coming types two. We have the guys that are alicyclic and the guys that are acyclic. This is Ali and this is A. They are two different things. Relax. Guys, relax. Pay attention. Now, when I say something, let me tell you something. Because as you go on in this class, you get to see, listen, you get to see some examples of aliphatic hydrocarbons with a ring-like structure. You get to see some aliphatic hydrocarbon with a ring. Something being a ring, that means that thing is like closed, right? And by explanation, we said that, for you to be aliphatic, you have to be open. Though there are some little examples of them, little members of them that have like a closed structure. But most of them are open. So you have to note these guys. See, everybody, are you not seeing cyclic? What does the word cyclic mean? Cyclic has like a circle, right? So when you're a circle, you have a closed chain. Relax, and relax. But me seeing this word Ali, it's telling me that, those compounds that have closed chain, they are still aliphatic in nature. Because I saw the word Ali, yes now. Relax, and relax. Are you there? Relax, guys. We are good to go. Just pay attention. Are you there? So my point here is this. We also have some of these guys that have closed chain. Alright? But they are aliphatic in nature. Class, what I just said, does it make sense to us so I can move further? Let me know in the comment section. What I just said, Does it make sense to us? So I can move further? Let me know in the comment section, guys. Relax. All these things are easy. They are not hard. Does it make good? Good. So you can see what I'm trying to say right now. Some of them, they are cyclic structure. Like when you're cyclic, like cycle, you have like a closed state now, yes now, but they are still aliphatic. Leave that alone. Who are the A's? You know when something is acyclic, it means that I am not. Acyclic, I am not cyclic. Acyclic, I am not cyclic. Yes, now I hope you know the A now. I'm trying to use sexual reproduction. Asexual. Do you understand? Sexual is so A means these are reproduction that are not sexual. So acyclic, they are aliphatic hydrocarbons that are not cyclic. These guys, the acyclic, everybody, they are the guys with the open chains. They are the guys with the open. They are not cyclic. They are the guys. Let's work on them right now. This is the common examples that we know. There are three groups, three brothers. They are the alkanes. The alkenes. Look at their names. So this one ended with A-N-E. This one ended with E-N-E. Alkanes, alkenes, alkynes. Guys, hope this thing is making sense to you all. Alright? So, acyclic, I am not cyclic. Alicyclic, I am cyclic, but I am aliphatic. I have a closed chain, but I still belongs to this family. Are you there? Acyclic, I am not cyclic. I don't have a closed chain, but I belong. I am one of the legitimate member of this family. Class, are all this making sense to you? I will soon explain aromatic. But before I do that, I have to dwell on aliphatic, which I'm doing right now. So guys, without wasting time, who are these alkanes, alkenes, and alkynes? Now everybody notes this point. Alkanes have another name. We also call them paraffins. Alkanes are also regarded to be called what? The paraffin. Alkenes are also regarded to be called the olefin. Alkynes are also called acetylene. Class, are you there? Note all of these. Alkanes, alkenes, alkynes. You can see their other names. Alkanes are also called paraffins. Alkenes are also called olefins. Alkynes are also called acetylene for your exam sake. Are you there? Relax and relax. Alright? Let us move further. Let's graduate, guys. Let us graduate. Alright? So, I will soon talk about aromatic, but before I do that, I have to basically, let me just talk about aromatic. From A, see, look at, are you not seeing in the spelling aromatic? Are you not seeing aroma? So it tells us that compounds that are here, they have good smell, good aroma. And who are these compounds? They are compounds with the benzene ring, with the benzene structure. Relax. So the aromatic hydrocarbons are the hydrocarbons that are benzene and its derivatives. Guys, relax. Derivatives, meaning benzene and its members. Relax, I will dwell on all of these. Are you there? But before that, I want us to stress on the aliphatic hydrocarbons. Alright, guys, can I move further? Are all these making sense to you guys? Let me know in the comments. Now, let me just tell us something. Relax. The alicyclic, if you observe, and the acyclic, I call them alkanes, alkenes, and alkynes. These guys, look at their members. So the other alternative form of all these guys here, their name will start with cyclo. So this one has cycloalkane, They are the cycloalkenes and also the relax. We are going to play with all these things. And the cycloalkynes, guys. Hope you are following me now. All these things are not hard. Alright? Just relax. They're all easy. So cycloalkanes, cycloalkenes, and the cycloalkyne. Cycloalkanes, cycloalkenes, and the cycloalkyne. Let me write this alkyne very well so you see properly. Alright? So you can see the members of the Aliphatic. They are alkynes. Are you there? So you are seeing them very well. We'll trash questions. Get ready. We're going to trash a lot. We're going to trash a lot in this class. A lot of them. So you know that organics is one of the simplest aspects in chemistry. Organics is not hard. We're going to trash a lot. Yes, and you prove to your friends that you know what you're doing. Do you understand what I'm saying? So relax. We are going to work on all these. A lot of things will be learned in the course of today's class. You can see all the members of the Aliphatic. You can see all the members of the acyclic. Class, hope these things are making sense. Relax, relax, and relax. Now, let us move further. If you are an alkane, guys, listen, who are these alkanes? I told you that, they are also called paraffins. These ones, they are also called olefins. These guys, they are also called acetylene. But note this very vital point. You have to know here that alkanes, Are you not seeing I wrote a straight line inside a bracket? This tells us that alkanes are single bonded compounds. Write that in your notes. They are all T. When you say a structure and the carbon-carbon connection, there are single bonds to tell you this thing is actually an alkane. Relax. We are going to identify them in the course of this class lesson. Alright? So that is for that. Moving further, who are these guys? They are the double bonded compounds. They have double bond. When you look at the structure and you just see these in the structure, relax. Though, in that same structure, you will see this. But let's say you now saw both. Yes, now, relax. Relax them. Just know that these guys are stronger than these guys. So whenever you see this and this, that compound is an alkene. Relax. If these guys are stronger, they will dominate. They must dominate. Yes, relax. They're all easy. So alkynes are the triple bonded compounds. Alkynes are the triple bonded compounds. Alright? Alkynes are the triple bonded compounds. Alright? So if you say a structure, we're going to draw a lot of structures and they are all easy. If you have a structure and you have single bonds, you have triple bond. I am an alkyne or an acetylene. Do you understand? That is for that. Let me start drawing structures so that you guys will start identifying them for me. They are not hard. Relax. Bear this in mind. Carbon is tetravalent. Let us move further. In this case, I want to connect, let's say, 3 atoms of carbon together. How many atoms are there connected? Is it not 3? Open your eyes and see. Open your eyes and see, guys. Now, what did I tell you when I started this class? Carbon, is it trivalent, pentavalent, or tetravalent? Tetra, meaning that it is 4 bonds that is expected to surround 1 carbon atom. Guys, listen. So let us look at each of them and ensure that all those bonds are surrounding each of the carbons. So looking at this carbon right now, how many bonds is surrounding? Look at this one, leave these 2 guys alone. Look at this one. How many bonds are surrounding this one? 1. So let us complete it. Yes. If you don't complete, there's a big problem. So complete by putting 1 here, putting another here, and putting another here. So let's now count. How many bonds are surrounding this carbon? 4. 1, 2, 3, 4. So we are good to go. Guys, so we are what? Good to go. Are you there? Are you there? You can see. But we are not good to go for these guys. So how many bonds is surrounding this one right now? 1, 2. So 2 bonds. Let's complete it. 3 and what? 4. Yes, now. How many bonds surround this? 1, 2, 3, 4. Alright, because this is where students fail organic chemistry when they don't understand how bonds, how bonds are placed in compounds. When you don't know it, it's a problem. Alright? So let us move further, everybody. Looking at this last carbon, we have to put another 1. We have to put another 1, 2, and 3. Yes, now let's count. 1, 2, 3, 4. Do you understand what I'm saying? Now, what are we discussing in the course of this concept right now? Are they not hydrocarbons? Yes, now. We are discussing about hydrocarbon. So what should surround this carbon are hydrogen. Yes, guys. Relax. So let's place our hydrogen all around. H, 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 and words H, everybody. Class, are you listening? Pay attention. Pay attention. So looking at this structure right now, let us try to identify. To identify a compound, to know the member or the family to which that, we are going to learn a lot of families. So if you observe now, we have learned like 6 different families so far. The alkane family, the alkene family, the alkyne family, the cycloalkane family, the cycloalkane family, the cycloalkyne family. They are all families, relax, and even the benzene family. Like we have learned 7 families so far. We are still going to see more families in the course of this class lesson. So which family of compound which family of compound does this compound belongs to? To know it, don't look at anything else. Look at the bonds. Look at those straight lines that are connecting the carbon only. That's what you have to look at. That's what you have to look at. So guys, looking at them now. What are the straight lines? Are they not single bonds? Yes, now. Are they not single bonds surrounding them? Yes, now. So, are they not single bonds surrounding the 3 carbons together? Yes. Hence, this compound is an alkane. Class, are you there? So, even if you don't know the name yet, but it's very easy. Me looking at this now, it has 3 carbons, then I know, because in organic chemistry, when a compound has 3 carbons, the name of that compound should start with prop. And then I add the 3 last letters to that prop. It gives me propane. So this compound is called propane. But I'm going to teach us IUPAC nomenclature in this class lesson, so you have to get ready for all of these things. So note this point also, your note. The acyclic hydrocarbons exist in 2 forms. Acyclic hydrocarbons could be, I told us that the acyclic, they are the open chains, right? This open chain could be in 2 forms. A compound can have open chain. This is open chain. It could be in 2 forms, I'm telling you now. So acyclic hydrocarbons exist in 2 ways. What are they? We have the straight chain hydrocarbon and the branched chain hydrocarbon, everybody. Look at what I mean by what I just said. These guys, they can be 2 forms. We have the straight chain hydrocarbon and as well as the branched chain hydrocarbon. So what did I just say? We have the straight chain hydrocarbon and as well as the branched. So when I say something is straight, you know that simple English now. Look at, we are interested with the carbon only, guys. Look at all these carbons. Are they not arranged in a straight line? Yes. So what kind of alkane is this? Is this a straight chain alkane or a branched chain? Is a straight chain alkane? Let me draw a branched chain alkane for you. So this is carbon coming bonding again with another carbon, bonding with another carbon, but this time around I have something coming down. You can see I've drawn another one down. Relax. So, I have to complete all the bonds. Hope you know what I'm doing right now. I have to ensure that all the carbons are carrying 4 bonds. Class, let's count together. Yes, now. This one, how many bonds surrounding it? 4. 1, 2, 3, 4. We are okay. How many surrounding this? 1, 2, 3, 4. We are okay for this. How many surrounding this? 1, 2, 3, 4. We are okay as well. How many surrounding this? 1, 2, 3, 4. So everything is okay. Let's place our hydrogen before I discuss about hydrocarbons. So now, moving further, this is H, 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 and this is H. So now, this compound, look at it. Is it an alkane, alkene, or an? It's not. It can never be a cyclo, because if you're cyclo, you have a cyclic structure, which I'll show us in this class. But before then, I want us to just master these 3 guys first, alright? These 3 set of compounds. So looking at this, is it an alkane, alkene, or an alkyne? It is an alkane. Why? Because look at all the bonds surrounding the 4 carbons here. They are all single bonds. Alright? So if they are single bonds, hence the compound is an alkane. But to be specific right now, what kind of alkane is this? Is this a straight chain alkane or a branched chain alkane? Everybody tell me in the comment section. Is this a straight chain alkane or a branched chain alkane? Is this a straight chain alkane or a branched chain alkane? Tell me in the comment section so we'll move further. Tell me if it's a straight chain or a branched chain alkane. Tell me if it's straight or branched. Is it? I don't want to say it. Look at it now. There is a straight. Also, there is another some stuff there. I don't know. So tell me. Good. It is a branched chain alkane. It is what? A branched chain alkane, because there is a branch, and this is the branch, like your leaf branch. You understand? So guys, that is for that. Relax and pay attention. You can see how we've been able to identify both straight chain alkanes and branch chain alkanes. Class, all these things are not hard. Just relax and relax well. Alright, let us move further. I want to basically draw other things on the board. Relax and relax. So I want to wipe this one right now. Okay, I think what will happen right now, I want to wipe the board in general so I can basically have space to draw more structures and teach us some basic information. So can I wipe the table drawn on the board? Hydrocarbon giving rise to aliphatic, aromatic. Can I wipe that? Can I wipe all of this on the board so I can have space to draw other things? Let me know in the comment section if I can wipe the board, guys. Can I wipe the board? Yes or no? Let me know. All right, good. Let us move further. Remember, our mind should tell us that we are still on hydrocarbons. We have not left hydrocarbons yet. All right, so I want to wipe the board so we can move further. Alright, we are good to go. Guys, if you are following, let me know in the comment. Just say, I am following. If you are following, let me know in the comment. Say, I am following. Say, everything is going well. Say, I'm understanding all what you're teaching. So let me know in the comment section if you are following the class lesson. Definitely you should follow, because they are all easy. They are all childish. Alright, so let us move further to draw. Good. I'm proud of you. Alright, let us move further. So I want to draw something on the board. I want to draw something on the board. Everybody relax. Relax and relax. Now this is another compound. Carbon bonding with carbon, and with a double bond is bonding with another carbon. Everybody, let us complete this structure together. Remember, we must ensure we place all the bonds correctly first before we add the hydrogen, because we are on hydrocarbon. So let us be very smart. Watch me as I do it. So if you observe right now, if you observe right now, you see that here I have just one bond surrounding this carbon. So what do? We have to ensure that it's 4 bonds. So I'll place, this is 1, this is 2, this is 3, this is 4. So this one is correct. So let us ensure we place the bonds correctly, because right now it is not correct. It is not 4 bonds that is surrounding this carbon. It is 3. 1 bond, 2 bond, and 3 bonds surrounding this carbon. So we have to ensure it is correct. So I can literally put it down or clean it and put it up. I can literally put it down where I did it now, or clean and put the bond up. Don't go and put another extra bond here. Don't do that. If you do that, you have spoilt the compound. You have drawn something that is not correct at all. And when the examiner sees it, especially for those writing like the work, will fail your work. You understand? So this doesn't exist. All right. So that is for that. Because now me drawing that showing 5 bonds surrounding carbon, and I told us carbon is tetravalent. So let us move further. So what about this 1, 2? So I have to put 3 and 4. Let me just make it fine. I can decide to still put this one here. I want to make it just fine and uniform. I can decide to put both up. I can decide to put one down and another one up. It's my choice. It's my choice. Alright? So all of them are correct. Shine your eyes. So if it says I'm doing it and you are not, and maybe I made a mistake with the bond allocation, tell me. Alright? So now, this is H. This is H as well. This is H. This is H, and this is H, and this is H, everybody. Alright, so everything is okay, right? Yes, now this is okay. 1, 2, 3, 4. 1, 2, 3, 4. Everything is okay, guys. So this guy on the board, is it an alkane, alkene, or an alkyne? Guys, I told us, whenever we see 2 different bonds, like this single bond and double bond are senior to them, so automatically this compound becomes an alkene. Guys, automatically what does this compound becomes? An alkene. An alkene. Or we simply call them olefins. Alright? Olefins. 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 Alright? You don't have to sleep. You have to be strong, alright? Me that's teaching right now, it's not easy right here, like it's really crazy. But you know, I'm still pushing just to ensure. I'm so exhausted, like really exhausted. But I won't give up. I won't give up, you understand? I have to ensure that you learn this thing, so that's why I'm taking my time. The pain to do all of these things for you guys, alright? So this is an alkene or an olefin. Are you there? Now listen, everybody. Now I'm going to draw another. Now, what kind of alkene is this? Is this a straight? Is this a straight chain alkene? Yes, it is. It is a straight, because look how the carbon connection, they are all in straight lines. Guys, they are all in what? Straight line. Guys, pay attention. Look at this other one. Guys, look at this other one. Look at this other one. Alright? So now, you can see what I've done, right? So let me fit in all the bonds. So here is 1 bond. So here is 1, 2, 3. That's 4. 1, 2, 3, 4. Let's do this one. 1, 2, 3, 4. Right? Let's do this one. We have to be very smart. 1, 2, 3, 4. Let's do this one. 1, 2, 3, 4. Let's check on this. 1, 2, 3, 4. Let's check on this as well. Open your eyes. Open your eyes. Open your eyes and listen. 1, 2, 3. So 1, 2, 3, 4. Let's check on this. 1, 2, 3, 4. So let's put in H, 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 H. Wherever you have your bond, you put hydrogen. H. Guys, open your eyes, shine your eyes to look what I just did. Here is H, here is H, here is H, here is H, here is H. Don't worry about the name, it is very easy to name. I'll teach us naming when we get there. But now I'm trying to tell you, I want you guys to be able to identify the compound. This compound, everybody, what's it called? It is an alkene, right? Yes, because I just saw it over here. So when I see just one, it has power over thousands of single bonds, alright? So that is for that. That is for that. All right. All right. That is for that. Thank you. I'm not even done. People are already answering me. This compound, is it a straight chain alkene or a branched chain alkene? This one, it is what? A branch. I can see a branch coming down. So this is a branched chain alkene. This is what? A branched chain alkene. Hope this is making sense to us. On me drawing the structure, they're not hard. Practice makes perfect. Hope everything is okay. We'll ensure, what I want you guys to do for me in this class, be vigilant. Anywhere you see that there's a mistake, maybe I add excess bond oversight, let me know. Let me know. Alright. Let me show my eyes very well to look at this one. 1, 2, 3, 4. But this one is okay. Let me show my eyes. 1, 2, 3, 4. Alright. Help me shine your eyes as well. Alright. So that is for that, guys. Alright. Guys, we are going to learn everything today in organics. Is that possible? Yes, it is. All you have to just, you have to have energy, strength. Because you have to take through the pain now. You have to go through the pain right now. So that at the end of everything, you'll be happy with yourself. When you're at the exam, you pass without stress. You'll be happy with yourself, guys. Alright, so this is for branch chain. This is for straight chain. Let us move forward. I want to wipe the board and draw something else on the board. I know, I'm aware about that. I'm aware. It's not alkane, no. This one is an alkene, no, alkene. Don't say branching alkane. It's an alkene, alright? So I want to wipe the board to draw something else for the alkynes. And then you see how it works. On how to name all these structures on the board, they are all easy. Work on them as we go on in these classes. But before then, I want you guys to listen well to every single information I'll be giving us in this class. The same mostly for your exam condition. Alright. This is another carbon bonding with another carbon, bonding with another carbon, and bonding with a triple bond and having something like this. So guys, let's complete this. Let's ensure we put all the bonds correctly. Here is bond, here should be a bond, here should be a bond. Hope you know. Here is 1, 2, here should be 3, and here should be 4. Here is 1, 2, 3, 4. So this is okay, but this is not okay. 1, 2, 3, 4. Class, are you there? Class, are you there? Hope you are aware that I can try to remove this and put it off. Are you there? You see them that, this carbon is surrounded by 4 bonds. But to just make it fine, we put it at the end. Do you understand? I can try to put it down as well. Do you understand? All the matters that should 4 bonds that should surround the carbon. So here should be H, 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 and here should be H. Now what compound is this? This compound is an alkyne. Why is it an alkyne? It has a triple bond. I told us triple bond is bigger, senior to all of those guys when it comes to strength and power. Alright, so these guys supersede the single bonds I'm saying. Even if there is a double bond, it will supersede it as well. So this compound is an alkyne or an acetylene. I told us already. Alright, and specifically this is what a straight chain alkyne. So branch chain alkyne sharp. Branch chain alkyne. H. Here is H. Here is H. Here is H. Just quickly draw it. Here is H and here is H. Am I good to go? Am I good to go, guys? Let me check. This one, 1, 2, 3, 1, 2, 3, 4. Okay. Alright, what about this? 1, 2, 3, 4. What about this? 1, 2, 3, 4. Okay, everything is okay. So this one is still an alkyne, but a branch. Don't worry about the names, they are all easy. I'll teach us naming very well. You'll be able to name any compound. Anything, any compound in chemistry, you'll be able to name it and even draw structures yourself. We're going to learn a lot. Alright? So that is for that. So everybody agree with me that that one drawn last is a branched chain alkyne. Alright? So let us move further. Let us move further, guys. Relax. Relax and relax. Everybody pay attention. I want to wipe the board because I have something very vital to tell you guys. I want to wipe the board because I have something very vital. I don't want to miss anything. I don't want to miss anything. So I want you guys to listen and listen well. I don't want to miss anything. Alright. Now, let us quickly start with, let us talk about the alicyclic hydrocarbons, which are those guys with a cyclic structure, they have like a closed chain, a ring. They are not benzene, no. These guys are not benzene. They just have a closed chain. Alright, they are not benzene. They are not benzene, guys. Because benzene has that benzene ring inside. They are not. Benzene have a closed chain. They are not. The alicyclic, they are not, which include your cycloalkane, cycloalkene, and cycloalkynes. They are not benzene, but they don't have. Now let me tell you something very vital you have to note. The smallest member of this cyclo family has 3 carbons. Hey, everybody listen. The smallest member of this cyclo family has how many carbons? 3 carbons. Relax, relax, and relax. Yes, pay attention. Now, I want to give you guys an example of a cyclo compound. Be it a cycloalkane, a cycloalkene, or a cycloalkyne. You'll be able to relate. Relax. So now, let me tell you something. It's like a bicycle. This is one carbon standing here. This is another standing here. And this is another standing here. Class, are you there? The smallest, be it to a cycloalkane, cycloalkene, or cycloalkyne. How many carbons should you have? 3 carbons. Be it to a cycloalkane, or cycloalkyne. You should have 3 carbons. So everybody, let's connect them together. Can we connect them with bond? Yes, let's do that. So I'm connecting them with bonds. I am connecting them with bonds which I've done. Now, are all these bonds sufficient for the carbons here? No. We have to based on what I told you guys, that carbon is tetravalent. So looking at this, how many bonds? Looking at this, how many bonds are surrounding it? Just 2 bonds. Let's complete. Guys, let's complete it. 2 now. 3 and what, everybody? 3 and what, everybody? 4. Do you understand? Do you understand what I just said? Let's do this. 1, 2, 3 and what? 4. Are you there? 1, 2, 3 and what? 4. Class, hope it's making sense to you. Hope all these things are making sense to you. Relax, relax. What should be here? Hydrogen, 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 and hydrogen. Now, everybody, this is the smallest member of this cyclo family, be it a cycloalkane, cycloalkene, or a cycloalkyne. Guys, now looking at this, what kind of cyclo group is this? Is this a cycloalkane, cycloalkene, or a cycloalkyne? Guys, I told us for us to know the member is based on the bonds surrounding each of the carbons. Now, what are the bonds surrounding these carbons here? Are they not single bonds? Yes, they are. So automatically, this compound is a cycloalkane class. All these things are making sense. Yes, now, is it not single bonds that are surrounding the carbon? Hence, this compound is a cycloalkane. Class, are you there? Now, you can see it has 3 carbons. Automatically, I told us when a compound has 3 carbons in organic chemistry, the name of that compound should start with prop. This part. Alright? So I'll just say prop. Alright, this ALK, I'll change to prop. So this compound specifically name will now be cyclopropane. Guys, relax. Relax. I'm not teaching Amy right now. When we get there, we'll work on it. So let me basically draw another structure on the board. Maybe for another member. So another family. So this carbon, this is another carbon, and this is another carbon class. Hope this is making sense to you. So now let's say this one is bonding here, this one is bonding here, and let's say this guy have the bonds between these 2 guys is a double bond. Let us assume, because now me drawing this automatically, what I just draw on the board is what, everybody? Okay, let me finish first. Let's put our bonds. Now, how many bonds are surrounding this? 2 now. Let's complete it. Alright, 3 and 4. What about this one? 1, 2, 3 surrounding it. So let's draw another 4. Class, are you there? Normally it should be like this. But because it is 1, remember I just read like anyhow you want to take it up, take it down, it's your choice. Class, are you there? 1, 2, 3. 3, 4. Alright, so let's put in our hydrogen. So here is H, here is H, here is H, Here is H as well. Class, so this guy on the board, is he a cycloalkane or a cycloalkene? Is a cycloalkene, and it has three. Guys, are you there? Are all these things making sense to you? Are all these things? So specifically, since it has three carbon, cyclopropene, propene. Relax, relax, and relax, everybody. So let's say, okay, let's basically just alter this and draw something. Let's say I have another double bond. I have another bond rather, like a triple bond here. So when I do that, automatically I'm going to eliminate things, right? Because now it has exceeded, all the carbons are exceeded, like especially these two guys, they have exceeded the 4 bonds, all right? Listen, open your eyes and watch. So now let's check this carbon, how many bonds are surrounding it? 1 bond, 2 bond, 3 bond, 4 bond, and 5 bond. So automatically you don't remove a bond inside. You don't remove bonds that are connecting the carbon. You don't have the right to do that. The only right you have is to remove the bond that is holding any of the hydrogen. Class, are you there? And we do the same thing here. Because now this one is 5. 1, 2, 3, 4, 5. So we have to ensure that it's 4. So 1, 2, 3, 4. Okay. Alright. So now if I write the chemical formula, it's going to be C what? C3. Alright. H what? H what, everybody? 2. Alright. So this one now, there's no way. Now if I show you, okay, well, I can ask you a question. What's C3H2? It's very hard for you to tell me what this is. But as a student, when you can draw structure, you can actually know what this guy is. Relax, relax, relax. Do you understand? There is no way they won't ask a professor. What's C3H? What's C3H? There are so many things in chemistry that can be C3H2. So nobody like that can just say, oh, C3H2 is a cycloalkyne. No, there's nobody like that. You understand? It doesn't work that way. You have to know what you're doing. But you can actually get a structure. You can actually basically work on the structure. Alright? Why is H2? I have to cover twice. Alright? What about this? This one is C3, H what? 1, 2, 3, 4, 5, 6. Alright? So that is for that. That is for that. At least now you guys are understanding what is happening. You guys are understanding what is going to happen. Alright? Because all this forms the basic foundation for your knowledge. Alright, all these forms the basic foundation for your knowledge in organics. If you don't know this, there is a problem. And that is why you guys are knowing it right now, and I'm proud of you guys. And happy for you guys as well, because this is not easy. You can't see people like this just want to, break it down this way. It's very, very rare to see. That's the truth. Not because I'm hyping myself, but I know that it's not easy. It's not easy at all. Alright, people, some persons might know it, but to deliver it this way is not easy, but we thank God for everything. Alright, so without wasting time, guys, let me tell you something. Relax, relax. All these lines, which we call bonds, that are surrounding all the elements, be it carbon, now, I'm saying now, all these bonds, all these lines, which are surrounding all of these elements, be it carbon, be it surrounding all of the elements, be it carbon-carbon connection or carbon-hydrogen connection or carbon-something connection, all these bonds, they are called covalent bonds. Class, in chemical bonding, we have two major kinds of bonds. There are others, alright? We have a covalent bond and electrovalent bond. Now, your JAMB exam can ask you this question. The bond that results in the transfer of electron is electrovalent bonding or ionic bonding. But the bond that results in the sharing of electron is covalent bonding. So in organic chemistry, you can see all of these things you are seeing. They are all covalent bonding. Class, what did I just say? They are all covalent. Notice, they are all covalent bond. All these bonds, most of them. They are all, like what we have seen so far, they are all covalent bond. And I want to stress on this covalent bonding right now. So pay attention. I don't know why I'm bored. Alright? So all these bonds that you're seeing connecting the carbon, hydrogen, carbon, carbon, they are all covalent bond. So let us move further, everybody. Let us move further, everybody. I don't know why the board so can move further. They are all covalent bonds. Remember, we are coming for questions. Remember, we are coming to trash questions. Remember, have that in your mind. There are questions, we are going to trash them. Alright? So we have stressed on this covalent bonding. I told us that all the bonds you see here connecting all the elements, they are all what? Covalent bonding. Alright? So now, without wasting time, let us move further. And I want to show you this covalent bond we are talking about. Alright? Now relax, because there's something I want to basically stress on right now. So let me quickly refill my marker so we can move forward. I want to refill my marker so we can move forward in this class lesson about the covalent bonding and how it relates to organic chemistry. Because questions here also comes out in the JAMB exam and other chemistry related examples, TTM, any chemistry related exam you can think of. So you have to basically know all of these things properly, guys. So let us work on them right now. Are you ready? Are you ready, guys? Are you ready? Are you ready? Are you ready? Good. 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 Now, in organic chemistry, I basically explained to you guys that these covalent bonds, they are the bonds that are between those elements, be it carbon-carbon connecting with itself, or carbon-hydrogen connection, or carbon anything. Now, this bond, there are two types in this aspect of chemistry. We have what we call the sigma. Hey, what did I say? We have what we call the sigma bond, which is a type of covalent bond, and what we call the pi bond. Guys, we have what we call the sigma bond and the pi bond. Alright, sigma and the pi bond. Now, sigma bond is symbolized as this. I'm about to write it on the board. Alright, sigma bond is symbolized as this, while pi bond is symbolized like pi in math, 22/7, but that is not the case here. Alright, are you not seeing the types of covalent bond we have? Now, in all those structures we've been drawing, what we've been drawing since your JAM exam, post-UTM exam, any other chemistry related exam, university chemistry exam, they can basically come and ask you questions. Oh, in this structure, how many pi bond can you see? How many sigma bond can that? Guys, listen. Let me show you what I mean by all this. Now relax. Let me explain something. I'm going to explain this using the three major guys, which are the alkanes, alkenes, and alkynes. So I will use their bonds. You know, compounds with single bonds, they are alkanes. Compounds with double bonds, they are alkynes. And compounds with triple bonds, they are alkenes and alkynes. Are you there? Now let me explain something. Let me come here and now write sigma and pi. Everybody listen and listen well. I want to use this explanation. I want to use this, I just wrote on the board to explain what I want to teach you guys right now because it's very vital. Now, I'll be using two marker in this case. Now, in this case, are you not seeing, you see not what just one straight line you are seeing? Now, let me show you something again. Listen and listen. Listen. Whenever you say single bond between maybe carbon-carbon or carbon-hydrogen, hey, whenever you say single bond between carbon-carbon or carbon-hydrogen, so guys, as I was saying, whenever you see a single bond between carbon-carbon or carbon-hydrogen, that one bond you are seeing there is a sigma bond. Is a sigma bond. But any other thing that is attached, see, sigma is the first. Any other thing that is attached underneath that sigma is a pi bond. So at first, how many sigma do I have? One sigma. How many, this same thing, how many pi do I have? 0 pi. There's no pi bond. Because I told us the first one we see is our sigma bond, while any other thing that will be attached is our pi. So in this case, I have one sigma and one pi. If another thing was attached down, I will now have how many now in this case? I will now have one sigma and 2 pi. If another thing was attached down, I will have what? 1 sigma, 3 pi. Like that. So the first one is always a sigma bond, whereby any other thing that will be attached to the pi bond. Class, are all these making sense? If you have like 1 million marker under that first marker, those 1 million marker, they are the pi bond, whereby that first marker is the sigma bond. Guys, listen. So on these, how many sigma bond here for this guy? Is a let's assume it's a compound. We have 1 here. How many pi bonds here as well? 0 pi. There's no pi bond. Looking at this, how many sigma bond? But it only have the first one. I told you the first one is only a sigma bond. But by any other thing that attached is a pi bond. So here we have 1 pi bond. Yes, now how many sigma bond here, guys? We have just 1 sigma and how many pi? 2 pi. Class, are you there? If another one was attached 3 pi, if another one was attached 4 pi. Class, does this make sense to you? Did you get this explanation so I can move further to now start solving practice questions? So I can move further to now start solving practical questions. Let me know in the comment. Others respond. Others respond. Is this understood? Is this understood? Let me know in the comments if you understood what I just said so I can move further. Alright, somebody just asked, can a nurse be a tutor? Because what I'm hearing. Oh my god. Alright, I'm going to take it again, boss. Yeah, I'm a nurse. I'm a registered nurse by profession. Alright. But I teach chemistry a lot. I love chemistry. Right from my secondary school days, I love chemistry, so that's why today I know chemistry a lot, and as well as biology. But I also know my nursing, profession very well as well. Alright, so for that person that basically asked this question, he said, I don't understand well, let me explain again. The first one you see is always a sigma bond, whereby any other thing that will be attached is a pi. So in this case, I saw just 1, so how many sigma 1? Did I say any other thing attached? No, that's why under this guy, we have 0 pi. Coming here, I have just 1 sigma, and one thing was attached under 1 pi. Here, 1 sigma, any other thing that was attached, 2 pi. Is that understood now? Because we need all these to start answering questions. We need we need more, we need to start answering jam questions that have been asked on this so far. So I want to wipe the board so I can bring structures on the board. Now, in answering questions on this, you should not be stressed about the structure. All you should basically, alright, let us basically work on examples. You should not be stressed about how the compound is, even if the compound is very big. That is not your business. Your business there is to determine the pi and the sigma. That is what you're interested in. So you guys should pay attention. That is what I'm interested in right now. So you guys should pay attention. Alright? Alright. Move further. So first example, everybody. This is a compound. It is carbon bonding to carbon with another double bond bonding to another carbon, and then let us move further. Here is H, here is H, here is. Alright. We have to be careful, guys. We have to be careful, please. As I call the bonds, you have to tell me so I don't make mistake, alright? So here is H, here is H, here is H, here is H, here is H. And tell me here, should I add another 1, 2, 3? So I should add another. And here is H. I can start to put this one down as my choice. Are you there? I can start to take it off. I don't want it to be uniform. Can I still put another bond here? No, now. Because there's another one. If I put another one, it's going to be 5 bonds. Class, now moving further, how many sigma can we see here? And how many pi bonds? Very easy. I told us to get our sigma. We basically look at the compound, like count all the single bonds we can see. Count all the single bonds we can see. Alright, so let's count all the single bonds. B to hold it. B, the single bonds is holding carbon, hydrogen. So this is 1. So count along. 1, 2, 3, 4, 5, 6, 7, 8, 9. Should I add this one? No, 9. Because this one is a pi bond already. 9, 10, 11. Class, let me know if it's correct. So I had 11 sigma bond and 1 pi bond. Because this automatically becomes a pi bond. Guys, let me know if it's okay in the comments. Alright, so this answer, 11 pi, 11 single bonds standing alone, and 1 pi. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Guys, confirm in the comments if it is 11 pi. Is it good? Let me know in the comment section if it's what you got as well. Guys, let me know in the comments. Is it 3 sigma? Is it 3 sigma? Is it 3 sigma? What I say now? Is it 3 sigma? I told us the sigma is not just between carbon. It is between carbon and hydrogen. What are you saying? Please correct yourself. Alright? Don't do that here. Why are you saying what you said? What you said, please delete that comment. Alright? So we can do the right thing. Is it 3 sigma? No, no. It is 11. Count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We are good. We are good. Alright, so this is the answer to the question. So your jam question, just look for, in your jam they ask for one most times. They can either ask for pi or sigma, so you know what to do. Alright, you know what to do. Alright, you know what to do. So let us move further. All these things are not hard. They are all very easy. So let's work with another example. Number 2, and this one is carbon, triple bond, carbon. Here is H. Here is H. 1, 2, 3, 4, correct. 1, 2, 3, 4. So everything is okay, everybody. Let's work it out together. How many sigma and how many pi? Sigma, let's count together, everybody. Here is 1, here is 2, here is 3, here is 4, here is 5, here is 6. So I have 6 sigma and 2 pi. Class, are all these making sense to you? Let me know in the comments if they're all making sense to you. Let me know in the comment section don't be scared about how it works. Like, leave the compound. You have no business with that. You have no business with the structure right now. What you have business with is you getting your answer. I'm not interested with how the structure is. I'm interested with my answer. Leave the structure, even if it's no big. It's just way to calm down, count. Though there are formulas to get all of it, but I don't want to teach you guys the formulas so you don't make mistakes. Alright? Now, this is another structure I want to bring here. Alright, this is another structure I want to bring here. So I'll be wiping the board so I can move further. Alright, I'll be wiping the board so I can move further. I want to basically talk more on those cycloalkanes, and the rest. Other things I want to tell you guys on. Just relax and relax. Pay attention. So can I wipe the board down, guys? Can I wipe? But what will happen right now? You just give me like maybe 1 or 2 minutes. I'm coming back. Ensuring in live class, 2 minutes, I'm back. Let me go get water and drink. So I can come back, so we'll continue. All right. All right, guys, I am back now. Let us move further to where we stopped. All right. So I think I have to basically talk about all the members of the Cyclic family, so that you guys will not see that it's only those 3 carbons that can form a cyclic compound. I told us the smallest of them is 3. So we have 3, 4, 5, 6. Alright, for your level. Alright, so I'm going to let me show you what I mean by what I just said. Leave this one alone, they're all easy. Let me move further. You have to basically exhaust all of this so I can move to another concept in the course of this class lesson. But all these are vital for your exam. Because all these are vital for your exams, guys. So I'm gonna wipe the board right now, so I can basically teach you what I want to talk about right now. So everybody pay attention. We can also have another cyclo compound having 4 carbon, like what I'm doing right now. It's not just 3 that we drew, 1, 2, 3. Do you understand what I'm saying? So now let's put our bonds. You know, each of them carries 2. This one is 1, 2. This one is 1, 2. So we have to complete 3, 4 from this. 3, 4. 3, 4, and 3, 4. So this is H, 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 and this is H, and this is H as well, guys. So what will you call this? This is a cycloalkane. Why is it an alkane? Because there are single bonds all around. Alright? Yes now. But you know, in organic chemistry, when a compound has 4 carbons, they call it but. So it's a cyclo or butane. It's called cyclobutane. You are doing them together. I'm solving questions and also explaining. All right, I'm solving questions and also explaining. I don't want to just explain. We're doing all of them together. But when we want to, these are also questions in your exams. But we'll soon get to those aspects first. When I'm confident about my explanation, everything then we can go about questions and dealing with them, properly dealing with those questions. All right. So that is for that. So now, everybody listen. We also have another one forming 5 carbon. 1, 2, 3, 4, and 5. Class, are you seeing what I've done? Remember, see now, if you remove this upper part, it will be 4. If you now add this upper part, it will be 5. Alright? So you have to put your bonds. 1, you understand what I'm saying now? Class, hope you know what I'm doing, right? Hope you know what I'm doing. Hope I'm not fast, alright? All these are, you put your hydrogen. So here become H, here become H, like that, like that, like that. You understand what I'm saying, right? So now this is also a cycloalkane, but they're single, but it's not an alkene. But we can form an alkene, alright, which our memory will form. Alright, so let's talk about these 6 guys. Here is 1, 2, 3, 4, 5, 6. Alright, like this, like this, like this, like this, like this, like this. Let's put our burn to complete 1, 2, 3, 4, 3, 4, 3, 4, 3, 4, 3, 4, and 3 and 4. Let's put our H, 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 and H, H. Alright, so this one now is also a cycloalkane, but specifically they call it cyclo. Since it has 6 cyclo, it's a cycloalkane. We are aware about that because all the carbons are all joined together by single bonds. But specifically they call it cyclohexane. Now what did I say? Cyclohexane because it has 6 carbons. And a compound in organic chemistry with 6 carbons is called hex. Alright? It's called hex. Guys, listen and listen well. This thing I just drawn on the board is different from benzene. Now let's add all the carbons together. This now is C6H12. Count all the carbons and count all the hydrogen. You see that we have 12, we have 6, we have 6 we have 6 hydrogen and 6 carbon and 12 hydrogen count. But now you are saying this thing. Benzene structure looks like this. This is benzene structure. Don't get it wrong. This is how benzene looks. Everybody, this is how benzene looks. Almost exactly how this guy looks. This is a bond. This is a bond. This is a bond. This is a bond. This is also a bond. And this is a bond. Are you there? But in benzene, are you not seeing ENE? There is a double bond somewhere. Yes, because anything that ends with in, it has a double bond. This is the knowledge you should have. I told us already, alkenes, they have double bond. And this is how the double bonds are arranged. There is a bond here. After that, you leave one line and go to another. After you leave this one and go to another. Class, are you there? This is how benzene looks like. So let's complete the structure. Remember we put hydrogen, benzene is also an hydrocarbon with carbon hydrogen. So should I go and do something one, two, should I do this? Never! Never do that, I've spoiled it. If I do that, it's not be 5. This one, I don't be 5, 1, 2, 3, 4, 5. It's not correct. So I have to basically draw just one bond here. 1. So let's use from 1, 2, 3, 4 here. 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 1, 2, 3. Yeah, so here should occupy H. Are you there? So this is your benzene, everybody. Are you there? And if you want to what's the chemical formula? C6H6. You have 6 carbon and 6 hydrogen. You can see that benzene is different from cyclohexane. This is a cyclic compound. This one is aromatic. If I don't want to draw benzene like this, I can start to basically do it like this. Everybody pay attention. If I don't want to draw benzene like this, I can start to basically add all the carbons. You know, at every junction there are carbon atoms. Are you there? At every junction there are carbon atoms. I can literally just hide the carbons. Now, just to show it back, I can literally hide the carbon. And, you know, me hiding the carbon, automatically the hydrogen is hiding. But now, to just know that these are the alternative form to which you draw a benzene. When you draw, you put a ring inside. Everybody, when you draw it, what do? You put a ring inside. When you put that ring, it shows that, this is actually a benzene structure. Yeah, what does it say? You put a ring inside. When you do that, it shows that, this is actually what a benzene structure. Alright, you put a ring inside. What does that mean? That is a benzene structure. Guys, are you there? Guys, hope what I'm saying is making sense to you. Hope what I'm saying is making sense to you. Alright? So you can see what we have drawn. When you draw something like this, you will hide all the carbons and hydrogen, put a ring inside. This is benzene. And the chemical formula is 6H6. The chemical formula is 6H6. And what it is what everybody aromatic in nature. And it is what everybody aromatic in nature. Alright? It is what everybody aromatic in nature. It is what everybody aromatic in nature. Alright? They are not hard. Relax, relax, relax. Alright? You flow. You'll be able to flow. This is benzene. I can draw it this way. You understand what I'm saying? This is showing the chemical formula of benzene. Are you there? Relax and relax. Alright? So without wasting time, let us answer. This one is a very, very, very popular jam question. Can I wipe the board? Yeah, I can. I've been able to. Can I wipe the board now? Yes, I can. I want to draw benzene, showing all the carbons and hydrogen broadly, so that I can basically ask the question, how many pi and how many sigma can we see in benzene? How many pi and how many sigma bond is a very simple thing. Alright, 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Class, are you there? So now let's draw H. You know, I told us now we have a double bond, leave one, we have another, leave one, and put another double bond, right? So here is H. Hope you know why I'm putting just one H, so because of what we have done initially. So the question now is how many pi, how many sigma, everybody? The pi is what? The sigma. Sorry, the sigma is what, the pi is what? Alright, sigma is what, pi is what? Simple like ABCD. Let's work it out together. The one you see first is your sigma bond. Let's count. Everybody, let's count carefully. Everybody, let's count carefully. This is benzene. Alright, let us count carefully. Let us count carefully. This benzene. Discovered by a man called Auguste Kekule. You got about the Kekule structure of benzene. The other men, their word structure. This is advanced now. Let me not go advanced. Alright, let us move further. So now this is benzene. Let's determine the sigma and pi together. To get your sigma, those single bonds, you see first is your sigma. Let's count. Let's count the carbons first before we go back to the hydrogens bond. So this one now, on start from here. 1, 2, 2. Should I count them all? 1, 2, 1, 2. I start from here, man should be here. 1, 2, 3, 4. Should I count some more now? 4, 5, and 6. So in this one first, we have 6. Sigma. Let's continue. 6, 7. I start from here now. 7, 8, 9, 10, 11, and 12. So altogether I have 12 sigma. And how many pi? Pi is that one that is attached to the first one you see. So I have 1 pi. Yes, now I have 1 pi. I have 2 pi 1. And also I have how many pi? 3 pi. So you can say I have what? 3 pi's. Yes, now, class, are all this making sense to you? Let me know in the comment if what I just said is making sense to you. Let me know. Alright? Let me know, guys, if all these things are making sense to you. Good. Chimeze. Good. James. Good. Chilima. You guys are doing so well. All right. That is for that. You can see how I've been able to do this. This one is a very popular jam question. You can go bring it to your exam the way I just wrote it here. And most times I ask the pi. This time around, they might sigma anyone. All right, let us move further. I think I have to wipe the board now because I've exhaustively talked about what my mind is telling me to talk about, and we're good now. Now, in summary, everybody, hope you can see that this cyclohexane is different from benzene. Hope you can see benzene is C6H6. Cyclohexane is what? 6 is H12. You see a reaction that converts this to that. But that reaction is not a very suitable one. It's a very bad reaction. I'll teach you guys as we move further. I'll get to the reactions in organic chemistry. So moving further, let us talk about something. Organic compounds. All these are we're in organic chemistry. So all these things we are drawing on the board, they are organic compounds. Meaning natural, anything organic is natural. Natural compounds. Organic compounds, and they possess some characteristics. And these characteristics possessed by organic compounds is strictly based on the bond that is present in them, which is what everybody, covalent bond. So because organic compounds have this covalent bond we are talking about, it accounts for the following properties I want to tell us right now. It accounts for the following properties I want to basically talk about right now. One of the properties that is seen in organic compounds due to their covalent nature is that they are insoluble in water. Most organic compounds are insoluble in water. So I don't know why the bottle will talk about that. Because, guys, note it too, because of the covalent nature in them, it accounts for the following properties, and one of them is that they are insoluble. They don't easily dissolve in water. They don't easily dissolve in water. Characteristics of organic compounds. Alright, features of organic compound. One of them is that they don't easily dissolve in water, meaning that they are insoluble in water. Alright? Meaning that they are what, guys? Insoluble in water. Just listen and listen well. Characteristics of what? Of organic compound. Now the characteristics I'm making mention of is based on these guys, is based on their covalent nature. And one of them is what? Insolubility in water. So they are insoluble in water. Insolubility in water. I've thought of solubility, right? Yeah, in the insolubility in water, I've thought of solubility in water and everything about solutions. So another characteristics that are possessed by these organic compounds we've been seeing since when we started, another one is that they have low melting and boiling point. Organic compounds, they usually have low melting and boiling point. In introductory chemistry, I explained what boiling and melting for low melting and boiling point. When we started this class lesson, like introduction to in the playlist, we've talked about what boiling point and melting point is. Boiling point, I stress only that it is the temperature at which the vapor pressure of a substance, which is the saturated vapor pressure of a substance, equals its atmospheric pressure, but to be specific, what value for atmospheric pressure? 1 atmospheric. I've talked about this many times. So note it now, that's for boiling point. Alright? So now let's get into other characteristics. Other characteristics include they are unstable or unstable. So they are unstable to heat. When you heat them, they are usually unstable. They have, another feature is thermal instability. They are unstable. thermal instability. When you just heat them easily, when you heat them, you can break easily, decompose, break. Thermal instability. Thermal what? Instability. Note these are exam questions. You can just ask you, which of the following are characteristics of organic compound based on their covalent nature? You tell them all this. So the one that is not here will be, which of the following is not. So the one that is not here will not be the answer. You understand what I'm saying? They are highly flammable, high flammability. You know, I taught us flame, right? Flames with zones, alright? I taught us flame. So high flammability. High flammability, they easily flammability, meaning that they can easily catch fire. High flammability. Organic compounds can easily catch fire. Very true. Alright. Another is slow reactivity. Alright. Organic reactions are very slow. That is why they are usually powered by catalysts. Slow reactivity. Slow reactivity. Slow reactivity. So all these are the characteristics of organic compounds based on their covalent nature. Based on their covalent nature. Based on their covalent nature. Alright? They usually are insoluble in water. They usually have low melting and boiling point. They are thermal unstable, thermal instability. They are highly flammable, easily catch fire, and also slow reactivity, meaning that their reactions are slow. That's why catalysts are involved in all these organic reactions to be able to speed up the rate of that reaction, guys. Alright, so that is for that. So you can see you've been able to learn that right now. So let us move further. Let us move further to other characteristics. Alright? To other things. Alright, so without wasting time, let us get into a new subheading. So we've been able to learn all of these. Let us get into a new subheading in the course of this class lesson. And this subheading, look how they call it. Homologous series. People are scared of this word. What's this? Don't worry, I'll teach you right now. You are good to go. Homologous series. Let me wipe the board. What are homologous series? What does homologous series mean? Relax. When we start answering questions, everything will make sense to you. Alright? I'm going to ask questions and set for questions based on what I've taught you guys so far. And we are good to go. You know, in your general exam, you have to learn how to name organic compound properly. Alright? So let's start with homologous series. What are homologous series? I will explain. Guys, listen and listen well. Homologous series. Now, before I tell you the definition, guys, I want to just tell you something. The term homologous series, it simply means family. Me, I have my family. We have our family name. Same applies to you. You have your family name. So your family name is your homologous series. Same applies to my family name. Are you there? All of you in that family, you have a trait. You have some characters you possess. You understand? Same applies to my family. Do you understand what I'm saying? So homologous series simply means family. But since we are discussing about homologous series in organic chemistry, we simply say this is a family of organic compound. A homologous series, by definition, this is a, I'm not going to write on the board, just note it. This is a family of organic compounds. Alright, these are families of organic compounds. This is a family of organic compounds which shows or which follows a regular structural pattern. Note what I just said. It is a family, there are families of organic compounds which shows or follows a regular structural pattern. Right? I know what I'm talking about. Every part of this definition is very vital. Which follows or shows a regular structural pattern, alright, such that successive member in that family differ by a group. Such that successive member, meaning members to come, successive member, they differ from each other by a group called the methylene group. Everybody note what I just said. It is very essential. I said that each family, each members of that family will differ by a group called methyl group, and methyl group is symbolized as CH2. Hey! See, each member in that family, what will they differ by? They will differ by a group called what? The methyl group, which is symbolized as CH2. I know I said that. Relax, I know I said that. Relax, it will help us a lot. Alright? So it's called methylene. And let us move further, everybody. Let us move further. Let us move further. Let us move further. Let us move further. Alright. Now, guys, pay attention. Pay attention. The question you asked me, I told us that homologous series simply means family of organic compounds. They are like families. You have your family name, I have my family name. But in organic chemistry, what are these families? You mean family of organic compounds. What are these families? They include what I want to write now. They include, look at in organic chemistry, these are the families we are going to work on right now. These are the families we are going to work on right now. Pay attention to all of these. The first family I'll be discussing about, they are the alkane family. Guys, hey, what did I just say? The first family I like to talk about, not that they are the number one, not that they should be number one, just based on how I'm going to teach you guys. The first one is called alkane family. We have other families which I'm going to list here and then start telling you guys things about them. The next family, listen and listen well. Listen and listen well. So after alkane family, all right. After the alkane family, the next I want to talk about are the alkene family, which I believe you guys are familiar with. You've seen them before. Alkene. The next family I want to talk about, they are the alkyne family. Are you there? The next family I want to talk about, they are the alcohol family, guys. The alcohol family. The next family I want to talk about, they are the alkynyl family. The next family I want to talk about, they are the alkanone family. Pay attention. The next family I want to talk about, they are the alkanoic acid family. Pay attention. The next family I want to talk about, they are the Ester family. Not like your normal Esther as a name, somebody's name. Ester. The next family I want to talk about, they are the Ester family. The next family I want to talk about, they are the amine family. The next family I want to talk about, they are the amide family. The next family I want to talk about, they are the nitrile family. Class, are you there? So all these on the board, they are homologous series or families of organic compounds. Class, hope they are making sense. They are the homologous series of what? Families of organic compounds. All of these you are seeing on the board, they have their general formula, because we need this general formula to be able to identify these families. Everybody, what did I just say? I want you to pay attention. This part is very important. Like, all of these you are seeing on the board, they have their general formula. Relax and relax. Relax and relax. I know what I'm talking about. Alright, so without wasting time, I just made mention of general formula, and I want you guys to understand. You know, a formula is used to get something. Oh, with their formula you can use to get them. With their formula you can use to determine them. With their formula you can use them to, you can use the formula of a family to identify their family. Yes, we solve jam questions on this very soon. Alright? With the formula we can use them to determine where that guy is from. Relax. Relax and relax. Class, are you there? Relax and relax. On their general formula for the alkane, everybody. For the alkane, they have the general formula. Before I talk about the alkane, before I talk about that general formula, stress learning properly, I think I have to tell you this. Guys, I think I have to tell you this. This is alkane. You are aware that, okay. Let me know. Before I talk about those general formula, let me bring out alkane first of all. Class, on alkane, I want to basically talk about alkane. Do you agree with me that alkanes are also called paraffins? Yes, I've established those facts. Alkanes are also called what? Paraffins. All right, alkanes are also called what? Paraffins. All right, alkanes are also regarded to be called paraffins. We are aware about that. All right, and hope you are aware that alkanes are single bonded, right? Yes, they're single bonded compound. Now, listen. When I decide, okay, there's something I want to teach you guys the way that I want everything to flow well. I want everything to flow well. That's what I'm trying to bring it. Okay, before I don't do that, let me tell you guys something else. Before I won't start, okay, let me tell you guys something else. In organic chemistry, let's say a compound has one carbon. You observe that compound. It has one carbon in its structure. That compound's name should start with met. Are you there? It will help us in naming organic compound. Let's say you saw another organic compound. It has 2 carbon. The name should start with et. Let's say you saw another compound. It has 3 carbon. The name should start with a pro. Let's say you saw another compound. It has 4 carbons. The name should start with but. Class, are you there? Let's say you saw another compound, it has 5 carbon. The name of that compound should start with pent. Let's say you have another compound, it has a 6 carbon. The name should start with hex. You saw another compound, it has 7 carbons. The name should start with hept. You saw another compound, it has 8 carbons. The name should start with oct. You saw another compound, it has 9 carbons. The name of that compound should start with non. Yes, very important. You saw another compound, it has 10 carbons. The name should start with DEC. DEC. Class, are you there? Note all of this, it will help us a lot. Note all of this, it will help us a lot. I know I'm saying what I just said. It will help us a lot. And now, let me do something. I want to basically draw carbon here. And when we draw carbon here, let me put my, carbon is expected to be surrounded by how many bonds? 4 bonds, which I've drawn, right? So I want to put all H surrounding H. I want to put basically like H, like everything, like H surrounding it, right? So me putting H surrounding it, guys, what is this? Remember I told us relax. Remember I told us that when a compound has 1 carbon, the name should start with met. Definitely this compound name should start with met. Do you agree with me? This compound's name should start with what, everybody? Met. Now, what kind of met is this? Met is just like the beginning name of that compound. Now, this name will not tell you what family that compound belongs to. Alright, so you now observe the compound. Oh, this compound is surrounded by single bond. And in organic chemistry, compounds that are all single bonded, they are the alkanes. So the name we end the ane. Automatically, this guy is called methane. Compressing it together, we are going to get CH4. Are you there? Yes, now, CH4. So this is your methane that you should know. Alright, let me just tell you this point that is very vital. Alright, guys, this is alkanes generally. Whenever alkane loses 1 hydrogen in them, everybody, whenever alkane loses, minus, I mean loss. Are you there? Whenever alkane loses 1 hydrogen, they form what we call the alkyne. Guys, what did I just say? Whenever alkane loses 1 hydrogen, they form what we call alkyne. Hope they are making sense. Whenever alkane loses hydrogen, they form what we call the alkyne. Alright? Now I want to tell you something very vital. Automatically, let's lose 1. So this is methane, right? Are you not seeing the name methane? Methane. Remove 1 hydrogen from methane. Alright, remove 1 hydrogen. We'll remove the rest, but relax. So let's now write the first member of this is an alkyne. So because actually the first member of the alkane family is methane. Are you there? The first member of the family is met, because met is the smallest and should have 1 carbon. If you don't relate from today, the first member of your alkane is methane. Are you there? Relax. Now let's remove it and put no, this is ALK. So ALK symbolizes this ones. Are you there? So ALK remains met. Are you there? Why the YL? And this one is ANE. So on this now, you now just add YL. So this is called methyl. Are you there? So by writing it here CH4, remove 1 hydrogen from it. What do you get? CH3. So CH3 now they call it what? Methyl. Class, hope these things are making sense to you. Whenever you remove 1 hydrogen from an alkane, you form a methyl. You form an alkyne. So the member of the alkyne is based on the alkane you are removing the hydrogen from. Relax, relax, and relax. I know what I'm talking about. I want to basically explain these things to you guys so that at least you guys will know what you're doing, like you know it well. Let me tell you something. Alkynes in general, they are symbolized as R. A very important point. Alkyne, they are symbolized as what? Arrow. If you don't symbolize alkynes as arrow, you can simply symbolize them as this thing on right now. Cn H2n plus 1. Now, what did I just say? If you don't symbolize an alkyne as arrow, you do it relax. I will tell you what this thing is. Relax now. If you don't symbolize an alkyne as arrow, you symbolize as this. We are good to go. Relax and relax and relax. I know what I'm saying. Alright, these things will help us a lot. Relax and relax. And they are all easy. They are all very easy. Relax. We've established that fact. I want to wipe the board. I want to wipe the board, guys. And John, we are still on alkane. Let me just tell you a few things about alkanes for now. Can I wipe? Yeah, I can. Not everywhere though. Just a part of this explanation because we have other things to talk about on alkanes, and so I will introduce this aspect of homologous series. Everybody pay attention. Pay attention, everybody. Pay attention. We are all easy. I will first of all start by telling you guys something. These guys you are seeing, they have their general formula. Everybody I just say. From your alkene, all of them have their general formula. But I will start with the general formula for these three members first, which are the alkanes, alkenes, and alkynes. Alkanes, they have their general formula to be listed on the right, but note it and never forget. CnH2n plus 2. Class, it is different from alkynes general formula now. See now, you guys are following me. Alkynes, is it not plus 1 that ended it? Alkane, is it not plus 2 that's ending it? Note it. I want to move further. What becomes now the general formula of the alkene? CnH2n. Relax. Pay attention. Alkene is what I just wrote. What about the general formula for the alkyne? It is CnH2n minus 2. Guys, note all what I've said. All these things are essential. They are very essential for your exams. Are you there? They are very, very essential for your exams. So you can see what we've been able to establish that. Oh, the general formula, because these things are very important. They can just ask, which of the following is the general formula for alkane? Look for the one that is CnH2n plus 2. The one that ends with plus 2 is one sound. Not plus 1. Plus 1 is alkyne, which is also called arrow, symbolized as arrow. Are you there? So now, we are on alkanes, right? So we've established the fact that, all alkanes, they have the general formula, which is CnH2n plus 2. With this alone, we can get the structure of all of this. We can get the structure, we can get the chemical formula for all of these members. Relax. Everybody pay attention. Remember I told us that, in organic chemistry, compound with one carbon is called met, right? So we can use this you are seeing here to get the correct chemical formula of any members of this alkane family, or even alkene or alkyne if we are discussing about them. Right now we are talking about the alkane. Now this your N you are seeing the formula. It means number of carbon present in the compound. So in this case now, how many carbons are in for met? How many carbons are there? For met, how many carbons are there? Is it not 1? So let's assume that all of them are alkanes. Everybody, let's assume that all of them are alkane. So you're going to add methane, ethane, you understand, propane, and to all of them, butane, pentane. Do you understand? Hexane, heptane, octane, like that, and nonane, and nornane, and decane. You understand? So let's assume now that all of them are alkane. So let's quickly get the chemical formula for methane. Sharp. Remember, for methane we have one carbon, right? Methane is an organic compound with one carbon, right? And we've established that fact. So the N in this formula will not be 1 because methane has 1 carbon. So let's now solve. Anywhere we see N equal 1. So let's now get the correct chemical formula for methane because we are on methane now. So here becomes C. Everybody pay attention. Alright, so here becomes what? Cn. And what is that N in this case? 1. H2. These two N is 2 times N, so put the bracket. What's the N as well? 1 as well. Plus 1, 2. So breaking it down, don't give us C1, H worth 2. Because 2 times 1 is 2 plus 2. So everything is C1, H worth 4. Class, right? Yes, now. So H4, which is same as what? CH4. So you can see that from the general formula, we got the correct chemical formula for methane to be CH4, which we have established already. Class. Hope all these things are making sense to you. Alright? Now, what did I tell you? All these guys now, are they not members? Look at my statement. All these guys, are they not members of the alkane family? Yes, they are members of the alkane. Are they members of alkenes or members of alkynes? No, they are not. They are members of the alkane because their name ended with A and E. Do you understand? And what did I tell you? I told us successive member, meaning members to come, members after the first to come, successive. Alright? Successive members, that's what that means. Alright? Listen and listen well. Listen and listen well, guys. Listen and listen well. Alright. So members to come, which are the successive member, they differ by a group in my definition. In homologous series, members like methane and ethane now. Ethane is the successive member. Here, what's the successive member between both of them? Propane is the successive member. Here, who's the successive member? Butane. You understand? Successive member differs by a group called the methylene group. So, for we to actually, let me tell you, what that statement really means is that for we to really get the next member, because we already agreed that this is methane, right? So, for we to get the next member, which is ethane, you don't have to go through all of this by putting N2 with 2. You can also use this method, but you just use the methane, which you got into CH4, add CH2 to it. Alright, when you add CH2 to methane, you get the next member, which is C2H6. Class, are you there? And this becomes ethane. So successive member differs by a group called methylene group. Are you there? So you basically do it like that. For propane, the same way. Do you understand? For propane, now you don't get propane. Now the ethane you get, which is C2H6 plus what? The CH2. You always add CH2 to the previous one to get the successive member, the next member. So here is now C3H worth 8 because this is 2 plus 1 carbon. So this one is now what? Propane. Class, are you there? That is what that definition tells us. Successive member differs by a group called the methylene group. Alright? Successive member differs by a group called what, everybody? The methylene group. You want to get butane, same method. Add CH2 to your propane, you get butane. You understand? So what you do for me as your task, ensure you provide in the comment section, provide all of them or do it in your notes. Alright? Write all of them and down to the can and tell me the chemical formula. You can either use this method by anywhere. Let's basically work on the method using N equals to 2. Alright, let's do that quickly. So let's say N is equal to 2 in this case. So it's going to be Cn. Always ensure you are using the correct general formula for that member you are working on, which is alkane. So this is C2H2NO2 plus 2. So here is C2H worth 2 times 2, 4 plus 2. So here is C2H worth 8. So you can see what I'm talking about, guys. Guys, I didn't know. Is this not here? Yes, now. Oh. Sorry. C2H6, right? 4 plus 2, 6. You understand? So this is what? Ethane. Class, are you there? You can literally just take the number 3, do it again, you still get propane like that. That's how it works. Class, that is how it works. Hope all these things are making sense to us. Hope all these things are making sense to us. So you do down till decane for the alkane family exactly. So get into alkene. Guys, now let's say we are talking about the alkene family. What will not happen? All these ones you are seeing in, their name will not start with in. Okay, let me just tell you something very vital now. Guys, relax. I'm coming. Just give me a few time now. I'm coming, guys. All right, guys. So you can see for the alkenes, same method. All right. Here now, let me just tell you, alkenes and alkyne, they don't have. Pay attention. Pay attention. Alkenes and alkyne, they don't. Their first member is not met. It's not the one that has met. There's not like methane. Let me show you. Let me prove it to you guys. Let me prove it to you guys. Assuming, for instance, now we are on alkenes. Now, let me just tell you, there is nothing like methane. Do you want to basically doubt that? There is nothing like methane. There is nothing like methane. It doesn't exist. If you want to basically, there's nothing like methane in organic chemistry. So let's just work on them. E and E. Alright, E and E. Let's say all of them are E and E right now. Because you're still going to tell me the chemical formulas of all these guys. Alright, using the general formula in the comment section as well. So do this, write the answer in the comment section. Alright. There is nothing like methane. Let me prove it to you guys. Meth, normally you have one carbon, right? And you already know that in this you are surrounded with how many? Is it not? Listen now. If you are meth, how many bonds should surround you? How many bonds should surround you? Is it not 4 bonds? Because one carbon you have that's 4 bonds. Okay, let's say assuming now we now basically put one. Anything that is in has a double bond. Let's say we do something like this. Let's say we do something like this, everybody. You want to say okay, methane now. Let's say we do something like this. Let's say okay, let's go hydrogen. The point is this. Is it guys, no now. Okay, let's wait. It doesn't exist. You don't use a double bond and hydrogen connect. You don't do that. If double bonds are to connect together, it's between carbon. You don't do this, guys. So that's why there's not like methane. The first member of the alkene, and as far as the alkynes, they are. We start from X, carbon 2. So there is ethene and ethine. There's not that methane as well. Normally now, okay, I'll now have 3 bonds at the wait here. If I haven't do this, I've caused problem. Because now, I don't know what I did now. I've caused big problem because now the bond surrounding this one is now 5. It's not like 1, 2, 3, 4, 5. And it's not like that. Okay, let's say I remove this one and put hydrogen here. Is the hydrogen that should be here? Is it not met we're talking about? Is it X? Is it not met? It's met we're talking about now. Met, Abi. And met. You already know that it's one carbon. So should I go and go Jora upon that carbon? When I go on that carbon, it's not met again. It's X. So there's nothing like what now? There's not like methane or methane. Class, are you there? There's not like methane or methane. Class, are you there? Are all these things making sense to you? Let me know in the comment. Are all these making sense to you? Let me know in the comment section. Are all these making sense to you? Let me know. Yeah, the classes will be saved. Alright, you have access to them from the beginning to the end. Class, are all these making sense to you? Let me know in the comment. Are all these making sense to you? All right, good one. So you can see, so what you have to do for me, let's quickly get the first member of, let's get that 18. Oh my God. Let's get 18 quickly, like, using the general formula to get 18. That's the first member of the alkene. Being the first member doesn't mean that you have 1 carbon, still have your 2 carbon. All right, here now, this guy has 2 carbon. And it's an alkene, right? 18 is an alkene. And what is the general formula of alkene? It's not CN H2N. So now it has N is equal to 2 in this case. So now it's C2 H2NO2. Anyway, C N equals 2. So C2 H worth 4. This is 18. Class, what is this? 18. What is this? 18. Yes, now. Alright. And this is 18. You want to get propane, for instance. What do? It's the same method. You add CH2. Alright. They always, each member, in as much T. All of them like this, they differ by a group called interlingual. Don't worry. This is organics. So add CH2 to this. You're going to get C3H6. Are you there? So C3H6 is propane. Guys, are all this making sense to you? C3H6 is what? Propene. It's propene. Yeah, look, shine your eyes so that we don't make any oversight. Shine your eyes very well for me. So that's with the alkene, alright? So you still do the alkene like that. You get the ethyne, propine, like that. Do you understand what I'm saying? They're all easy. So what I'll do right now, what your jam exam can ask you, is what I want to bring on the board. There's a question your jam can ask you. That's what I'll bring based on what I've explained so far. Let me bring that question on the board. So I want to wipe the board so I can have space to do what I want to do. So I can continue. Let me bring that question on the board and then I can have space to do what I want to do. So pay attention everybody. I want to wipe the board so I can have space to work on the question. I want to solve what jam has brought before and they might bring it again. What jam exam has brought before and they might bring, they are all easy questions. They are all very, very easy questions. So guys, pay attention, open your ears very well. Let me go and look for that question right now and bring it out. I'm going to look for that question right now and bring it out. Alright, relax. Let me go find the question first. I'm gonna go bring the question. Where are you? Where is this question? Where are you? Oh my God. Alright, hold on. I've seen it. Alright. Okay, I've seen it, guys. Let me bring it up. What your jam have asked before, it says, question based on what I've explained so far. Which of the following compounds, or which of the following is an alkyne? Did I say which of the following is an alkane? Options. Option A is C2H6. They are all easy, just the same. Option B is C3H6. Option C is C5H8. And option D is C2H5OH. Alright, C2H5OH, this is option D. So let us work this out together. Now, this question you are seeing right now, look at how it works. They say which of the following is an alkyne. So they want you to identify which compound here is an alkyne. Very easy. First of all, when you see questions like this on the identification of the guy that is an alkyne, try to remember quickly the general formula of that guy. The general formula when I told you guys is CnH2n minus 2. Is it not what I told us? Yes, it's what I told us. Now guys, listen and listen well. So now, the way you do it, you now start taking each of them. Like, you start checking for each of the options. Alright, using the number of carbon they have. Yes, now, because this N signifies the number of carbon. So, in option A, how many carbon? Now, after you basically use the number of carbon they have to basically work on your calculation here, when you get the same compound, it tells you that that compound is from the family. But when you don't get the same compound, you are still going to use the same number of carbon now. But when you don't get the same compound, that compound is not an alkyne, no. But they want us to determine one that is an alkyne. Class, you understand? So then let's work it out together. So option A now, it has an N is equal to 2, right? For option A, N is equal to 2. So anyway, we see N equal to 2. So C2H2NO2 minus 2. So C2H4 minus 2. So C2H2. So it did not give us back what option A is. So this guy is not an alkyne. This is the alkyne form of anything that has 2 carbon, not C2H6. It's not correct. This is not an alkyne. This is the actual alkyne form that has this is the chemical formula that is the alkyne based on that number of carbons. Alright, that's how it works. That is how it works, guys. That is how it works. You understand? So let's work out another option. Option B, C3H6, alright? N is equal to 3. So alright, so quickly CnH2n minus 2. So C3H2NO3 minus 2. So C3H6 minus 2. Everything will give me C3H4. So you can see it still did not give me back the option B. So option B is still wrong because the alkyne form of that option B is C3H4. Is C3H for glass? Does it make sense to you? Does all this make sense? Let's check option C. For option C now, for option C, everybody, N is equal to 5, right? And the chemical general formula is CnH2n minus 2. So C5H2NO5 minus 2. And when we do that, everything will get C5H10 minus 2. 2 times 2, 6 times 5, 10. Everything C5H8. Wow! We got that same compound. So telling me that, oh, this compound is actually correct. This one is the alkyne out of all of them. This is the alkyne out of all of them. Option D is not an alkyne, because for you to be an alkyne, even an alkane or an alkene, you'll be an hydrocarbon. Is option D an hydrocarbon? No, now. Option D, there is oxygen, so automatically it's not an hydrocarbon. It's not even part of it at all. This one has a family. I'll show you where it belongs in this homologous series. I'll show you where option D belongs. Class, are all these making sense to you guys? Are all these making sense to you guys? Are all these making sense to you guys? That is for that. Alright? So now moving forward, let me tell you guys something. You know you can quickly name this compound. Yes, sir. This guy is like C5H8. He's an alkyne, and I told you any compound with 5 carbon, the name shall pent, right? So pent and YNE, this guy is called pentane. Don't worry, once start naming compound, this guy is pentane. That's 5 carbon. Pent. And he's an alkyne, take it. Pentane. No stress. Don't stress yourself. You know, don't stress yourself. Guys, hope it's making sense. I want to give you guys your own question right now. I want to give you guys your own question right now. Alright? I want to give you guys your own practice question right now. So get ready. Get ready, guys. Get ready for your own practice question. Get ready for your own practice question on this aspect. Get ready, guys, for your own practice question based on what I've explained so far. Get ready. So I want to wipe the board right now so I can give you your own practice question. Alright, I'm coming. Pay attention, all these things are vital. They're extremely vital, guys. So get ready for your questions. I hope you guys are following me. I hope you guys are following me. Alright, moving forward. So now you do this one for me. Identify the compound here that is an alkene. Tell me, out of the options you have cancelled, no, we cancelled a lot of them. So just rewrite them and tell me the one that is an alkene. This is your question right now. This is your question right now. Tell me the one here that is an alkene. Tell me the compound here that is an alkene. So I'm about wiping the board so we can move forward. The same option. So tell me the compound here that is an alkene. The option here that is an alkene, they are all easy. They are not hard at all. They are all easy. They are not difficult at all. So get ready so we can move forward. There are a lot of things to learn. We're going to trash them. I'm going to trash them. So you guys should pay attention. Pay attention, alright? Make sure you like the live. Don't watch that liking. Ensure you like the live, guys. Good. People are ready to provide the answers. That's very nice. People are already providing answers. That is very nice. So let us move further. Let us move further, guys. Alright. So let us get back into all of these guys. At least we'll be able to work on all these things on the board. Now I want to basically tell you guys something. Because as a student, you have to understand something very important. You know, in your exam question, they can give you a structure. They'll draw, listen, they'll give you a chemical formula and tell you, draw the structure of that chemical formula. Ever listen. Listen to what I'm saying. Listen. This is an example. I will not tell you, okay, this is C2H6. Everybody, what did I just say? This is C2H6. Everybody listen. This is C2H6. Okay, I want to tell you, okay, this C2H6 is an alkane. Let us all draw the structure together. How do we do? We have C2. That means we have two carbons connected together. And they said H6. See, if you can do this one first correctly, this one must enter. Everybody listen. The total number of hydrogen must enter. Just draw your, what do you call it? Draw your. Now, start with your bonds first. Let's say bond contains 6 hydrogen. 1, 2, 3, 4, 5, and 6. Alright, this is H, this is H, this is H, and this is H, and this is H, and this is H. Are you there? So what I just drew is C2H6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Do you understand? They can give you a chemical formula and they'll tell you draw structure. Draw structure. So as a student, you should know it works. I'm going to give us more so we can be able to draw them together. They're not hard. They are all easy. Guys, they are all easy. Guys, they are all easy. Look at another one. Let's draw this structure. Don't be scared. We are still on hydrocarbon. This is C2H2. Everybody, what did I just draw? C2H2. Let us draw. Now, I'm not going to tell you what compound, where this guy belongs to, because I should not spoon feed you. I have to basically just give you the compound. Let us think together and draw the structure. Now, two carbons connecting together, so carbon bonding with itself. Now, as a student, you now think, what can I do to ensure that this compound takes the two carbon they are telling me it has? Because normally, some students say, it has two carbon, so I'll do like this, I'll do like I'll put H, I'll stop that, and this is the compound is not correct, it's not correct. Say that like that. Don't do that. Don't do that. They say it's not correct. This situation is not like that, it's not like that, it doesn't exist. It doesn't exist. What are you saying? It exists. What's situation? Think. So now, remember I told us when you draw something like this, it's not correct, so you have not placed all the bonds. You have not obeyed the tetravalency in carbon, and carbon is tetravalent. You have not obeyed it. So how will you obey it? How will you obey it? Everybody pay attention. How will you now obey it? Let me wipe again so I can draw this one alone on the board. Guys, as I tell you, think, this is C2H2. So how will you obey it? How will you obey the tetravalence in carbon? Alright, so now these two carbons like this, and I'm done. Don't do that. You're not done like this. Because you have not obeyed, the carbon bonds are not correct. Okay, how will I obey it now? To obey it, I'll put there, another one there, another one there, another one there. Don't do that. How many hydrogen they tell you they are? Is it more than 2 hydrogen? It's 2 now. So there's no way you can have to put, because all this one you're doing now, we need to occupy hydrogen. When you do all of this, you are forming your question yourself. When you do all of this, you are forming. So when you see that, when you think that, when you are done drawing what you have, and you say, there's no hydrogen here I can put now based on the question. Then your next thought will be, I have to put it, I have to now put in all those lines to ensure that between the carbons, to make sure that my carbons are correct. Alright, so I'm thinking, if I put 2 bonds, and will I be correct? You know it was single bond, and I put 2. Will I still be correct about the bonding in carbon? So here is 1, here is 2, here is 3. It's still not correct. Because you have to ensure, will I do another one? Don't do it here. You cannot do something here now. You want to change the compound. So then you put it also between them. Just, are you there? Are you listening? You can see what I've done. So actually, this is correct. This compound has 2 carbons. Its name should start with F, right? And then it is an alkyne, so it's called ketine. All these things are not hard. They're not hard. Practice makes perfect. All right, practice makes perfect, guys. Practice makes perfect. Practice makes perfect. All right. Practice makes perfect, guys. The first one we did was C2H6, right? Hope we're correct about it, right? C2H6 now. Abi. Hope we're correct too, because I saw somebody say that. I thought you said it's alkene. I don't know. You that said that, have you been able to correct yourself? So I'll know we're on track, so I don't make any little oversight mistake. You that said that, have you been able to correct yourself? Let me know. Let me know. Let me know, guys, so we can move further. Alright, good. Class, hope all these things are making sense to you. Let's even go back to that one we drew initially, which is C5H8. You can basically work on these 5 now, 5 carbons. Think, it's not going to think, that's what you need. 5 carbons connecting together. I want to try my best to ensure that you guys can stand on your own when you step outside. 1, 2, 3, 4, and 5. Alright, so okay, let's put our hydrogen. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have possibly problem. Normally H, nothing like this. So this one does not exist. What I'm doing now doesn't exist for this guy that we're drawing. But they told me to draw for C5H8. No C5H what I'm drawing now. You understand? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10, 11, 12. So no. What do? We reduce it. Try to be removing hydrogen to ensure that bonds are, we'll get that 8. Okay, let me start from this side. Okay, I have to basically eliminate this one. We are 12 already. Let's eliminate. We have to eliminate. How many are we going to eliminate when we have 12? I'm going to eliminate 4 hydrogen. Yes, now 4. Now I want to get back our 8. We have 12 already. We eliminate 4. So I'll remove this 1, remove this 2, remove this 3, and remove this 4. Class, are you there? So what we now do to ensure that this guy is correct? I'll put it, make sure that the bond is 3. Yes, nah. Yeah, I will not make sure that it's 2. If I make sure that it's 2, it's not correct. If I make sure that it's 2, I still have to add another hydrogen. Class, are you listening to what I'm saying? Obviously, are they not making sense to you? So I have to make sure that it's 3. I have to make sure that it's 3. Hope I'm not fast though. I have to make sure that it's 3. This is correct now. 1, 2, 3, 4, 5, 6, 7, 8. It's making sense. Now this one is it has pentyne. This one is pentyne. Alright, don't worry, we're going to learn how to name compounds very soon. But before then, we have to basically work on all these things we're working on. Class, hope all these things are making sense to you. At least I've been able to do justice to this. So when you see compounds, they're chemical compounds, you can draw their structures. They're not hard. Think. Draw a lot. Alright, so guys, let us move on this one we are on now, which is let me refill my marker guide. Let's continue on the next homologous series, which are the alcohol down to the nitrile on the board. Because at least we've been exhaustively talked about alkenes, and alkyne. Though we're going to stress on them also as we move further. But for now, let us basically work on their general formula. Because I told us that all homologous series, all families of organic compounds, they have their general formula. So let's work on the general formulas of these other guys, so we can be good to go. So what are the general formulas starting from alcohol? How does their general formula work? So let's work on them right now. Let's do that. The general formulas from alcohols down. Alright, the general formulas from alcohols down. The general formula from alcohols down. So everybody listen. The general formula for alcohol, they begin like this. Everybody listen. Alcohol, look at it. It is arrow bond OH. Everybody pay attention. They ask you what is the general formula for alcohol. What will you say? Arrow bond OH. Relax. Class, what did I tell us is arrow? Another representation for arrow. Is it not CN H2N plus 1 bond this OH? Yes. You must always actually put your bond so as to separate them, because this thing means something. I will explain. Relax. So if you are ready, general formula for alcohol will be this. Write it like this. Class, all this making sense? Relax. They are not hard. Let us move further. What about the general formula for the alkanoics? They are the arrow bond CHO. They are the arrow bond CHO. Or we simply come here and say, oh, CN H2N plus 1. Alright, and then bond CHO. You understand? These are the alkanoics. Alright? Don't worry, relax. Alright? What about the alkanos? Alkanones. That is arrow bond CO arrow prime. These two arrows, because they are two different arrows, I just use something to separate. They call it prime. I just use to separate it from the other. They are the same arrow, just use something to differentiate it from the other. Alright, so if you want to draw, it's going to be what now? So then arrow signifies CnH2n plus. I did not say arrow signifies CnH2n plus 2, I said plus 1. So let's do it together. So it's going to be CnH2n plus 1 bond CO bond, another CnH2n plus what? 1. If I have 2 of it now, that's why I did what I just did. What about the alkanoic acid? This one, they are the C bond COOH, alright, which is basically same as what now? CnH2n plus 1 bond COOH. Everybody pay attention. These are exam questions. Alright. What about the esters? Esters are the arrow bond COO arrow prime. Alright. So basically we simply say that they are the CnH2n plus 1 bond COO bond CnH2n plus 1 as well, right? Yes, now. What about the ethers? They are the arrow bond O arrow prime, which is the CnH2, the ethers now, plus 1 bond O will give me what? CnH2n plus 1. Everybody pay attention. What about the amines? They are the arrow bonds NH2, which are the CnH2n plus 1 bond NH2. Are you there? What about the amides? They are the arrow bonds CO NH what? 2. Yeah, guys, don't worry, they're all easy. Arrow bond CO NH2. That's the amide. NH2 or word CnH2n plus 1 bond CONH2. So any compound with this thing, you call it an amide. Relax. What about the nitrile? They are the arrow bond C triple bond N or CnH2n plus 1 bond triple bond N. Class, you can see all these are the other families of these. All these on the board are the other general formulas of these guys. If you don't write them this way using R, you can tell me, okay, what does this R mean, which have told us everything. Class, are you there? Hope all these things are making sense to you. They are not hard. Practice makes perfect. Practice makes perfect. Practice makes perfect, guys. Practice makes perfect. Practice makes perfect. Now, guys, moving further, there's something very vital and essential I have to tell you. There's something very vital and essential I have to tell you. Very, very important. Everybody listen. Listen. These alkanals you are seeing, they also have another name. If you don't call them alkanals, you can call them aldehydes. Alkanals are also called what? Aldehydes. Alkanones, they also have another name. You can also call them ketones. They are the ketones. The ketones. Alright? Ketone. Alkanoic acids, they can also be called carboxylic acid. Carboxylic acids. Are you there? Esters, also called the alkyne alkanoids. Esters, they also call the alkanoids. Just pay attention. What about the eta-alkoxy-alkane? But these are those guys. Amine, amide, nitrile. Alright, we have to go. So these are the other names of these guys. Alright? So that is for that. Note all of those things so we can move further. Now there's something I want to tell you guys. There's something very important I have to tell you. You know, in organic chemistry, as we have what we call homologous series, so we have another very, very vital group called a functional group. What is a functional group, everybody? Now, by description, what we have drawn, we've been writing a lot of things on the board. We have been writing the functional groups of all these compounds. They have their functional group. They have their functional group. They have their functional what? Group. And I'm going to tell you, they have their functional group. And pay attention. like these alkenes, they have the double. Okay. Let me define functional group first. What is a functional group? A functional group, listen, is an atom, a bond, or a radical. It's not a big English, just listen. Functional groups are bonds, atom, or radical that are common to a particular homologous series, and it determines the main chemical properties of that series. Alright? And it's simply the set of chemical reactivity. Relax, I'll explain. A functional group could be an atom, meaning could be an element, could be atom or atoms, could be radicals, meaning different atoms coming together forming a charge, could be that, could be also a bond, alright, that is common to all families of a particular homologous series, alright, and this functional group, they are the guys that determine the main chemical reactivity of that family. Yeah, they are the one that determines the chemical behavior of that family. The kind of functional they have tells you their behavior. Relax. And also they are the main site of chemical reactivity, meaning if those guys are to react, the reactivity occurs in the functional group. Let me show you the functional groups in all of these things. Relax. Let's start with, okay, for the alkenes now, these guys, they only just double bond, which is normal, same in every other compound, so we'll leave it alone and start with alkenes. Alkenes, they have something special, which is a bond. So this a functional group now, I told us functional group could be atoms, could be radicals, or bonds. So you cannot see that in alkenes, they have their structure, they have bonds now, that double bond. So the double bond is the functional group of alkene. Alkene, the triple bond, is the functional group of alkyne. Now I told you functional group could also be atoms. Now going over to alcohol, this one, everybody pay attention. This is an atom, oxygen atom, hydrogen atom coming together. So functional group could also be atoms. So you can see that this is an atom. Do you understand? This is not a functional, this is an alkyne group. All the arrows are alkyne group. So all those other things that are not arrow attached to that arrow will be at the functional group in that compound. So guys, you can ask you, what is the functional group in alcohol? What will you tell them? What will you tell them? Don't tell them OH, you tell them bond OH. Tell them bond OH, bond OH, bond OH. Now let's move further. What is the functional group in alkanes? Is it arrow bond CHO? No, just state bond CHO, bond CHO, bond CHO. That is the functional group in the alkanes of the alkyne family, because that is seen in all of them. If you want to draw different alkanes, you see it in all of them. Relax. Whatever the alkanone, what's the functional group? Bond CO, bond CO bond, bond CO bond, alkanones. Whatever the functional group alkanoic acid, bond COOH, bond COH, you can see what I'm talking about. Whatever the functional group Ester, bond COR prime. No, prime is not homo. Just bond COR, you understand? So those lines, these are alkyne group. Whatever amine, bond O bond. No, what about Ester rather, bond O bond. Whatever amine, bond NH2. What about amide, bond CONH2. What about nitrile, bond C triple bond N. All these things are the functional groups. All these things are the functional groups. Guys, are all this making sense to you? Let me know. Guys, are all these things making sense to you? Let me know in the comment section so we can move forward. So all these things are the functional groups that are seen in this compound. All these are the functional groups that are seen in this compound. All these are the functional groups that are seen in this compound. Alright? Now we have to understand the structure of these functional groups, because it will help us as we go on in this class. I'm going to start with the alcohol. I'm going to start with the alkanals rather, not alcohol. Leave alcohol alone, it doesn't have a structure. Now, alkanals then, are you not seeing them here? Arrow bond show, right? This functional group we are looking at right now, it has its own structure. This is how we draw it. Everybody listen. This is how we draw the structure of alkanals. You draw, I tell you start from bond. Bond C. Alright? Bond what? C. Bond what, everybody? C. Because that's the first thing I'm saying. Bond C. Then there is a double bond. I can decide to draw it any direction. So bond C, just pay attention. Bond C, double bond O, bond H. Now, how did I form this? This thing alone. I start from here. Bond C. Now, it's not CHO that I say. It's not CHO you're saying. This is the structural form of the functional group alkanals. This is the structural form for the functional group alkanal. It will help us a lot to note it, guys. Alright, now why did I do like this? Let me just tell you, these alkanals, they have this connection always. Carbon, the way carbon connects with oxygen is a double bond. Carbon does not connect with oxygen with a single bond. Carbon connects with oxygen with a what? A double bond. There are reasons, alright? But for now, notice it. The way carbon is, now you have, even if the oxygen is not closer to it, carbon should still combine. It is the carbon that is bonding with the elements, not these two guys bonding with each other. Carbon is the baba of them all. So it's one bonding with everything. So you can see that that's why carbon is tetravalent to basically connect itself to different things. So if you observe now, how many bonds are seen here? Still correct. 1, 2, 3, 4. You can see this is structural form for alkanals. Class, are you there? This is structural form for the functional group for alkanal. Guys, are all this making sense to you? Guys, are all this making sense to you? Now let me tell you something. When you draw a compound and you automatically just see this group, alright, in that format, a C bond, a C double bond O group, they call it the carbonyl. Hey, what is it called? Carbonyl group. So in your exam now, they can ask you now, can you give me examples of homologous series that have the carbonyl group? One of them is called what? The alkanal. That C double O itself is called carbonyl. That C double O, what's it called, everybody? Carbonyl. Carbonyl is seen in the alkanal. You see them in other families very soon. You see them in other families very soon, as the case may be, as we move further. Class, hope you guys are following me. Alright? Alright, so let us move further. Okay, so that is for that. That's how we draw the structure of the alkanals, the functional group specifically of alkanal. We're going to see it in structures very soon. Just relax. So let's get into next. These guys, which is the alkanone. I told you I was going to start from here. So the alkanones. So I'll be wiping the board so I can have space to basically work on them. Alright, I'm going to reduce the pace, alright? So as I was saying, the way these things are connected, carbon is the guy that is bonding with these two elements. It's not these two elements that bond with themselves. Do you understand? So carbon is one bonding with them. Do you understand? So carbon will bond with, and the way carbon bond with oxygen, whenever carbon sees oxygen, is a double bond. It's a double bond, guys. It's a double bond, note it. Alright? So one wipe, so I can move over to another one, which is the alkanone. So watch alkanones now. Watch what I'm going to work on alkanones to move forward. Watch the way I'm going to work on alkanones so move further. Alkanones, they are arrow. Okay, just let's pick the functional group. The functional group is arrow bond C. Yes, now just picking the functional group. I'm not picking the alkyne group. I'm just picking the functional group. Bond C O. Bond C O bond. All right, bond C O bond. Bond C O bond. That's how we're picking it. So in this case, now you can see there's no other element, just carbon and oxygen. So you know how carbon will bond with oxygen with a double bond. So bond C double is always going like this most times. And you can see now, it's always going, carbon has bonded with this oxygen with a double bond. This bond still remains and is here. Do you understand what I'm saying? This bond still remains and is here. I can start to put this one up, I can start to take it up, and it's just my choice. I can start to take it up so show you that okay. So it should show you what I'm doing. Because are you saying? I can start to bond C double bond O bond. Do you understand what I'm saying? I can draw it like this, just my choice. Bond C, alright, double bond O bond. You understand what I'm saying? And now you can observe that they stay carbonyl. So another example of compound with this group called the carbonyl group is what? Alkanones. The alkanones, also regarded to call it ketones. Alright, they have the carbonyl group. The carbonyl group. The carbonyl group. The alkanones, also called ketones. They can ask you which of them have the carbonyl group. What will you say? The alkanones or ketones. The alkanones or what? Ketones. Alright, we talked about alkanes having carbonyl group. Alright, so let's talk about the alkanoic acids. Remember, we are picking their bonds only to draw their structure. Alright, so I'm going to wipe this one so I can work on the carbox. The alkanoic acids also called carboxylic acid. Can I wipe? Yeah, I can. Carbonyl, that's the C double one O group, the carbonyl group. The carbonyl group, everybody. Pay attention. So now the next one is I'm going to pick I'll pick bond COOH. Alright, bond COOH. Now if you observe what is happening, we have like, I know you want to like say something. Okay, you saw two oxygen now, and in your mind, the way carbon will bond with this oxygen, double bond. No, now we have to ensure that we still obey carbon. Most times, carbon, if there are two oxygen, carbon will bond carbon will bond with one of the oxygen with double bond and the other with a single. No, the other end, let me tell you how it works. This oxygen is combined with this one guy. This oxygen is attached there together in this case. Hey, look at what I mean. Bond C double bond O, and this carbon is still bonded with OH. Class, are you there? See now, class. Like the class, you don't do it like this. I know you're gonna say, okay, you want to bond it like that, and now go and allow it. Don't do it like that. You are spoiling it. Carbon monoxide bonds 1, 2, 3, 4, 5. No, they will be together. Guys, if you can hear me, let me know. I had to change network. If you can hear me, let me know, guys. Quickly do that. Let me refresh this router. For now, I'm using my phone network. So after the router is on, I'll connect it back. Alright? So that is for that. So guys, alright, so let us move further. So as I was saying, here, you can see what we are on the carbon deal. You can see what we are on, right? Here, we're talking about this alkanoic acid, the way they bond. Always know that whenever, even if you have more than one oxygen, carbon first of all will bond with one of the oxygen with a double bond. You understand? With a double bond, right? Without it, most likely to combine with whatever is attached. Do you understand? Because it should not go, there should not be another, you can see it not exceed it, so that's why it should be like this. Class, are you there? Hope all these things are going well. Hope all these things are going well. Network can be really crazy right now. First, is it okay? Let me know in the comment if the network is okay. Let me know in the comment section if the network is okay. Let me know in the comments if the network is okay, guys. Alright, good. I'm trying to, my router is not on, like it's still loading. Oh my god, I want to use this router on my phone, like I don't trust it. The network can just, go away. Alright, no problem. So now Ester, same applies to the esters, alright? So same applies to the esters. I believe you guys are sharing all the things we're doing, right? For the esters, it is R bond C O bond, right? So then you're going to be bond C double bond O and bond O. You understand what I'm saying, right? Yes now. Yes guys. Hope it's making sense to you. Yeah, hope it's making sense to you. Yeah, guys. Hope it's making sense to you. But one, like the carbon is 1, 2, 3, 4. You're not seeing the structural form of carbon. Sorry, the structural form of the way the guy is. Are you not seeing for instance? Are you not seeing for instance? Okay, we can literally just add the other arrow. But these are like, I want to tell you that esters, they have the carbonyl. So the arrow can be attached here. If you want to draw everything, you can literally just add the arrows to everything. Same applies to the ones we have done initially. Alright, so you can see the carbonyl. So you can see we've talked about 3 different compounds with carbonyl. Alright, or 4 say alkynes, they have carbonyl. Alkanones, they have carbonyl. Even these guys have carbonyl. These guys have carbonyl as well. Alright, so alkanals, alkanones, alkanoic acids, and esters, they have carbonyl. Class, are you there? Are you not seeing the carbonyl group? Are you not seeing the carbonyl group? Are you not seeing it? Class, aren't you seeing it? Is this something we are guessing? We're not guessing it. There are a lot of them though. Alkanals, alkanones, alkanoic acid, esters, even we're going to work on them. Alright, we're going to work on them right now. I think the router is on. I'll just use my phone for some time and change over the router soon. Alright. So that is for that. Now what about the esters? How do we draw them? No, ethers, because this one we just drew is ether, ester. So for the ethers, look at them, ethers, arrow bond OR. So this one is still bond O like this. This is how they look like. Ethers, this is how they look. This is the functional group. Alright. So now let's get into amine. Amine is just functional group that bond NH2. Alright. Where the amide is bond C double bond O NH2. Yes, now look at it. You know, carbon always bond with oxygen. Yes, all the classes will be saved. You get to see them after everything, so there's no problem. Alright, so that is for that. You can see how amide was drawn, and same applies to the nitrile. Alright, so amide, you not see the carbonyl, so amide has a carbonyl as well. Amide has a carbonyl. Nitrile is just R, just bond C triple bond, and this is a functional group. You understand? So that is for that. You can see how we've been able to work on all of them. So at least it will make sense when you go into organic chemistry. All these things will make sense to you. Oh, all right, guys. Let us move into things that I know that are extremely very important for us to learn. Guys, is the network okay now? Please let me know. Because somebody just said network. Is the network okay? Oh my God. Is the network okay now? Jesus Christ. It's okay at my end. Oh, you guys should not make me scared. Alright, let me try and change the network right now. There are a lot of things to learn, Hannah. Don't worry. Relax, relax. There's a lot of things to learn. But no problem. Let us, if you're tired, you can go and sleep. And we'll come back later. Maybe you can wake up in the morning and still see us here. You can wake up in the morning and still see us here. Alright? Let's see how it goes. Alright, we've been able to work on all of these and understanding all of the homologous series, all of the alkyne groups and functional groups. So let us go further and tell you guys something. I want to tell you guys something. Pay attention. There's something I'm going to tell you guys right now. There's something I'm going to tell you guys right now. Pay attention. Pay attention. Pay attention. Alright? Pay attention. Now, you guys have to understand that organic compounds can be saturated. Everybody knows what I just said. Organic compounds can be saturated and unsaturated. When I say an organic compound is saturated, what do I mean? You know, when I tell myself, I am saturated, when I'm done drinking water, I am full. I am saturated, I'm full. When I'm saturated, I mean that I'm not full yet. I still can drink more water. You understand? So when a compound is saturated, it means that compound is full. There's nothing you can add to that compound. Now let me just tell us right now. For the three major hydrocarbons, alkenes are saturated. Alkenes, and the alkynes are unsaturated compounds. Alkenes are saturated. Alkenes and alkynes, they are unsaturated. Note that. Alkenes, let me show you what I mean by it. Let's draw an alkane quickly. Hope you know an alkane. Now remember, use the term or the concept of, hey, I am full, so there is nothing that can be added to me. While for unsaturated, I am not full, there's still more things that can be added to me. You understand? So on these, look at this structure. Can I add another thing here? No, I cannot. Because if I do that, I'm going to spoil the compound. So alkanes, they are always full. There's nothing you want to add to them. Do you understand? So there's a reaction we're going to learn in organic chemistry today, which is basically called addition reaction. It is not seen in alkanes. Alkanes do not undergo a reaction that you add things to them. The only reaction they can undergo and other things is what we call combustion and also substitution, where they substitute things. Relax. What about alkenes and alkynes? Let me draw an alkene. Alright, alkenes like this, right? H, H and H and H, right? This is an alkene. I won't go to the structure. I can literally add things here. The way I can add things by breaking a bond. I'm going to teach us organic reaction very soon. By breaking a bond. When I break this bond, I break my card. If I want to form two parts, right? One of them will come here, another will come here. So automatically I've added H. Do you understand? So I've broken this bond. So with this now, the things can be added to them. The same applies to alkenes and alkynes. Then they are unsaturated, they are not full. Do you understand? So I believe you know the difference between saturated and unsaturated compounds now. Saturated and unsaturated hydrocarbons, because they're still hydrocarbons. So if they ask you which of the following is a saturated hydrocarbon, alkenes are saturated. Which of the following they are unsaturated, alkenes, alkynes, they are unsaturated hydrocarbons. Alright, things can still be added to them, so they are unsaturated. Alright? So that is for that. That is for that. Let us move further. We'll learn about saturated, unsaturated, and the rest. Let us move further. Guys. We are good. We are getting there. Alright, that is for that. Let us move further to learn other things. Talking about Alright, with all this said, I'm confident to go into this aspect called IUPAC nomenclature. Let's name compounds together. Let us learn how to name compounds together. Alright? Let us learn. Alright. Let us name compounds together. If you're exhausted, go and sleep. Come back tomorrow, you get to see us here too. Alright? Don't be tired. You have to be strong. When I started this class, I was so tired. Oh my God. Alright, let us go further. So, let's get into this concept. We call it IUPAC nomenclature. IUPAC nomenclature. What does this aspect of organic chemistry talks about? IUPAC nomenclature. Let's work on it right now. IUPAC nomenclature. Alright? On IUPAC nomenclature, IUPAC simply means International Union for Pure and Applied Chemistry. They are union that basically teaches chemists on how to name compounds, right? Not just that, other things they do. Yes. So now, there are the people that work about this naming of compounds. Now, let me just basically brief us about IUPAC nomenclature because it's very cheap and very, very vital aspect in your exam. Alright? So let's start with IUPAC nomenclature. How does it work? Let us work it together now. IUPAC nomenclature, guys. Now, there are rules to name organic compounds. What are these rules? Number one, write it in your notes. I'll just give you some brief rules. Number one, identify the longest continuous carbon chain. That is the first rule, guys. Identify the longest continuous carbon chain. Rule number two, after identifying the longest continuous carbon chain, relax. Name the chain you have identified. Number two, name the chain. No. Don't name it yet. Number two, number the chain. And what I'm saying? Number the chain. That's number two. Number the chain. Number three, name the chain. Number three, name the chain. Number three, you name the chain. Number four, identify substituents or branches. Identify substituents or branches. Number one, I repeat. Identify the longest continuous carbon chain. Number two, number the chain. Number three, name the chain. Number four, identify any substituent or branches. And the last rule rather, give that substituent a number. Give that substituent a number. in bracket, a low number as possible. Give that substituent a number, in bracket, a low number as possible. A low number you can think of, alright? A low number you can think of. That's what you do. A low number you can think of, guys. Now, let us work it out together. Now, I just gave us the general rules, but in my naming, I can name some compounds and I'm not going to use all the rules. Are you there? Just relax. Let's start from scratch. If you are still learning, let's start from the scratch. So let's say we have a compound, your JAM exam or WAEC exam or post-UTM exam gives you this to basically name. How will you name this compound? Very easy. So now this is hydrogen, 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 and this is hydrogen. Now what's the first rule? Identify the longest continuous carbon chain. Wow. Oh, look at this compound. Try to look for the chains that carbons are connected together and identify the longest. In this case, the longest continuous carbon chain is what I'm seeing right now in this horizontal fashion, right? Yeah, I've identified the chain. Now the next rule, number the chain. Yeah, that's what I said. And oh, did I tell you the direction to number? Oh, okay, note it. When you are numbering the chain, number forward and backward. Everybody, number forward and backward. So forward numbering 1, 2, and 3, and number backward 1, 2, and 3. You can see what we have done. A, number the chain. After numbering the chain, give this chain a name. Give this chain a name. Now, number forward, number backward, we have 3 carbons. So I told us an organic compound with 3 carbon. What is the name of that compound? That compound name should start with prop. What did I say? That compound's name should start with what? Prop. That compound's name should start with what, everybody? Prop. Prop, right? That compound's name should start with what, everybody? Prop. You know what I'm saying, right? That compound's name should start with what? Prop. Alright, that compound's name should start with prop. Coming. That compound name should start with prop. All right. Now, moving further, now if you observe, there is no branch, there is no substituent here. Because you cannot tell me that hydrogen, hydrogen is a normal thing. When you don't see hydrogen, you see something else. That thing you are seeing is a substituent. We are going to learn how to name all of those kind of compounds. So that one, which is identify the substituent or name the substituent, we are not going to apply it here. Do you understand? There is no substituent. So and the longest continuous carbon chain is what we are seeing, and basically it's prop, right? 3 carbons, right? So now observe what is the name of this compound. What family does this compound belong to? Now check your carbon-carbon connection. You see that they are all single bonds, and this compound name should end is an alkane, right? So this compound name should end with propane, guys. This compound's name should end with propane. You understand? Because it's an alkane. And you there? That's how it works. So that's how it works. Now let's move on into more examples. Alright, they're all easy. So this is another. So carbon bonding with carbon. Just pay attention, bonding with another carbon and bonding with another carbon. So basically what we do, I'm the one doing it, I'm the one asking the questions, and I'm still the one solving them. They're all easy. This is how you come in your exams. So pay attention. This is H, 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 and this is H, right? So what do we do, everybody? Okay, now, at some point, I want to put here as CL. Class, are you there? I just put there as CL, relax. Now, you're looking at CL here, in this compound. Automatically, the CL we are seeing right now is a branch. Yes, now, it's a branch. It's something that is special in this compound. It's something I've not seen before. I just saw it. It's a branch or substituent. So we have to ensure that we include it to our number, to our name of the name of this compound. What is the first rule? Identify the longest continuous carbon chain. Oh, when carbons are connected, look at them. Identify the one that is longest. And all the carbons were all arranged in this horizontal fashion, which is not always the case. You can see other branched compound that carbon will come down. So you have to basically identify the one that is longest. So I'm going to work on these examples. So this one that is the horizontal is the longest. And what's the next rule? Number the chain. Number forward and backward. So this is 1, this is 2, this is 3, and this is 4. This is 1, this is 2, this is 3, and this is 4, right? So after we've done this, everybody pay attention. After we've done, what do we do next? What do we do next? Tell me. I told you something now. Okay, after name the chain. The chain is 4 carbon. Oh, good. The name should start with good, right? And all the carbons are all connected by single bond. O is an alkane, so the name should end with butane. But now there is a substituent. We have to ensure that we treat our substituent like a guest. Treat the substituent well. And I told you this substituent, you should ensure that it has a low number as possible. And the number for a substituent is solely dependent on the carbon it is same. And I told us make it the lowest number. So when you count forward, you can see the importance of that counting forward and backward. If you count forward, this, everybody listen. If you count forward, the substituent, leave all this downward counting. Count forward. The substituent was at carbon 3. Yes, now. No, look, leave these ones. Count forward. See, close your eyes from these things. Count forward, everybody. Is at carbon 3. Are you there? Yes, sir. Count forward is at carbon 3. Count backward. It has 1 carbon. Leave up now. Count backward, carbon 2. Ensure your substituent have a low number as possible. Alright? So that's what. Do you agree with me that the best number to go for is it? Now, let me tell you, this is chlorine. You know, in organic chemistry, we call it chlorine. But listen, in inorganic chemistry, you know, like organic periodic table is called chlorine. But in organic chemistry, the name will actually from chlorine to chloro. Alright, since it's in a compound, it changes to chloro. Do you understand what I'm saying? If it's bromine, it changes to bromo. Normally it's bromine, but it changes to bromo. If it's iodine, it changes to iodo. If it's fluorine, it changes to fluoro. Are you there? So in this case, it's chlorine. Is that carbon 2? That's the best number. So counting forward, we have it to be 3 chloro. Counting backward, we have to be 2 chloro. And I told us we must ensure that the substrate have a low number as possible. Everybody, pay attention. Are you there? Listen. Now, let me tell you something. Between numbers and letters, we use dash to separate them. Do you understand in organic chemistry? But we are not going to go for this because this one is longer. And I told us we ensure that our substituent have a low number as possible. So the best number is 2 chloro. So you now put the substituent, and the number in front of the compound. So 2 chloro. Is there any other substituent you can see? No. 2 chlorobutane, that's the name. 2 chlorobutane. Class, does this make sense to you? Does this make sense to you? Let me know in the comment section if this is making sense to you. Let me know in the comment section if what I just said is making sense to you. Let me know in the comment section so I can move further into more examples. Let me know, guys. Good. Alright, I don't know why I can move further. Relax, they are all these. They are not hard at all. Relax, Let's name as much we can name. I'll go to your jam pack, we're going to look for questions, alright? I'll name them, they're all easy. But first, let's just be thinking of anyone, bring them, name them together. So let's say we have another. This one is carbon, bonding with carbon, bonding with carbon, and bonding with carbon. And this time around, there is a chain. That's another branch coming down. Pay attention. Now this one automatically becomes H, and the one doing it, H, and what's H, right? And here automatically become H, and H, right? So now everything is okay. What did I tell us? You identify the longest continuous carbon. That's the rule, right? That's the first rule. So let's identify it together. Now think, is it in the horizontal? I told us it's not always in the horizontal. Think, look at all the places carbons are connected. I can see that, carbon, because when I count like this, it give me for 1, 2, 3, 4. 1, 2, 3, 4. Is it the longest? No, it's not. So the longest is 1, 2, 3, 4, 5, 6. Guys, are you following me? Yes, now. So this automatically becomes the longest counting. Class, are all these making sense to you? This automatically becomes the longest counting. Class, are all these making sense to you? We can now go and take with this 4 now. So that was 6, 1, 2, 3, 4, 5, 6. So we've been able to determine the longest continuous carbon chain. So since we've been able to determine the longest continuous carbon chain, guys, automatically automatically what was not added in the chain will now become a branch or a substituent. And if you observe, this guy now is not part of the chain, so automatically it's a branch on its own. So this one is CH3, so I'll clean it and now add it to the guy. This guy is automatically a branch, so it is not part of us, which is the longest continuous carbon chain. So it automatically becomes a branch. So after doing all of this, let's number forward and backward, which is the rule. After identifying the longest continuous carbon chain, let's number forward and backward. Let's do it together. So this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Let's do it backward. This is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So counting, we had eggs, right? And all the carbon, they are all single bonds connecting themselves hexane. Now, automatically there is a substituent here, or a branch, so we should ensure that we treat it right, alright, making sure that it has a low number as possible. So what do we do, guys? Do we count forward or backward? Which of the counts should we go? When we count forward, is that carbon 3. When we count backward, let's do 1, 2, 3, 4. Is that carbon 4? Hey, when we count forward, what number now? It's not carbon 3. When we count forward, it's not. When we count backward, it's not carbon 4. Which one do we go for the lowest number now? Automatically, hope you guys are aware that this one is called methyl. We've established all of these facts initially. So this is called methyl. So automatically, this guy becomes what? We're going to use automatically this one, it will go away now. We cannot use this longest number now. This one gave a big number for our substrate, which will have to treat it right to give it a low number. So it's going to be what? 3 methyl. I told us now. We add the number of carbon to the branch or the substance. So 3 methyl. Alright. So the name of the compound is 3 methyl hexane. That's the name of the compound. 3 methyl hexane. Class, hope is making sense to you. So the name of this compound is 3 methyl hexane. Class, hope is making sense to you. The name of this compound is what? 3 methyl hexane. Class, is it 3 methyl hexane? Let me know in the comment. Is it 3 methyl hexane you got as well? Let me know in the comment. We're going to name a lot of them today in this class lesson. So get ready. So the name of this compound is what? 3 methyl hexane. 3 methyl hexane. Can I wipe the board now? Can I wipe the board now? Good. Good. Let me go and find other compounds. I want to wipe the board. I want to wipe the board, guys. I want to wipe the board. Yes, pay attention. Pay attention. So now, let us now name another one with, if you observe things, we'll be naming the compounds with just one branch or one subsequent. Now let's name another compound with like 2 branch or 3 branch. Let's say it goes 2 or 3 branch. So let's work it out together. So this is a compound, carbon bonding with itself, carbon bonding with itself, carbon bonding with itself. So this time around I have BR. This time around I have another carbon. I have Cl. So let's name it together. Let's see how we're going to work on this. They are all easy. They are all very, very easy. They are not difficult at all. They are all very easy. They are not difficult at all. Okay, first, let me basically work on identical ones, BR. Alright? So guys, let's work it out together. So what do we do? What's the first step? Identify the longest continuous carbon chain. That's the first step, right? So there's no branch. So the longest continuous carbon chain automatically becomes what I'm saying in the horizontal fashion, or not always the case. You saw the previous one. So let's number forward and backward. 1, 2, 3, 4, and 5. Let's number backward. 1, 2, 3, 4, and 5, guys. So we must ensure that our substance have a low number as possible. Relax. So it has 5 carbon, the name should have with pens, right? And they are all single bonds, is pentane. Now, if you observe, counting forward, everybody. Counting forward, what was the numbering? We have 2 substrates and they are the same. Bromine, going here, call it bromo, alright? So what do we do? Let's come forward and look at numbering. One counted forward, at carbon 2 we have the bromine. Forward, leave backward alone. Leave this one. At carbon 2 we have bromine. So I call it 2 bromo. This one was on forward counting, right? And now moving further, at carbon 3 we have bromo. At carbon 2 I have bromo. At carbon 3 I have another bromo. So 3 bromo. Are you there? So now, let's count. There's no other branch now. So let's continue. 1, 2, 3. Oh, at carbon 3 I had bromo. So this for backward. For backward counting, at carbon 3 here I had bromo. So So we start with 3 bromo, and add carbon 4, add another bromo, 4 bromo. So we must ensure that our numbering is low. Add them together, it gives us what? 7. And add these 2 guys together, what will give us 5. So when we go with the forward counting, like I said, you must ensure that your number have a lower number as possible. So the forward counting in this case wins. So the name of this compound, now since it's 2 bromo, 3 bromo, they're identical. They're identical, everybody. So this is how it works. So when you have a substituent that is identical, you will now use what they call prefix. Prefix includes mono, di, tri, tetra, relax. So call it, you numbers bring them together, so 2, 3. Are you there? Now, numbers are separated by comma, not dash, comma, 2, 3. And then I say 2, 3 bromo, pentane, no, nah, use a prefix. They call it, so there are 2 now, it's going to be di, bromo. They call this one prefix. Class, are you there? Prefix. It's called 2, 3 diagram. We don't just want to go back up, we will not go there. 2, 3 diagram. It will not go. Class, are you there? Let me know in the comment section. Class, let me know in the comment section if you are following me. Alright, let me know in the comment section if you are following me. Let me know in the comment section if you are following me. Let me know in the comment section if you are following me about what the name I just gave now. Let me know. Let me know. Sorry, no. Sorry. Hold on. Just know it's going to be di, bromo. Alright? Alright, guys, I believe you're following me. Alright, no problem. We can call them prefix, you understand? But what I want to tell you guys right now is that you should understand here that, like, you should basically try to tell how many of each of them. You really wrote that because we have 2 bromine. Do you understand 2 bromine? That's why it's dibromo, what now? Pentane. The longest chain is 5. That's 5 carbons, so it's pent. And they're all single bonds. That's why it's called pentane. Alright? I can literally use small letters. Let's use small letters. Anyone. All that matters is that you know what you are doing, right? So let us move further to another question. So I'm going to wipe the board so I can move further to more questions I can think of right now. Everybody pay attention, listen and listen well. Listen and listen well. So this is another compound. This is another one. So in this case, we have CH3 here. I have B. We have Cl here. Alright, so here include HH and everything. So guys, let's identify the longest continuous carbon chain first. You have to be very smart. We have to be very, very smart. We have to be very, very smart. You have to be smart as a student, so you have to be smart as a student. Alright, if you observe here, counting in the horizontal fashion, we have 1, 2, 3, 4. There's also another was connected. So let's try and look at this one. 1, 2, 3, 4. Oh, the same numbering, so I can literally do any of them. Counting like this, counting like this, counting like this, the same number, so it's 4, 4. Okay. Class, are you there? Okay, let me write H here. Let me write H here and put CH3 down. Class, are you what I'm the same thing, just the same thing. So 1, 2, 3, 4. 1, 2, 3, 4, same number. What if, for instance, I change it from CH3 to C to H5? What do you do as a student? So have this in mind that you have 2 carbons here. So now, this one will not be the longest number. This will not be the longest. But now it's 1, 2, 3, 4, 5. Because if you elongate this C to H5, everybody listen. This is H5. If you elongate it, C2, you have 2 of it, and H5. Alright? H, 1, 2, 3, 4, and 5. So if you observe now, you see that this one will give you the longest number. Plus, are you there? It's not hard. automatically this that is not among will not be a substituent, alright, which is the CH3 substituent. Guys, are you following me? Alright, so that is for that. So automatically this also, these are substituent, this is substituent. So let's number 1, 2, 3, 4, 5. Now pay attention. 1, 2, 3, 4, and 5. Guys, are you there? So counting forward, everyone listen. Counting forward, what did we get? That's the question you're asking. Counting forward, what did we get? When we counted forward, we have 1, 2, 3. So 3 methyl. Everyone listen up. 3 methyl at carbon. Oh, sorry, even 2 methyl, 2 chloro first. This 2 chloro first, 2 chloro and 3 methyl, right? You know this one is methyl now. Alright? So let's come backward. So at backward counting, 1, 2, 3. So backward. Backward, guys, hope you are following me. Backward gave us 3 methyl and what 4 chloro. Very bad. Alright, we can't go with this. 4 chloro, we can't go with it because this one is bigger. Alright, 7 and this one is 5. Alright, it's not always like this, so you know, we just mentioned we're having the same 7 and 5. Alright, so go with that one that is the smallest. Alright, so the name of the compound will now start with 2. You know it's 2 chloro. You write 2 chloro first, so not because, even if for instance we had 2 chloro next, that's number 2, write it first, but alphabetically C comes for M. So 2 chloro, 3 methyl, and the longest chain is how many? 5, so it's pentane. So the name of this compound is pentane. Why? If you observe, I told us between numbers and letters we use dash. Numbers and letters dash. But between now I cannot say 2, 3 dichloromethyl. No, they're not the same. If there were 2 chlorine groups, so it's going to 2, 3 dichloro. If it was 2 methyl group, we're going to maybe 3, 3 dimethyl, something like that. But we cannot do that here because they're different. They're different families. Alright? So that is the name of this compound. I believe that this to some extent we have understood how it works. So let me name another family. Let's say the alkene family. The alkene family, guys. The alkene family. Can I have alkene family right now? There's no how you see questions on naming that you will not be able to solve in your exams. They are all easy. So let's name the alkene family, everybody. The alkene family. Let us name it together. So maybe I'll draw this one first. C double bond C bond C. Alright, here is H. 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 Alright. Continue. Guys, hope you are hearing me. Guys, hope you guys are following me. Let me know. Oh, it's blurry. Network is so bad. Sorry about that, guys. Now, let me try and change my network now. Let's see. On-chain network. Just very stable now. Yeah. All right. So now let's identify the longest. Normally, identify the longest continuous carbon chain. Okay, let me press a little bit so we're able to settle before I move further. All right. So, guys, let us move further. Let me know if you can hear me and if the network is okay or better now. Let me know in the comments. Alright, let me know in the comment section if network is okay. Let me know in the comment section if network is okay. Better now, better. I've changed it to the router's network. Alright, so let us move further. Alright, guys, let me know if the network is better now. Let me know if it's okay now. Let me know if the network is okay now. Let me know if the network is okay. Let me know if the network is okay now. Is it okay now? Let me know. You know, router, I'm crazy. I just put it off and continue using my phone. Guys, let me know if the network is okay now. Guys, let me know if the network is okay so we can move further. Guys, let me know if the network is okay so we can move further. Alright, it's better now. Alright, so you can see how the compound was named. So now, me calling it 2-butene, I can literally call it this. I can call it, start with the boots. Alright? Are you there? Boots. I'll start with, I'll put the number at the middle. 2 in. You can either name it like this or like this. So, 2-butene, 2-butene, or butene. You understand? 2-butene or butene. Guys, are you there? Alright? Why did I give it 2? Because I told us the non-brain should go with it. Even if I'm not stressing it right now, or no, I'll be forcing it. Even if I'm not forcing it right now, I hope you are still following me. Right? Not because I'm not shouting you. I'm really stressed out. I won't lie. Alright? So now, the point I'm trying to make here is this. We have it's between 2 numbers, right? You should go with the lower number. That's why it went with 2. You understand my point? That's why it went with 2. Alright, so that is for that. So I don't know why the I can move further to other compounds that are alkenes. Other compounds that are alkenes. Other compounds that are alkenes. Everybody pay attention. So these are another one, carbon burning with carbon, bonding with carbon, maybe the double bond, and here there is Cl, there is, let's say Cl, here, let me see how smart you are now. Let's work it out together. Now, we must always ensure that we respect our functional group before anything else. Guys, we respect our functional group before anything. Don't go and respect a substituent and don't respect your functional group. Respect your functional group first. The rule is to identify the longest construct which we have done, right? Name, number, forward and backward, right? So let me just tell you, whenever, okay, let's just number 1, 2, 3, and 4. 1, 2, 3, and 4. The point I'm trying to make right now, respect your functional, respect, meaning that your numbering now, in this case of questions, you are not going to use the forward counting. It's not always like this, so that's why you must look. Count forward and backward. Respect meaning that your counting should always come from the side that the functional group is closer to. This is a functional group, this is substituent, this is a functional group, this is. Respect your functional group, guys. Functional group is a site of chemical reactivity now. It's not where if this guy want to fight you or not, it's not here that the reaction will occur. If this guy want to basically, do a lot of things, the chemical properties determined by these things. So you want to respect something that came from outside, and don't respect the roots. Don't do that. Alright? You respect the substituent, the functional group. So the numbers should start like this. Do you understand? Even this one had big glass, it's none of your business. You respect the king. Are you there? So that is for that. So moving further, what we do everybody? We basically ensure that now if you observe that between now this one is already gone. Do you understand my point? This is already gone. This is seen in other kinds of compounds with functional groups. Are you there? So this is already gone. So I told us now it's between the functional group double bond in is 2 and 3. Now it's still boots, right? It's still boots, right? Now 2 and 3, right? Sorry, between 1 and 2, so give 1. 1 butene. But we cannot go and use 1 butene in this case because now there is a substituent. So the name will now be listen, but 1 in. So then the something number should not come first. If you observe that we were in carbon 3. So that's like 3 chloro and another 3 chloro. Are you there? We have 2 chlorine, so it's going to be 3 dichloro. Are you there? Yes, now we have this chlorine group at carbon 3 in both this side and this side. That's why it's 3 dichloro butane. So the name of my is 3 dichloro butane. Guys, are you following me? Guys, are you following me? Guys, are you following me? Hope we are on track, guys. Hope everything is going well. Hope we are on track. Let me know. Guys, hope we are on track. Let me know in the comments so we can move further. Hope we're on track. Hope we're on track. Hope we're on track. I want to basically do something. Let me go and find past questions on naming first, so I can basically work on that. Not that okay, I'm done on naming. All right. We're gonna work on a lot. There are a lot of compounds to learn to name. No problem. Work on them. I'm gonna find them, man. They are not hard at all. They're not hard at all. Alright, I just saw another one in your jam pack. So let's work it out together. So now we'll basically wipe the board. So I can bring this one I just saw based on this alkene. Everybody pay attention, pay attention. Look at the compound. They condensed it. Even if they condense, you as a student, you basically make it easy for you. They don't, what they wrote here is wrong, but let me just correct it. Here is CH2. Here is C. They just wrote a lot of things. But no problem, let us work on what they wrote. Let me just write CH and CH and bonding with CH2. Let me, now these are the group, bro. Though they won't do something worse than this are drawn on the board. Let me elongate it. That's why, as a student, don't be saying, yeah, pro, you want to just name it like this. I can name it like this, but relax, do it small. Break it, open all the chains. So this one now, you have CH3, so CH3. And you're not seeing it, H, and H. This is bonding with this C, so it has bonding with this C. So now, H and H. What they wrote here was CH3. Do you understand? Where would that, you now can put H here, no, now, you continue. That's why it should be CH2, that's what they wrote here. Alright, no problem. So this one is also going to be, so this one should be what now, C bonding to H. Alright? And actually it should be CH2. Alright, it should be CH2. We just wrote things in the last question. But no problem, let us move further. This one going to this. Hope you are seeing the hand. This one going to this now. This one is going to this. Now, this one will now have one bond because there's a double bond here. Yes, that's correct. This one cannot have two now. Because if you have two, it will not be another bond. And it doesn't make sense. So it already cause problems. It's not five. Do you understand? That's why bring it out, guys. Alright, and this one is C, and this one is an H. We are okay. CH2, you can see everything is okay. So let's name it together. This is what the jam brought. So what becomes the name of the compound? Very easy. What becomes the name? Tell me. And then I always sometimes about this is name it forward and backward. I told you guys, you already ensure that our numbers are from the functional group. So you can name it forward and backward. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So you have to ensure that, look at now, your something now, your function now be big number 4 or 5. No, now, should be 1 or 2. So in this case, keep the lower number. So it's pen, so it's going to be what now? 1 pentine. There is no branch. You understand? There is no branch. 1 pentine or pen, 1 ion. Or pens, 1 N. You understand? 1 pentine or pen, 1 what? Ion. Class, hope it's making sense to you. Hope all these things are making sense to you. This is what they brought in their pack. And the first question, that's it. It's very easy. They're not hard. They're not hard. A lot of them are here. So you just need to lay your hands on them. They're not hard at all. Practice makes perfect. Let me bring this one I saw here now. Guys, they are not hard. Practice. I can see a lot of them here. You'll be able to follow all these. There's no way you'll not be able to solve all these things here. Right? They're not hard at all. They are not hard at all. They are not hard at all. Guys, they are not hard. And they're not hard. They're not hard at all. Let's basically move into other things that are vital to us right now. Alright, so since I believe you'll be able to name all compounds. Now let me just tell you something very important. Now, you know, we've talked about alkanes, alkenes, and alkynes, right? Now, on the hybridization, let me just tell you, all compounds that are single bonded, like the alkanes, they are sp3 hybridized. Compounds that are double bonded like the alkenes, they are sp2 hybridized. Compounds like that are triple bonded like the alkynes, they are sp hybridized. Benzene, they are sp2 hybridized. Look at what I'm saying now. Alkanes, note it, though there are reasons for all these. Alkanes generally are sp3 hybridized. Alkenes are sp2 hybridized. sp3 alkynes are sp hybridized. We talked about all these, and benzene, they behave like that, you know, that guy now that has the EDE and EDE. Do you understand? They are also sp2 hybridized, though there are reasons for all these. But for the exam sake, I saw me opening this jump pack, I saw one question on that, and the answer is is on this thing I just wrote on the board. Let me go and find it out. They said question based on what I just wrote on the board is, it's not a brief question, very cheap. The hybridization of carbon. Because all these are for the element carbon of carbon atom in a time is what? Look at the compound, look at the name that ended into ethyne. Ethyne is ESP T, there's no sp4. What have you write instead? There's no sp4, so I cannot put in the option. Let me just change it to be maybe sp. Option B, sp2, dsc, sp3, and G, sp3d. Class, what's the answer to this question? Very cheap. If I told us anyone with iron, the relation should be sp, so the answer should be option what A. You understand? It's a jump pass question. They are all very easy, they are not difficult at all. They are all very cheap, they are not difficult at all. Hope you guys are following me. Alright, hope you guys are following. Alright, so that is for that. We worked on this. So let's move further to name other compounds. Alright, other compounds, guys. Other compounds I want to name right now. They're not hard. They're not hard at all. They're not hard. Just listen and you are good to go. Alright, just listen and you are good to go. Just pay attention, that's all you have to do. Alright, let's work on them. Let's work on them. Let's have the ways. Let's trash them. Let's trash them, guys. Let us trash them all. You guys are following. Alright, so that is for that. Let us basically unwipe the board. So let me draw another structure on the board. Let's name it together. Alright, let's name these structures together. Let's basically start from the alcohols. Let's start naming from alcohols. 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 Alright, I'm going to form alcohols on the board. So it's going to be C, H, 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 and OH. Alright, let's name this one together, everybody. It's an alcohol. This is the longest continuous carbon chain, right? Yes, nah. Yes. And this is a functional group. Do you understand? So basically what should happen here, number forward and backward. Alright, 1, 2. 1, 2, right? Yes, 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 guys. So we ensure that there's no substance here, there's no chlorine or methyl. So this functional group is OH. So we are aware about this. So we must ensure that our functional group has a low number as possible. So the best count is from this side, right? So the longest name is X, right? X, and it is OH. It has OH. Now remember, OH is not the alcohols. Yes, now okay. Oh, did I tell you something? They are called the alcohols, right? Or we call them the alkanoids. Did I say this? Oh, I can't remember right now. But let us basically just know these are alcohols. You know, alcohols, now this is how they are. They are arrow bond OH. This is how they are. You know, this arrow is a methyl group. Automatically, this is a methyl group. Alright? This thing all together is a methyl group. This C2H5 is methyl. They call it ethyl. It is from ethane. Ethane, that is C2H6. Remove one hydrogen from this, you get C2H5. Alright, so this guy is an ethyl, or ethyl bonding with an OH. Do you understand? Yeah, it is ethyl bonding with OH. But I'm not saying that right now. I'm just trying to tell you that, okay, so I'm just trying to tell you that, oh, this thing is actually an alcohol, alright? No problem about that, alright? Let us name it together. Now, you know, I told us X, and you have X, right? The longest thing is X, and this OH was found at carbon 1, alright? Alright, relax. You can call it 1-ethanol. 1-ethanol, anol. You start with anol, you take the anol. So this is like 1-ethanol, but most times we just call it ethanol, alright? Or ethanol, or ethanol, alright? That number should be in the middle, et, or etan, pick it, even a name that you pick it down to one, all. You understand? So that's the name of this compound, no problem. Let us work on other things. Let us work on other compounds. They are not hard. Another one on these guys. You must always ensure that you respect your functional group. If you don't respect your functional group, there's a problem. So let's do another. So this is bonding. So H, OH. It can be anywhere. It can be anywhere. So don't just say it's only at the first carbon. In this case, it's in the first carbon. It can be anywhere. Alright? I'll show when it's anywhere. You understand? So basically come forward and backward. Don't come forward and backward. 1, 2, 3, 4. 1, 2, 3, 4, right? So doing that, what happens is that this guy is doing 1, yes, like that, carbon 1, and it has 4, 1, butanol, pick it, alright? But if I don't name it, putting the 1 inside, you're going to call butan, 1, all. Do you understand? Let's say, for instance, that H was here, and the OH was inside here. So what becomes the best? You know, this is the functional group You understand? So this is a functional group here. Listen. This is a functional group, right? So not counting forward, backward. When you connect forward is at carbon 3. When you connect backward is at carbon 2. When you connect forward is at carbon 3. When you connect backward is at carbon 2. So go with this one counting as well. Do you understand? So name will not automatically change to 2 canal or put on 2 all. Class, are you there? All these things are not hard now. They are not hard. Class, are you following me? Class, are you following me? Class, are you following me? Let me know in the comments. Alright? So that is for that, eh? They are not difficult. Practice me perfect now. I've done a lot, alright? They are not hard. Alright, let's go over to the alkanals. Let's go back to the alkanals. We will name some alcohol. Even if they are software, always respect your functional group. That's all you have to do. Respect your functional group and you don't have a problem. Respect your functional group first before you respect anything. And I've told us all of these common functional groups to take care of. Alright? So let's work on others. Let us work on others. Now everybody pay attention. I want to work on the alkanals. How does an alkanal look like? So let's say we have carbon. That carbon is CHO now. It's CHO. CHO, CHO. So this guy is an alkanal. Class, do you agree with me that this thing is an alkanal? Yes, now is it not arrow bond C double bond OH? Or we simply say arrow bond CHO? Yes, now. Double OH. Yes, now this is already a substituent on its own. Yes, this one is already an alkyne group now. This is ethyl C2H5. Alright. So what do we do to name this compound? Identify the longest continuous carbon chain. When you know that this compound is an alkanal, and that's 3. Count forward and backward. Alright, 1, 2, 3. Must ensure we respect our functional group and have a lower number as possible. So basically it's 3 and it's prop, right? So prop. So the functional group is carbon 1, so it's 1 propanal. Yes, now, yes, because this is it is an alkanal, guy. It is an alkanal. Anybody that has a C double OH alkanal, or even do that, we simply call it what the propan 1 al. Propan 1 al, that good. You can just basically pick propan 1 al. I thought us these things now, guys. They're not hard. Propan 1 al. Class, are you there? Propan 1 al. Propan 1 al. That's the name. That is the name. Alright? That is the name, guys. They're not hard. They're not hard. You already ensure you respect it. Let it have the lowest number. That's how it works. Let it have the lowest number. Let it have the lowest number, guys. So this one is for your own practice question. So work on this one right now. This is for you guys. Bond. So here is C. Let me see how smart you are. You already know that me drawing a branch, I want you guys to think hard. Alright, to be able to identify if there's any functional, if there's any longest chain, right? So double bond O. Just know that for you to know an alkanal, the function is always found at the beginning. Because in alcohol, you can put it anywhere. But alkanal is always found at the beginning. Are you there? The CHO on hydrogen is always found at the beginning. Alright? So let's complete H, and H, right? So what do we do? And the kind of is on 1, 2, 3, 4. 1, 2, 3, 4, 5. You know now. 1, 2, 3, 4, 5, 6, 7. You understand what to do, right? So automatically this one automatically becomes a branch. You understand? Always ensure that this guy has the lowest number as possible. Always ensure it has the lowest number as possible now. Always ensure it has the lowest number as possible, guys. Always ensure it has the lowest number as possible. Alright? That's all you have to ensure. They're not hard. They're not easy. Can I move further? Yes. This for you guys. This for you. This is for you on the whiteboard. So we can work on the alkanones. How do we name the alkanones? They're all easy. How do we name the alkanones? They're all easy. Very cheap. They're not hard. How do we name the alkanones? How do we name the alkanones? How does this guy look like? Are they not the arrow or C O arrow prime? Yes, now. So they will look like this. Look at how they look. Let's draw an alkyne group like maybe methyl or ethyl. This is ethyl, right? Ethyl. bonding to C, and this is bonding to O, alright, and bonding to R. Let's do another one, maybe C, H3, alright. All these things are alkyne groups. So this one is one arrow, this one is another arrow, alright. This one is ethyl, this one is methyl. Right now, yes, now 1, 2, 6, 5, ethyl. This one is methyl, right? So what do we do? They have the longest continuous carbon chain as well. Number 4 down backward. 1, 2, 3, 4. 1, 2, 3, 4. Ensure your subsequent. Ensure now there is no subsequent. Ensure your compound has a lower number as possible. Yes, and ensure that functional group has a lower number as possible, guys. So what do we do, everybody? So one more candle like this will have carbon 3. One more candle like this will have carbon 2. So this guy will be called 2 propanone. No, not 4. 2 butanone. 2 butanone. Or we simply call it what now? Butan. Stop here. Butan. 2 old. You understand? It's not hard. For you to know an alkanone, the functional group is inside. But alkynes is always outside. There's no way you can bring the functional group of an alkanal inside. It's always outside as seen. Alright, this one is called butanone or butanone. Hope is clear, right? Hope is clear. Hope is clear. Is it clear? Is it clear? Let me know. Is it clear? Let me know. There's no compound you cannot name, guys. There are a lot of them here. They're all cheap. They're all cheap. They're all very cheap. Alright, they're all cheap. Let's work on them. So that is for that. So let me give you your own practice on alkanones, guys. Relax. Relax, quickly, right? So we can move forward, alright? So this is your own number. Remember, this is not common chain, forward, backward, no what to do, right? So that is for that. So on the white board so I can move further. On the white board so I can move further, guys. On the white board so I can move further to other families. Naming, they are all easy. On the white board so I can move further. Let me know. Quickly screenshot on the white. This one is a practice question. So let's get into other families like the alkanoic acids and the rest. Alright, based on how I wrote it on the board. So let's move further, everybody. So alkanoic acid, how does this guys look like? Noic acids. They're always like this arrow bond COOH, which structurally represent an arrow bond C double bond O bond OH. This is how they are. Do you understand? So now they can give you a question that says bond H, like this H, another one, H, bond C. So this is your arrow. All these are your arrow, guys. Yes, now bonding to this carbon, bonding to this oxygen, bonding to this hydrogen. Or oxygen and hydrogen. I told you that. You know, when it's bonding to just hydrogen, that's an alkanal. When it's bonding to oxygen and hydrogen, is an alkanoic acid. Hope you are aware. Alright, so without wasting time, what does this tell us? This guy is an alkanoic acid. How many carbons does it have? That's 3. So they call it propan. And it's a carbon 1. Alright? No, I told us now always ensure with number to the direction of the functional group. And the functional group should have a low number as possible. So it should be 1 propanoic acid. Are you there? Yes. Now 1 propanoic acid or propanoic acid. Or you can call it propan 1 oic acid. Right? That's how it works. It's not hard. That is how it works. It is not hard. So without wasting time, let me give you guys this question. This is what we just solved now. Look at number 10. Number 10 says, look at it on the board. Look at number 10. It says the name of the compound below is what? Look at the compound CH3. That's the CH3 now. This is CH3. That's the first part. They condensed it. Alright, CH3, CH2. Actually, CH3, CH2. That's the second one. And C double bond O and OH. So what's the answer to the question? C, propanoic acid. Is it acetic acid? Is it propanol? No, it can't be a propanol. If it's a propanol, that bond OH will not be there. It will bond O, it will bond H. You understand? Is it ethanoic acid? No, if it's ethanoic acid, you have two carbons. Like maybe this one and this one will not be there. Ethanoic, that's two carbon. Et means two. You understand, guys? Alright, is it? Now let me just tell you, ethanoic acid and acetic acid, they are the same thing. The common name for ethanoic acid is acetic acid. So A and D, they are literally the same option. Class, are you there? Class, are you there? Class, are you there? Class, are you there? Let me know. Hope you are following me. Alright, so that you can see all of them, they are all G. So let us move further. Let us move further. Can I write? Can I write? All right. Let us move further. All right. Let us talk about something very, very important here. I want to basically teach you guys how to name esters. Esters, very important. Esters. Let's talk about how to name esters. Esters. Okay, esters. So here is the first example. Remember, this is how esters are. Arrow, born C-O-O, arrow prime. Are you there? This is an ester. Or alkyne, or alkyne, alkanoids. Look at this, how we name them. Alkyne, you name this one first. You name the last arrow first before you now name this part. Are you there? Name this one first before you now name this part. That's how it works. So let me give you an example. This is C. Let's write this first alkyne, H, and H. Bond into C. Let's say double bond O. Guys, listen, double bond O and bond O. Yes, now bond O, bond. You know, literally it was bond O arrow, and this arrow is another alkyne, so it will be a bond. Another alkyne. Let's basically call this one. Let's call this one another CH3. So basically, it's going to be like this: H, and H, right? And what did I tell us? You name this side before you now name this food, guys. Are you there? What's this one called? CH3. What's it called? Is it on metal? All right. And what's it called? X, right? X, anoids, metal, X anoids. Class, are you there? The name of this company is called. Name this one first. Name this one first. Metal, X. Why is it ethanoid? That's two carbon, guys. Nah, that's why it's called an ethanoid. Class, hope is making sense to you. It's not hard. All right. This one, you name this first, last part first. Before you name it, name it to metal, ethanoid, metal, ethanoid, metal, ethanoid, guys. Metal ethanoid. Hope is making sense. Alright. Metal ethanoid. I repeat what I just said. Let me go. Guys, don't be scared. You know, look at the arrows. You name this first one, first name first, and then you now name this other part. Alright, this is the alkanoid part. So this is the alkyne, the first alkyne, alkanoids. So name the last part first. So let's work on other examples. Let's say we have C like this, H, and another C, H, and then you have C. You now have a double bond up, which is showing this C double bond, and then O, and then another C. 2H5. Are you aware that I can literally do it like this? You know that this is already called ethyl. They can show it to me, they can draw it in a structural form. So this is ethyl, and this is what? How many now? 1, 2, 3, 4. How many carbons? Both. 4 is both an anoate. You understand? So it's called ethyl butanoate. Ethyl butanoate. Class, are you there? That's the name of the compound. Ethyl butanoate. Ethyl butan. That's the name of that compound. Ethyl butanoate. Alright, ethyl butanoate. Ethyl butanoate. Class, are you there? Class, are you there? Ethyl butanoate. Let's go. Is that anything that looks like that?
ethyl butanoate, C2H5. So let us formulate the chemical formula of this guy I just named, which is ethyl butanoate. Now, how many carbons can we see? See what? Count all your carbons. Count all your carbons. 1, 2, 3, 4, 5, 6. So C6. Are you there? Count all your hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Am I correct? Let's start. 5, 6, 7, 8, 9, 10, 11, 12. So 6 is H12. How many oxygen do you have? 1, 2, O2, right? 6 is H12, O2, right? So you can see it's actually correspond. This is ethyl butanoate, right? We are good to go. It's not hard. 6 is H12, 6 is H12O2. You can say it worse. You name the last parts in the structure. You know your exam, you can literally just condense all of them together, guys. In your exam, you can condense them, eh? You should not be scared. You can condense them. Not only this, like a lot of things, they can condense them, eh? They can condense them. Now, like, they can say, okay, C2H5 bond C double bond O. Okay, C3H7, alright? This is propyl, right? This one is propyl itself, and then bond CH3. They can be like the same name in your exam. So it's left for you to now straighten, alright? This one is not, but it's simple. Name this one methyl, alright? Don't name this one low, show you how this carbon. No, I know you want to say, what them alkanoic. So this one is methyl propanoic. No, it's butanoate. We have another extra carbon, so it's butanoate. So it's methyl butanoate, you understand? Methyl butanoate. Do you understand what I'm saying? They're all easy. So this is how you name esters. This is how you name esters, guys. So that is for that. That is for that. All these things are very, very important. They're not hard at all. These are your name esters. Try to think of something now. Okay, C3H7. Go and correct with this. C2H6. C2H6 and CH2. That's C3H8. Removing one. Okay, we're good. So this is butanoate now. Alright. We are good to go, guys. So let us work on esters. No, the next is ether. Alright. Alright, let us work on them. For ethers, these guys are esters. For ethers, hope you're aware that they have, they behave like, for ethers, they are like this. Ethers are literally like this. They have arrow bond OR. So they have two arrow group, right? Arrow bond OR. So basically, you name this one first, you name this one, and that's why it's ether. Alright? So for instance, now you have something like this C2H5 bond O on this other arrow, let's say CH3. All of them are all alkyne. So you call it methyl, you call this one first. Methyl, ethyl, ether. Methyl, ethyl, ether. Methyl, ethyl, ether. Alright, methyl, ethyl, ether. Alright, methyl, ethyl, ether. Methyl, ethyl, ether. Methyl, ethyl, ether. I'm coming. Guys, hope you are paying attention to what we are saying, eh? I'm coming. Let us move further. coming, guys. Relax, relax. So we can move further. There's something I want to tell us right now. Okay, wait. Hold on. So let's say, for instance, here, just relax. Let's work on it so that you don't get confused on this aspect. Here is CH3, and here is a C2H5. All right. Here is CH3, and here is C2H5, for instance. Alright, there are like easy ways to name this compound, which is basically, they are like this set of compounds, they have their trivial name. All compounds have trivial names and IUPAC name. Like, we are an IUPAC nomenclature, so but first of all, let me just teach you guys how to get the trivial name. Let me give you guys how to get the trivial name first, alright? So to get a trivial name, you simply just observe. This one is, look how it works, this one is ethyl, right? And this one is what? Methyl. Don't use first or second here, alright? Just listen. This one is ethyl, this one is methyl. So you name for trivial name before we get into the other IUPAC name. The trivial name is basically what's based on you understanding that N comes for, no, E comes for N. Do you understand? E. A, B, C, D, A, B, C, D, A, B, C, D, E, A, B, C, D, E. Do you understand? So E comes before this, right? So it's going to be ethyl, methyl, ethyl. Ethyl, methyl, ethyl. Do you understand how that's how it works? Ethyl, methyl, ethyl. This one come. No, we're not basically naming this one first. If this one was still here, we'll still call it ethyl, methyl, ethyl. That's like the trivial name. Alright, but the IUPAC name, you basically look at it works. The IUPAC name. Now that's why ethers is also called alkoxyl alkane. Alright, alkoxyl alkane. Alright, now observe them. If I want to give this guy its IUPAC name, the real name it should be. This alkane is to be named, you identify the longest chain. Observe your subsequent. Observe the two arrow. The one that is longest takes the parent's name. Now this one is not X, it's not two carbons, this is one. So you change the parent name. So the name of this compound should end with ethane. Are you there? And this one now becomes methoxyl, alkoxyl, methoxyl. Are you there? So this one becomes what now? Methoxyl. Look at now, alkoxyl, right? ALK and oxyl, right? So that's how it works. Methoxyl ethane, that's the name of the compound. IUPAC. That's how it works, guys. That's the name of the compound. IUPAC. Alright, that is the name of the compound. IUPAC. You basically look at the one that is longest. C2H5 is bigger than that one, so that one automatically forms the parent name. Alright. I'm going to basically work on more examples so that we can get to understand this ethers properly. Alright, so we get to understand this ethers properly. Alright, actually there's no L, so let's remove the L. It's like this. Alkoxyl alkane, right? So we are going to work on more examples so as to master it properly. Alright. So just relax, unwipe the board so I can work on them right now. Everybody pay attention, So let me bring more examples. Look at this one. This is CH3 born C3H7. Alright, so what do we do? The trivial name is basically named alphabetically, right? The trivial name is named alphabetically. This is propyl, this is methyl, right? And this is propyl. For the trivial name, propyl, right? So the name M comes for P, right? A, B, C, D, E, F, you understand, down to M. M comes for P, right? So we'll start with methyl propyl ethyl. Alright, the name will not be, This is the ether. So it's going to be methyl propyl ether. It's an ether, but for the real name, ether is also called alkoxyl alkane, right? So then this alkane is the one that is the longest. This one is bigger, so this one automatically now turn to the parent name called propane. Alright, this alkane form. And what's alkoxyl? Methoxyl. Methoxyl propane. You understand what I'm saying? Methoxyl propane, that's the name. You understand? It's very easy. It's not hard. Practice makes perfect, guys. The name of the compound become what? Methoxyl propane. Right? Methoxyl propane. So that is for that. Let's say for instance, we have identical groups. Alright, look at how the name becomes. So let's say we have identical like this. Identical. So here it's now C387. Now it's propyl, right? So you cannot keep alphabetically. So it's going to be dipropyl ether. Right? Dipropyl ether. So what becomes the name? One of them, they have the same number. So one of them turns to the parent name propane, and the other one is called pro-oxy. Yes, propoxy propane. All right, propoxy propane. Propoxy propane. Propoxy propane. You understand? So since they're the same, you can see how easy these things are. They are not hard at all. So right now on naming, I think I've done justice to naming. The other guys, which are your amine, they're not hard. They're not hard at all. No problem. Let us move further. Let's get to something very vital in this aspect. We are done with IUPAC nomenclature. We did a lot of things on IUPAC nomenclature. So let's move further. Let us move further to very vital aspects in organics. We're still having more concepts to treat. Let us work on them right now. So pay attention in this aspect of chemistry, organic chemistry. So right now, let's get into isomerism, which is a part of stereochemistry. What is isomerism? When you hear about isomerism, what is this isomerism? You've been hearing isomerism. What is isomerism in chemistry? Let us break it down without, any form of stress. So just pay attention. That's all I have. I'm going to just define it properly so that we get to understand how it works. All right. Now, isomerism basically, we have various types of isomerism. We have what we call the structural isomerism and the stereoisomerism. All right, structural isomerism and stereo. For structural, we're going to talk about them. For stereo, we're going to talk about them. Just relax. So what is isomerism? I'm coming. So let's start with isomerism. Isomerism, what is this? People are really listen. Isomerism, let me just explain something. Isomerism, I told us that could be of two types. We have structural or stereo. Structural, or what do you call it now? I'm not going to say it now. Structural or the stereoisomerism. Alright? On stereo, we have other subtype. So my definition now is just based on the structural isomerism, which we also, for basic level chemistry, we call it a definition for isomerism. Are you there? So isomerism basically is a concept in chemistry where two or more compounds have same molecular formula but different arrangement of the atoms, which lead to different properties. Don't worry, all these are just big English. Let us break it down together. All right. Now, isomerism is like a phenomenon in chemistry where there are different structures, different compounds, where there are compounds have different compounds. They have same molecular formula, meaning same chemical formula, but different structures. This is me defining structural isomerism, which you also call, isomerism in general. But we're going to dwell on them as we move further, so you get to understand what is really happening. So, on isomerism, we have two types without wasting time. We have the structural isomerism, and the stereoisomerism. Alright, structural and stereoisomerism. So I just defined like the structural isomerism without wasting time. Structural isomerism and also the stereoisomerism. Alright, just pay attention. So I'm on structural right now, where I'm basically explaining to you that in structural isomerism, pay attention, there is a phenomenon whereby compounds, two or more compounds, they have same molecular formula but different structures. Guys, it's not a big English. They have same molecular formula, they have same chemical formula, but they have different structures. This is what we call structural isomerism. Relax. I'm going to explain. Alright, relax. Now on this guys, just listen and listen well. On this, we have different subtypes of structural isomerism. We have different subtypes on structural isomerism. Alright, we're going to work on them. When we are going to work on them right now, we have different subtypes of structural, like number one now. So in structural isomerism, look at the word structural, is a phenomenon whereby two or more compounds have the same chemical formula but different structures. Now, without wasting time, we're going to get to stereo, but before then, let us basically continue on structural. The first one to learn, we call it chain isomerism. On structural, we call chain isomerism. Alright, this one now, they are isomerism. What is chain isomerism? It's very easy. Just pay attention. On chain isomerism, it is a phenomenon whereby compounds have the same chemical formula but different arrangement of their carbon chain. Just relax and listen to what I'm saying. But different arrangement of their carbon chain. Just pay attention. Remember, I told us now a chain could be branched or a chain should be could be straight. Now I'm going to use hexane as a case study here, or maybe butane. Let's use butane, which is the simplest. Everybody pay attention. I can only work on butane. 1, 2, 3, 4. Guys, pay attention. They are not hard. This is H, 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 this is H. Class, you have to me that this is butane because I taught us naming, so there's no way you won't know that this is butane, right? It is butane now. They have 4 carbon, 1, 2, 3, 4, single bond all through. Now, listen, what is butane? Is it not C4H10? In structural isomerism number one chain, it is a phenomenon whereby two different structures, they have the same chemical formula but different structures. Two different compounds, they have the same chemical formula but different structures. I will show it to you. I want to use butane as something else. So now, as a student, you not think, how can I draw another form of this that basically we have different structure but the same chemical formula? You not start thinking. I didn't know what to do, because I'm experienced. I've been doing this thing for years. So for you now, don't worry, you get to follow soonest. Right? So these are your carbon, and then after the carbon in a straight chain, I can literally put one down to form a branch. Automatically, you know what should happen here. Don't worry, it's not hard. It's not hard at all. Just relax. All right, relax. They're not hard. Relax. Now, I can literally, pay attention everybody. Are you not see what I've done? Relax. Now, my point here is this. Are you not see what I've drawn? What I've drawn now is a different compound on its own. This compound now, see, this chain isomerism, it is a phenomenon where compounds have different structures. First of all, let's count the chemical formula. The 1, 2, 3, 4 carbon as well. How many hydrogen? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow. So this compound, they are different structures, but they have the same chemical formula, but different structure. The structure is based on the chain arrangement. One had a straight chain, another had a branch chain. So it's based on that chain. That's why I call chain isomerism. It's based on their chain. That is why it's called everybody chain isomerism. Is it not based on the chain? It's not on the chain now. That's why it's called chain isomerism. I told us chain now. I started all these things. So this chain isomerism, alright, which is one type of structural. So in this type of isomerism, we are focusing on the structures of the compound. they will have the same chemical formula, we have seen them, but their structures will be different, and this is a good example. Alright, I will explain something to you that is very vital for your exam sake. Alright, like, let me tell you something. They can ask you a question. Now, first of all, digest what I've said. Digest what I've said so I can move further. So I will not, be making it too much. Digest all what I've said so I can move further. Digest all what I've said so I can move further, everybody. Digest all what I've said so I can move further. Alright, digest all what I've said so I can move further, everybody. Digest it so I can move further. They're not hard. Digest all what I've said so I can move further. Digest it. Just know that chain isomerism, which is one type of structural isomerism, is a isomerism that results in compounds having different structures but the same chemical formula. Alright, the difference is in their structure. This is butane, this is another thing. Oh, let's name it together, everybody. This one now, you number forward and backward, right? Yes, now I can literally use this one to be another substance I'm not changing. Well, this become a branch of below. 1, 2, and 3. 1, 2, and 3. So I go forward, backward, 2. So this is 2 methyl, and the longest chain is propane. So you can see that 2 methyl propane and butane are words. So they can ask you a question in your exam. Listen, they can ask you a question in exam. 2 methyl propane and butane are dash. Is this structural? Are they structural isomer? But now they are called isomer because they have the same chemical formula but different structure. They are called isomer, specifically chain isomer. They cannot ask you, okay, in your exam, butane and 2 methyl propane, are they structural isomer? What do you do in your exam? How to answer these questions? Are they structural isomer? Are they positional isomer? Are they functional group isomer? Which I'm going to teach us about position isomerism, functional group isomerism, like that. I'm going to teach us all these things. Are you there? But they are chain isomer because they define their chain, the way their chains are arranged. So the answer is just want to pick that one that is chain isomer. But even if it's not this example, you can still get it, guys. Just think, draw their structures. From when they give a compound butane, you can draw it. 2 methyl propane, you can draw it based on it. 2 methyl propane and prop is 3 carbon, and put 2 methyl in where it should be. Guys, it's not hard. It's not hard. Are you not following me? You're following this chain isomerism, which is one type of structural isomerism. There's something I want to tell us right now. Alright? Let me just tell us something right now. Let me tell us something right now. I want to tell us something right now. Just pay attention. So now, isomerism, chain isomerism or chain isomers start for the alkane family. Everybody listen. For the alkane family, the chain isomers start from butane. Hey, listen. For the alkane family, your chain isomers start from butane. Now, this is butane. How many forms of itself can it produce? It can produce 2 forms of itself and another. So they can ask you now, what is the number of chain isomer? What is the number of chain isomer in butane? What will you tell the person? 2. Now, you don't see it now, guys. See now, class, it's not hard. I can use a formula to tell you, or I can literally use a formula to tell you, guys. I can literally use a formula to tell you. They're not hard, alright? They're not hard. Guys, they're not hard. It's 2 now. I drew itself and something else that looks like it, but they have the same different structure but the same chemical formula. Alright? So if they ask what are they, we have the normal butane and 2 methyl propane. Alright? These are the numbers of chain isomer. Butane is what starts it. If I want to draw propane itself, there's no way I can draw another form of propane. Yes, now this is propane, everybody. Is this not propane? Can I literally draw propane? What's the chemical formula of propane? Everybody watch. What's the chemical formula of propane now? What is the chemical formula of propane? Tell me. Is it not C3H? Tell me quickly. C3H word. C3 10. No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So C3H8, this is propane. 1, 2, 3, 4, 5, 6, 7, 8. So this is propane. There's no way I can draw propane that will get something else. Okay, now let's say for instance this is another propane. This is another form of this. I want to draw something like this. It's not possible. Okay, I want to bend this one. I want to not bend it down. I want to take it down. I want to bend it. Let me see if we can do something. I want to bend it. I bend this one down. Alright, and this one down. Let's work out together. Alright. Maybe you want to name the longest continuous carbon chain. Okay, let's name this one. It's not even correct. No, guys, it's not. It will not work. It will not work. If I wanted to try another form of propane, it will not work. But now, okay, if I now can add another hydrogen now, listen, if I add another hydrogen, it will cause a problem. Okay, I've added another hydrogen. So automatically 1, 2, 3, 4. Okay, wait. So what am I even drawing? It will not work. Like the point I'm trying to make right now is that the number of isomers starts from butane for the alkane family. Let's name this guy together. Alright, so at carbon, see, 1, 2, 1, 2. So I just 1 ethyl ethane. There's not like that. 1 ethyl ethane. There's nothing like that. 1 methyl ethane. 1 methyl ethane. Not like that. Yes, note it. The first number of alkane that's have a chain isomer, it's chain though, it's not just called isomer, a chain isomer is butane, it's 2. It's 2, guys, it's 2. Alright, butane has 2 chain isomers. I will literally just give you their numbers. No, you can see in chain isomerism, they have in this isomerism, they have the same chemical formula but different structural arrangements. Alright, that's for chain. We are on structural now, so their structure will be different. So in this one now, they are different in way their chains are arranged, the way the structures of their chains are arranged. So I said butane is what? Butane has how many? It has 4. So it has 2 chain isomer. Alright, butane in general, it has 2 chain isomer, which we have worked on already. Butane has 2 chain isomer. There's a formula I can basically use to work on it. After that, the next one is this. Pay attention, guys. Pay attention. Butane. Methane does not have. Methane doesn't have everybody. It's butane that starts it. All right. Whereby for pentane has a 2. Pentane has 3. All right. Pentane has 3. All right. Work on that. Pentane you're seeing here, it has 3 chain isomer. Alright, pentane has 3 chain isomer. Pentane has what? 3 chain isomer. So butane has 2. I can draw pentane in 3 ways. That's what this tells us. This pentane. I can set to draw pentane in 3 ways. After 4 is right now. So the next is hexane. So how many chain isomer can be drawn from hexane? You draw the first straight chain, you now start drawing other chains. All that matters is that they will have the same structure. All that matters is that they will have the same chemical formula for different structures. You understand what I'm saying? The next is hexane. And hexane has 5. Alright, hexane has 5. Whereby I can draw hexane in 5 ways. Whereby heptane has 9. Alright, the number of chain isomer is for heptane is 9. Heptane is 9. I can draw heptane in 9 ways. That's what they're telling me now. All these are the numbers of chain isomers. All the numbers of chain isomers. I can literally show you how they are gotten by drawing them or giving you a formula to know, but I want you to memorize this point. Alright? I want you to memorize this point, guys. Alright? Whether octane down till nonane, octane is 18. Yeah, octane has 18 chain isomer. I can draw octane that very big in 18 ways. That's what it's telling me. I can draw octane in 18 different ways. They will have different structures. All the structures I'll draw will be different, but the same chemical formula. Whether nonane is 35 and alkene is 75. Alright, octane is 18, nonane is 35, and the alkene is 75. Octane, 18 chain isomer, nonane is 35, and the alkene is what? 75. I can literally show you how we got them using the formula, guys. I can literally show you how we're going to get them using the formula. Alright, I can literally show you how we get them using the formula. And the formula is 2 raised to the power of n minus 4 plus 1. Look at it. 2 raised to the power of n. You see minus 4 plus 1. This is the formula. 2 raised to the power of n minus 4 plus 1. Alright, so for butane, I said the number of chain isomers start from butane. If you even check for your methane now, you see no lead methane doesn't have, do the math. Where n is your number of carbon? N is always your number of carbon. In butane, how many carbon do we have? We have 4 carbon now. Leave all these ones. These are the answers, right? Let us get the answers. Butane, we have 4 carbons. Everybody knows that. So it's going to be series power of 4 minus 4 plus 9. So 4 minus 4 is what? 4 minus 4 for that first one. 4 minus 4 is what, everybody? 4 minus 4 is 0, right? So it's going to be what? A series of 0 plus 1. And any series of 0 is 1, right? So 1 plus 1, that is a 2. And this is for butane. You understand? That's how it works. So that is how it works. So butane has 2. You can see the 2. What are they? Butane itself and 2 methylpropane. You understand? Guys, hope you understand what I'm saying. Alright? Hope you understand what I'm saying, guys. Hope you are following, eh? They're not hard. They're not hard at all. They're not hard at all. They're not hard at all. So you can literally check. Do it for me. Check if all the numbers are in line. So this one is 3 now. Is C n raised to power minus 4 plus 1. So here is C raised to power now. Paint is 5. 5 minus 4 plus 1. So C raised to power 1 plus 1. Right? Is it 1 plus 1? 5 minus 4. Is it 5 minus 4 for the other guy? Let's check it out together. Eh? Check it out for me. Let's see. For pentane. Are we on track? Oh, guys, sorry. It's not C, it's 2. What am I saying? Sorry, guys, it's 2 of N. This is me so stressed out right now. Alright, so this one, and 2 of 1 is 2. Alright, so 2 plus 1, that's why it's 3. Sorry, guys, 2, not the C. 2. So you can see that's why this guy is 3. Check for hexane, you see it's 5. Check for heptane. Why for these guys, from octane down, this formula will not work. Alright, all these are just strict formulas to get them. From octane down, the formula will not work, which is 2 raised to n minus 4 plus 1. They have their own special formula. Alright, they have their own special formula. Alright, these are just, tricks. Alright, they have their own special formula. I'm talking about alkane, so numbers of chain isomer. Alright, they have their own special formula. Like for the octane now, it's 2 raised to n minus 4 plus 2. For the octane, the way to get it together 18, use the formula 2 raised to n minus 4 plus 2. For the other nonane, to get their own, it is 2 raised to n minus 4 plus 3. Alright, whereby for decane, to get it, decane is what? 2 raised to n minus 4 plus 1. Do everything, you're going to be good. Alright, just try it out and you're going to get those numbers. Try it out, you're going to get those numbers I just said. Try it out, you're going to get those numbers I just said. Alright, so that is for that. That is for that, guys. That is for that. We're on track. Plus 1 plus 10. No, plus 1 plus 10. Plus 1 plus 10. Those are the 3. Plus 1 plus 10 for the last one. Plus 1 plus 10, guys. All these are just strict. But what the matter is just try to memorize it, because this is how it comes to your exam. They'll tell you how many chain isomers are seen in butane. Just go to your option and see 2 and you're good to go. There's only butane I could draw. I cannot start drawing butane. They are not hard. Or, we have other things to learn. So that is for that on chain isomerism. So in chain isomerism in general, these compounds, they have the same chemical formula, alright? But they now have different their structural, in their chain arrangement, how their chains are arranged. That's chain isomerism, alright? So that is for that. So let's talk about number 2 type of structural isomerism we have to learn now. Number 2 type of structural isomerism we have to learn. And this one is called positional isomerism. They call it positional isomerism. Positional, very easy. This one, look at the word. From the term, you'll be able to know what they talk about. In isomerism in general, you are having same chemical formula but different structure. So now the difference here, the difference these compounds have is in their position, is in the position of their functional group. So in positional isomerism, it is basically what happens is a phenomenon that occurs between compounds with the same chemical formula but different structures, specifically in the position of their functional group. They have different structures, specifically in the position of their functional group. Everybody pay attention. Now this is what I mean by what I'm saying right now. So this is an alcohol. So the OH is here, alright? Pay attention. This is H, and this is H, and this is H, and this is H. I'm explaining positional isomerism. Alright? Positional isomerism. Positional isomerism. So positional isomerism, the compounds are different in the position of the functional group. Alright, so let's note this. Let me try another one. Exactly, this is, our soul aims to get the same chemical formula, but this time around, the functional group is here. And here is H, 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 right? So what do we do next? Let's name this one. This is 2-propanol, right? Because the functional groups are carbon. So 1, 2, 3. 1, 2, 3. Counting forward backward is 2-propanol, right? So now what about this? This one is 1-propanol. Alright, this is 1, where's that carbon? 1, 2, 3. 1, 2, 3. So let's go with this one. 1-propanol. Alright, 1-propanol. So if you observe, let's look at their chemical formulas together. So this one is C, 1, 2, 3. C3, H word. Let's count. 1, 2, 3. Okay, let's just count 1, 2, 3, 4, 5, 6, 7. Right? C3 is an OH. Same applies to the other one. C3, 1, 2, 3, 4, 5, 6, 7. H7, OH. But the difference in these guys is in the position of their functional group. So in positional isomerism, it occurs when compounds have the same chemical formula but different position of their functional group. So you think of things that are alkenes, alkynes, they can undergo positional. Yes, now, some of them can be 2-propyne, 2 this one, 2 that, 2 propyne, 1 propyne, something like that. I don't know if you understand what I'm saying. So it's just going to observe, look at the structure well, and look at the one that can actually, that's why you must learn, when they give you a name of a compound, learn to draw the structure. You can do it, it's not hard, you practice all of these things. So this is positional isomerism. It is a phenomenon whereby compounds, they have the same chemical formula, or the same molecular formula, they are the same, but difference in the position. This one is positioned at carbon 1, alright? This one is positioned at carbon 2, alright? So difference in that position leads to what we call positional isomerism, alright? So that is for that. So let's get into other types of isomerism to talk about, specifically on structural isomerism. The next is what we call the functional group isomerism. As I'm giving you now, so note this in summary, alcohols undergo positional isomerism. So just note that alcohols undergoes positional isomerism. While for those first one, which is chain, all from butane down to decene, they undergo positional isomerism. They undergo chain isomerism rather, not positional. Chain isomerism. But for alcohols, the alkanoids, they undergo positional isomerism. I will just give you some common examples. Alright, so that is for that. Let's get into another type of structural isomerism called functional group isomerism. Called the functional group isomerism. Now, here, look at it. By definition, what is functional? You can define it, guys. You can define it. All you should have in your mind is that, okay, these compounds, they will have the same chemical formula, but different structure based on their difference in functional group. So when I'm mentioning, there will be a difference in that thing. Like I mentioned, positional. So they have the same structure, they have the same chemical formula, but difference in the position. So functional group isomerism now, yeah, they have the same chemical formula, but difference in their functional group. Alright, and they have the same chemical formula. A good example of compounds that undergoes this are alcohols and the alkoxyalkane. Alcohols and the alkoxyalkane. Let me show you what I mean by this. Alcohols, note this. Alcohol on position, I do the others. Alcohols and the alkoxyalkane. Let me give you an example. Let me draw one of them. I want to draw ethanol. Ethanol. I want to draw ethanol. Ethanol means we have 2 carbon, right? And here is OH, here is H, here is H, here is H, here is H, and here is H. This is C2. 1, 2, 3, 4, 5, 6. I can try to, I want to basically add all the hydrogens together. I can see that OH, but I want to add all the hydrogens together in this case, and O, just one oxygen. So now I want to draw an alkoxyalkane. Thank God we already know how alkoxyalkanes look like. They are the arrow bond, O arrow, they are the ethers, right? So now the one I want to draw right now is this one, they call dimethyl ether. Dimethyl ether. You know, alkoxyalkanes, they look like this arrow bond, O arrow, right? So dimethyl means that we have 2 of the methyl, CH3 bond O and CH3, right? This is dimethyl ether. You know, now they have 2 now. Normally, if I don't name them, we will name them alphabetically, but they have the same. This is dimethyl. This is ethanol, right? Now, what is this is what C2, 1, 2, H word, C 6, and O. And you don't see that they have the same chemical formula or different structures. I don't see their structure, this one structure like this. So our story here is like different structures and different functional group. They have the same chemical formula, but different in their structure and different in their functional group. You understand? For functional group isomerism. Do you understand? Guys, the so heavy here is to understand that functional group isomerism, there will be difference in that dimension. There will be difference in that subheading, which is the functional group. So there is a different functional group. This is on the alkoxy alkane functional group. This is the alcohol functional group, right? So now that is for that. This guy is called dimethyl ether, right? It's dimethyl what ether. So how do you name it? Or the IUPAC name? You call they are the same, so you can literally call any of them first. So it's going to be methane will end it, right? So it's going to be methoxyl, right? Methoxyl, methane. You know, methoxyl methane. Is there anything like methoxyl methane? Yeah, there is. Methoxyl methane. Alright, guys, hope you are following me. We've done all of these things now, so it's not something I should not be slowing down to name the compounds, right? Practice makes perfect. Practice makes what perfect? Methoxyl methane. Hope you know it's an ether. Hope you know methoxyl methane is an ether. Are you there? Are you aware that methoxyl ethane is an ether? Yeah, good. Because ethers are also called alkoxyl alkane. So you can see examples of these guys that undergo functional group isomerism. You can see examples of these guys that undergo functional group isomerism. Guys, hope you are following me. Hope the network is still okay. Let me know in the comments if the network is okay. Let me know in the comment section if the network is still okay, so we can move forward to talk about all the types. Alright, there are others like metamerism, tautomerism, alright? All those ones are all our broader aspects. So without wasting time, we'll go over to stereoisomerism. These are the ones I know the exam normally asks. Alright? Now, I want you guys to note this. Functional group isomerism is also seen in alkanones and alkanals. Alright? Please note what I just said. Functional group isomerism, because this one is functional group isomerism, right? The subheading is functional group isomerism. Functional group isomerism. I'm just giving you the example. So when you on your leisure can go and try to form them so that they will have the same chemical formula but different structure. I'm giving them the guys that are going, so you must start it. Functional group isomerism. Who are these guys? They include these guys, this set of compounds, alkanals and alkanones. They are functional group isomers. Alright. Even these guys, we talked about alcohols and alkoxy alkane. They are functional group isomer. Also, what do you call it now? Alkanoic acids and esters. Alkanoic acids and esters. They are also functional group isomer. Please, I want you guys to go and try your best possible to think of compounds that will have the same structure but different different functional group. You can do it. You can do it, guys. You can do it. I believe in you that you can do it, alright? You basically just think. Which one will have different structure but different structure but the same chemical formula? Go and think. I've taught us name it so you can be able to walk through all of them. They're not hard at all. So let us get into stereoisomerism. That one that has to do with geometric and optical. Alright? Geometric and optical. So let's stress on stereoisomerism right now, which has to do with geometric and optical isomerism. Alright, just pay attention. In stereoisomerism is different from structural. For structural, it has to do with compounds having the same chemical formula or molecular formula, but difference in their structure. We saw different times like the chain, like the positional and the functional group. Though there are others like tautomerism, metamerism, but those ones are they're not advanced though, but they are like topics to be treated individually. Alright, so in summary, for structural isomerism, it has to do with like the compounds having the same chemical formula but difference in their structure based on maybe their chain arrangement or their position or the functional group they have. And I've given us examples of compounds that undergo this functional group isomerism. You understand what we are talking about? like likes of alcohols and alkoxy-alkane. I showed you guys example, like likes of alkanes and alkanones, like likes of alkanoic acids and esters. We are good. Now let us get into stereoisomerism. In stereoisomerism, it's basically a phenomenon that occurs when a compound have same chemical formula and same connectivity of atom, but they differ in their 3D arrangement of atom in space. All right, they differ in the 3D arrangement of atom in space. I will show you what I mean by this. All right, just pay attention. Just pay attention, guys. Pay attention. Let me wipe the board so I can have space to work on stereoisomerism right now. So let us work on stereoisomerism. So let us work on what? Stereoisomerism. Guys, pay attention. Pay attention. Pay attention. This is a very, very essential. Stereoisomerism. Stereoisomerism. What is this stereoisomerism? I said that it is a phenomenon whereby compounds, they have the same chemical formula, they have the same element connectivity, but there is a difference in their 3D arrangement in space. I will show you what I mean by what I just said. Just relax. All right, they have the same chemical formula, they have the same connectivity of the atoms, but they differ. So there's always a difference. All right, so they differ in their 3D arrangement in space. Now, what are the types of stereoisomerism? We have the geometric isomerism and the optical isomerism. All right, the geometric isomerism and the optical isomerism. Just pay attention so that I can explain to you what I mean by all these I just said. Just pay attention so I can explain to you what I mean by what I just said. So we have geometric. In geometric isomerism, what happens? This geometric isomerism is also called something. If we don't call it geometric isomerism, we can call it the cis and trans isomerism. Guys, pay attention. Let me show you what I mean by all this I'm saying. Let me refill the marker so we can work on this geometric isomerism properly. In geometric isomerism, compounds have, stereoisomerism, where geometric isomerism is found, is a phenomenon whereby these compounds, they have the same chemical formula, but the only difference here is the way the atoms are arranged in space. And you see the space I'm talking about, the way the atoms are arranged in what space, the way the atoms are arranged in what space. Just listen, let me show you what I mean by what I just said. And I'm giving out geometric. In geometric isomerism, this isomerism is due to restriction, is due to restricted rotation around a double bond or a ring. Just listen. All these things are not hard. Alright? Just note this. I want you guys to note this. Geometric isomerism results due to restriction in rotation around a double bond or a ring. Alright? So on this now, we have good examples of geometric isomerism compounds. In actual, they also call the cis and trans. The cis and trans isomerism. This is what I mean. I'll be using compounds that undergo this, they are the alkene. Alkene, they don't undergo this. Compound with there's a double bond in that compound, they undergo geometric isomerism. And let me show you what I mean by what I just said. Alright? I'll be using a very popular alkene. Let me draw the two structures here. So this is a bond, this is a double bond, bonding to CH3 and bonding to another CH3, bonding to H and bonding to H. I want you to tell me the name of these compounds. They're not hard. This is another bonding to, this time is CH3, bonding to H, bonding to CH3 and bonding to H. Alright? I want you to tell me something on the board. What I just drew on the board. Okay, I think I have to basically do something. Just listen and listen well. Okay, I should. Alright. Okay, let me do this way. So here becomes CH3 and here becomes H. Alright? I'm going to do this way. And let me just, let me put here to be identical. CH3 and here is H and here is H. We are good. Alright, so now in geometric isomerism, please note it occurs as a result of restriction in this double bond of the copper to rotate. There's a restricted, this double bond now, there's a restriction. It occurs due to failure for this double bond to rotate, you understand? So that's for geometric isomerism. And what are the examples? They are the cis and trans isomerism. Now, these are the two common examples, though there are others. Alright? Now, what compound is this, first of all? What compound is this, first of all? That'll be a question you ask me. What compound is this, first of all? Alright? What compound is this, first of all? Alright, let us work on this. Now, this compound on the board, by IUPAC nomenclature, it is an alkene. So let's name this is the longest continuous carbon chain, right? Yeah, this is the longest continuous carbon chain, right? So this is carbon 1, this is carbon 2, this is carbon 3, and this is carbon 4. Also, this is the longest continuous carbon chain, right? Yes, now guys, this is carbon 1, this is carbon 2, this is carbon 3, and this is carbon 4. This is carbon 1, this is carbon 2, and this is carbon 3, and this is carbon 4. You understand? This is carbon 1, carbon 2, carbon 3, this is carbon 1, carbon 2, carbon 3, and carbon 4. So basically, our SOA is to basically ensure that our substituents, our functional group have the lowest number as possible. Alright, so counting forward backward, we had 2 and 3. So the name of this compound will now be 2-butene, right? 2-butene. Or if you don't call it that, you can call it what now? Butene, right? What? 2-ene. Now, but because now this compound we are seeing on the board undergoes geometric isomerism, the name will now have something. Alright, the name will now have something. Just pay attention. This one is still the same because between the two, the carbons between the functional group is 2 and 3. So this one is 2-butene, but now the same name. Or what? Butene. Butene. But what is the special name based on this geometric isomerism? I said that it is also called cis and trans isomerism. Cis and trans what? Isomerism. Now, how do you know the one that is the cis and how do you know the one that is the trans? That's the question we ask ourselves. And we're going to do this based on the, what do you call it now? Based on the hydrogen. So when the hydrogen atom you are seeing on the board is on same side, is on same side of the double bond, is on same side of the double bond, we call that one a cis. When it's on same side, it's called what? The cis. So if you observe now, the hydrogen is on the same side of the double bond. This side of the double bond. So this one will not be what now? Cis. 2-butene or cis butene. Do you understand? But when the hydrogen are on opposite side, we use the hydrogen. When the hydrogen is on opposite side, we say this is what? A trans. Alright? Butene. Alright? If it's of different sides, call it a cis butene. If it's of what do you call it now? If it's of the same what do you call it now? The same side, cis. If it's of different side trans. Alright? So that is for that. That is for that. That is for that, guys. So I'm gonna give us more example. So that is for that, guys. I'm coming. Let me give us another one. Let me see how far you guys can name this one. You guys should relax that. Oh, easy. Let me basically look at another one for you guys. So now tell me the one that is cis and trans. So this one has a carbon, double bond. This is chloro, this is chloro, and this is hydrogen, and this is hydrogen. This is another one. This is C double O. This is chloro. This is CH3. No, this is H. Should we yes? That is H. This is H. This is CHCl, and this is H. Right. So let's work on this one on the board right now. All right. Let's work on this one on the board right now. Let us work on this one on the board right now, guys. Let us work on this one on the board right now. I'm trying to get something. Relax. This one on the board. Okay, let's ensure that. Okay, wait. This is H, should be what H. Alright, so I told us already, how do we determine cis and trans? Use your hydrogen most importantly. If your hydrogen are in same side of that your double bond, like the same side of the double bond, then we say it's a cis. If they are of opposite side, it's called the trans. Alright, so in that name the comma, this comma has 2 carbons. So what should be the name? Any comma with 2 carbons, what's it? You know now. You know X now, ethyne, rather 18. Alright, so what becomes the name? Alright, look at it now. Name it. There's no, this long as 1, 2, 1, 2. So you give it to 1. So this one is what now? And you have 2 chloro. Alright, the chloro is at carbon what? One of them is at carbon 1 and the next at carbon 2. So it's going to be called 1, 2 dichloroethene. Alright, so if they are the opposite side, what do you call them? If they are opposite side, you call them trans. So this one is the trans 1, 2 dichloroethene, right? Because they are opposite side. The hydrogen of what? Opposite side. Alright, the hydrogen of opposite what side? But if they are on the same side, it's going to be cis, the same guy, because this is 1, this is 2. So the chlorine, that's now 1, 2. You know, I can literally call it cis 1, 2 dichloroethene or ethane, you understand? Or just call it ethene most times. Because the hydrogen are facing, they are in the same side, either on opposite side. We use the hydrogen. We can also use other substance, but let's use the hydrogen so it's easy, so you don't forget. If the hydrogen of opposite side are seen in the up one trans, if they are on the same side, it's called a what now? A cis. Class, hope you are following me. Oh. Hope you are following me. Hope you are following me, guys. Hope you are following me. So that is for that. So now let's get into optical isomerism, which is the number 2. Alright, let's get into optical isomerism. What happens in optical isomerism? In optical isomerism, the compounds will possess a chiral center. Alright, don't worry, they're all easy. In optical isomerism, the compounds will possess a chiral center. Let us work on optical isomerism. In optical isomerism, the compound possesses a chiral center. So they ask you which one is also called the cis and trans. You simply tell them that it is what geometric word isomerism. You tell them it's geometric word isomerism. So let's talk about optical isomerism, which is a number next on stereo. Optical isomerism. What is optical isomerism? What's optical? Optical isomerism is a type of stereo isomerism stated on the board in which compounds have same molecular formula. Now that one we just drew. Look at the molecular formula, they're the same. You can see this one, H to that one, they're all the same. Alright? So in isomerism, you have the same chemical formula, but difference is something. Like in those guys, they're different in the way those things are arranged in space. The hydrogen, the chlorine, the CH3, all those things. So now let's get into optical isomerism. Optical isomerism is a type of stereoisomerism in which compounds have same molecular formula or chemical formula. We already know that. But there is a difference in in the arrangement of the atom in space. Alright, such that they are non-superimposable mirror image of each other. Alright, just relax, just relax, just relax. I'm going to explain what I mean by this. Just relax, just relax, just relax. Let me explain something to you now. Just relax. I just mentioned the word and I don't want you to be confused. So I'm going to basically work on it right now. So in optical isomerism, where do you know that anything isomerism you have the same chemical formula but different arrangement in your structures, right? So that is for that. So and another key point about isomerism, this optical, is that you should possess a chiral center. In optical isomerism, you possess what? A chiral center. Let's say we have a compound like this. This is X, this is Y, this is Z, and this is what? P, for instance. Now, what is a chiral center? Relax. In optical isomerism, you must, the first point you should take note here is that you must possess a chiral center. What is a chiral center? A chiral center is a carbon that is directly connected to that is directly connected around, directly like, it's a type of carbon where like 4 different things are surrounding it. 4 different. So all these things are different. So this carbon here is a chiral carbon. Alright, chiral what carbon, which basically forms a center. Alright, they call it a chiral what center. Do you understand what I'm saying? So in optical isomerism, the compounds that are involved in the optical isomerism must have a chiral center. Alright, must have different things surrounding it. 4. You can see X, Y, Z, and P. There are 4 different things. Are you there? So that is for that. And also for isomerism to occur, you should basically listen. You should basically have a chiral center. That's one point. And also for isomerism, you should have the what do you call it now? You should have the same chemical form but different structural arrangement. Alright, and I'm going to show you what I mean by that. And I'm going to show you what I mean by that. Just relax and relax. And also compounds that undergo optical isomerism, they are able to rotate plane polarized light Write that down as well. Compounds that undergo optical isomerism, they are able to what now? They are able to rotate plane. These are key points for your jam. They are able to rotate plane polarized light. All right. They are able to rotate what, guys? Plane polarized light. They are able to rotate plane polarized light. They are able to rotate plane polarized light. All right. So that is for that. And I'm going to show you something. Just relax. So I will summarize this thing right now. I just said. So for you to undergo optical isomerism, you must basically first have same chemical formula but different structures. That's normal. Very importantly, for the compounds to be able to undergo optical isomerism, they must have a chiral center. That's the second point. After having the same chemical formula, they will have what? A chiral center. Are you there? After having the same chemical formula, they will have a chiral center. Alright? And also, most importantly, they will be able to rotate plane polarized light. Just listen. This plane polarized light I am talking about can be rotated to the right or left. Everybody listen. This plane polarized light I'm talking about can be rotated to the right or left. If, for instance, I will show you what I mean by all this. If, for instance, this plane polarized light is rotated to the left, to the right, they call it dextro-rotatory. If this plane polarized light is rotated to the left, they call it labio-rotatory. I will explain. Relax. If this plane polarized light is rotated to the right, it's called dextro-rotatory. If it's rotated to the left, it's called what? Labio-rotatory. Dextro-rotatory and then labio-rotatory, guys. Alright? So that is for that. If the plane polarized light is rotated to the left, dextro-rotatory, right, labio-rotatory. Alright? I'm coming so we can move further. So we can move further. Everybody just pay attention. Relax. So that is for that. So remember, for you to be able to, basically undergo optical isomerism first, normally all type of isomerism undergoes it. You must basically, have same chemical formula. You have different structures, but the same chemical formula. Also, you have a chiral center in you, and also you must be able to rotate plane polarized light. Some of them rotate plane polarized light to the right, some of them rotate to the left, and I will show you what I mean very soon in a few minutes. Alright? Just relax. I want you to digest all what I've said. I can't see I'm repeating all this. I'm repeating all this. Alright? So that is for that. All right, that is for that. All right, so I'm going to use an example of a compound to explain what I mean by a compound rotating plane polarized light to the left or right, and also how, because when a compound rotates a plane polarized light to the right, they call it destrorotatory. So that compound formed, they call it the D form of that compound. If you rotate it to the left, they call it L form of that compound. Relax. I'll be using lactic acid as an example. I'll be using lactic acid as an example. Relax. All these things are easy. First of all, I'll draw lactic acid on the board so you see what I'm talking about. This is lactic acid. Alright, lactic acid is bonded to COH. There is CH3 here. There is OH here. No, there is H here. And also there is a CH3 here. Alright, so this is lactic acid. And I'm going to draw another one at the... I'm going to draw another one here. This is another lactic acid. But this time around, you have to be very smart. I did something. I changed something. Looking at this lactic acid, look at what I did, guys. I changed. Can you tell me why I changed something? Both of them are lactic acid. But now I changed the position of something. I changed the position of something. Here, the OH was here, right? Here, the OH was at the left. Now, the way we understand the D form of compounds is that you use the penultimate carbon, meaning the carbon before the last, to determine the D or L, to determine if that compound is rotating plane polarized light to the right. Now, if the OH group is found at the right, is found at the right hand side, it means that that compound is rotating to the right. We call it destrorotatory. So now, this compound will be called D-lactic acid. But if the OH is rotated to the left, this is left hand side down, so that compound will be called L-lactic acid. Are you there? All these things are not hard. All these things are not hard, everybody. All these things are not hard. Alright? I repeat again. I repeat again, everybody. I repeat again. Now, optical isomerism. In optical isomerism, first of all, the first thing you must understand is that in optical isomerism, that compound we have. Now, if you check the chemical formula, let's bring it to this C, yes. Now, just relax. There is carbon at the center bonding to, hydrogen. Like, it's literally the same. If you want to compress them, same thing. Like we have C3, 1, 2, 3, C3, H works 1, 2, 3, 6, and O3. Yes, now do this one as well. It is also what C3, H 1, 2, 3, 6, H6, and O3. 1, 2, 3. You understand? So you can see that they have the same chemical formula but different structures. And the structures are based on how they rotate plane polarized light. Alright, and for you to undergo optical isomerism, you must basically become a chiral center. You must have a chiral carbon. If you observe now, look at this carbon. Are they not attached to 4 different groups? Look at them now. Are they not 4 different things? So you can see that you must basically possess a chiral carbon. You must basically possess a chiral carbon, guys. Possess, very important. Alright, you must basically have a chiral carbon, and also you will be able to rotate plane polarized light to the right. So this one now, the plane polarized light was rotated to the right. This one was rotated to the left. Are you there? So when it was rotated to the right, they call it D form of lactic acid. If it is rotated to the left, it is the L form of lactic acid. This is but don't worry, even if you don't know lactic acid before, chemically, this is it. Alright, but that's no problem. That should not stress you at all. Alright, all that matters is you understand the picture behind all of these things happening. Do you understand what I'm saying? So that is for that. That is for that. You coming, guys? Alright, so you can see how all these things are working. I'm coming, just give me a few minutes. I want to put off this J now. Alright guys, can you hear me now? If you can hear me, let me know in the comments. If you can hear me, let me know in the comment section. If you can hear me, let me know in the comment section so we can move further. So you can see the dextro-rotatory and the labio-rotatory. All right, good one. All right. So under optical isomerism, we have like two types. I'll explain that right away. Under optical isomerism, we have like two types. So just pay attention. All right, coming guys. So we can move further on the types and get to understand it well. So we are still on optical isomerism, we're not done yet. So on optical isomerism, we have two types. We have what we call enantiomerism and diastereomerism. Relax, they're not hard. We have what we call enantiomerism and diastereomerism. Enantiomerism and diastereomerism. Now, before I move further, let me just tell you something very vital. If I talk on this enantiomerism and diastereomerism, though I've been talking about them, but I can't not tell you that I'm talking about them. Don't worry, I will explain it right now. All right. So before then, let me tell you something about the characteristics of compounds that undergo optical isomerism. Remember, we established the fact that these compounds, pay attention, we established the fact that this compound, number one point about them is that they should change their isomerism optically. They have the same chemical formula. Also, they have paracenter, they should have paracenter seen in this lactic acid. Also, they can be able to rotate plane polarized light to the left or right. How do you determine which one is D? If you rotate to the right, you are dextro-rotatory. If you rotate to the left, you are the labio-rotatory or labio-rotatory, guys. Alright, labio or labio-rotatory, we have established on that. And how do you get that? It's based on the carbon before the last carbon. Alright, the carbon, use that carbon before the last carbon. If the carbon is located at the right hand side, it is dextro. If the carbon is located at the left, it is the L form, which is labio-rotatory. Alright, and another very key thing you have to know about these guys that are enantiomers. Sorry, these guys that undergo optical isomerism is that they are mirror images to one another. Let me explain what I mean by that. Generally, compounds that are undergo optical isomerism, generally speaking, they are mirror images to one another. Let me draw them. So this is COOH bonding to C. Here is H, here is OH, and here is CH3, right? So let's say this is a mirror. Alright, so now this is COOH and this is bond. Now, if you see what I've drawn, the D form and the L form, they are always mirror images to one another. Now, if you look yourself in the mirror, is it not when you get back? When you look yourself in the mirror, you get yourself. So this thing looking at the mirror, so it's getting its own reflection, its own self. Do you understand? So compounds here, specifically optical isomerism, they are always mirror images to one another. Alright, so these are features you should know about them. They are always mirror images to one another. Alright, they are always mirror images to one another. They are always mirror images to one another. Alright, they are always mirror images. When you look at yourself, you say, this is a reflection of me. They are always like mirror images to one another. So that's the point. Looking at these guys, this one is the D. Why? D lactic acid. Why is it D lactic acid? It is D lactic acid because the functional group, the carbon bearing this OH is located at the right. This L, carbon bearing this OH is located at the left. Do you understand? This is L-lactic acid. And to get it, you look at the penultimate carbon, the carbon bearing the last carbon. So the dimension is D and L form of a compound. Alright, so that is for that. So guys, moving further, let us talk about enantiomerism and diastereomerism. What are the differences so we can get it well? Now, enantiomerism, and listen, and also most importantly, okay, now we have two types, enantiomerism. What is enantiomerism? It is a type of optical isomerism in which two molecules are non-superimposable mirror images to one another. This is not a big word. Two compounds are not, they are non-superimposable. I cannot take this one and place it on top of this one. Think, can it be imposed on this? Let's say I pick this one with this now and just put it here. You see that OH will be here. It cannot be arranged, so they are non-superimposable. Alright? These compounds called enantiomers, they are types of optical isomerism that are non-superimposable to one another. They are not. They are not superimposable to one another, guys. Are you there? They are non-superimposable to one another. So that is for that. While every other thing I've been discussing about, talking about Cara center, talking about a rotating plate polarizer to the left and right, destro rotatory, linear rotatory, are all characteristics of enantiomerism. Are all what characteristics of what, guys? Enantiomerism. All what I've been talking about, they are all characteristics of what? Enantiomerism. What about diastereomerism? Diastereomerism occur when the compounds are not mirror images to one another. All right. Like the point I want to make here is this: like enantiomerism, diastereomerism, they are different. If they actually what gave rise to that D and L form, it is the diastereomerism. Now, the D and the L form of these compounds, like this is D lactic acid, this L lactic acid, they are called enantiomers. Remember, general term is isomer, right? But specifically, since they are under isomer, all what I've explained, compounds rotating plane polarizer to the right, to the left, and the destro rotatory, linear rotatory, they are all under enantiomerism. While diastereomerism, they are compounds that are not mirror images to one another. All right, they are compounds that are not mirror images to one another. Do you understand? That's one key point you should know about them. They are not mirror images, and they usually have different physical and chemical properties. Right? They usually have different physical and chemical properties. Note that as well. All right, and also that is that. But they are not the ones that give rise to that D and L. What gives rise to D and L is the enantiomerism. All right, so that is for that. No, the point is this. Now, see, the difference, one of the difference between enantiomerism and diastereomerism, enantiomerism, they are mirror images to one another. Diastereomerism, enantiomerism, they are mirror images. Yes, now, this is a mirror. But diastereomerism, they are not mirror images. Are you there? They are not. For enantiomerism, they are mirror images. While for diastereomerism, they are not mirror images. That's one of the key differences. All right. So that is for that, guys. So let us move further. Let us move further. Note all these. Now, let us learn something very, very vital. We have to note here that whenever enantiomers mix, like for instance now, this D form of lactic acid and L form, they can mix together. When two enantiomers mix, they form what we call a racemic mixture. What did I say? They form a racemic mixture or a racemate. Whenever enantiomers mix, like the D and L, which are under enantiomerism, they form what we call a racemic mixture. All right. And now remember, let me just tell you, those ones that are like this, the one that rotate plane polarizer to the right, which is the destro and the left, they will not cancel each other. The solution will not be optically inactive. Normally, they were optically active individually, but after they mix together, this one is positive, this one is negative, they will not cancel each other. The compound in general will not be optically inactive. So a racemic mixture, which is formed by a combination of two enantiomers, they are optically inactive. A racemic mixture, a racemate are optically what? Inactive, guys. They are optically inactive. Note that they are optically inactive. They're optically inactive. They are optically inactive. Note that thing I just said, very, very vital. The D is usually the plus, the L is usually the minus, you understand? And then they will now basically cancel each other to become optically inactive. Note that, to cancel each other to become what? Optically what? Inactive. Are you there? Let us move further. Let us move further. Now, let us talk about this. You know, we've been talking about hydrocarbons and the rest. So we'll talk about, we're done isomerism. Yeah, we are done. No much talks. So let's talk about hydrocarbons in general. You know, we've been discussing about hydrocarbons like ever since, but there are other key points we have to know about hydrocarbons. So everybody, you have to pay attention on this right now. Now, hydrocarbons, they can be gotten from various sources, all right? You know, hydrocarbons are compounds that contain carbon and hydrogen, hope you're aware, and they can be gotten from various sources. Hydrocarbons basically are gotten from coal, natural gas, petroleum, all right? And these places they are gotten, they're usually called fossil fuels. When hydrocarbons are gotten from coal, natural gases, or petroleum, they call them fossil fuels, right? Now, without wasting time, let us move forward to talk about some terms called there's one term I want us to learn: octane number system. Octane number system. What is that? Because people do hear of that, but they don't know what it is. Octane number system. Now, this octane number system is a method used to measure the anti-knocking quality of petrol. Pay attention. Octane number system. Octane number system is basically I'm not going to say it now. It is the method used to basically, you know, measure the anti-knocking quality of a petrol or a gasoline. Are you there? Or a petrol or a gasoline in an internal combustion engine. Like in an engine, all right? So it's a system that basically explains the octane number, the measure of the anti-knocking quality of a petrol. Because there are some fuels, petrol that can knock engine. So this system helps us to understand if a particular fuel can knock an engine. So you have to basically, the method used to check, all right, to measure, all right, the anti-knocking quality, all right. So what is knocking? Knocking is an irregular or explosion of the fuel in the engine cylinder. That's knocking, and when the engines will not just knock, some part of the engine can just burst. That's knocking, all right. So that is for that. Now, octane numbers that are usually low, they can cause knocking, while compounds with octane numbers high, they resist knocking. Are you there? Take note of what I just said. Octane number that is low, they can cause knocking. That octane number that is high, usually 100 and above, 100, they are basically, they resist knocking to occur. Are you there? They resist knocking. All right, so that is for that. Now, there is a very, very vital compound that basically is used to perform this. They call it 2,2,4-trimethylpentane. All right, this is a very, very important compound here to prevent knocking. 2,2,4-trimethylpentane. Pentane. Can we draw the structure? Yeah, we can. 5-carbon pentane, right? 1, 2, 3, 4, 5. And it said 2,2,4-trimethyl. So you have like 3 defined methyl. One at carbon 2, 1, 2. Okay, 2 to 4. So here is CH3, CH3, and then 1, 2, 3, 4. So another CH3. Alright, you are good. don't worry, this is the name of the compound, this is the structure of the compound. So this compound is very, very vital to prevent knocking. It's a very vital compound to prevent knocking. Alright, it resists knocking. 2,4-trimethylpentane. It resists knocking. Alright. It's called isooctane. It's an isomer of octane, isooctane. No problem about that. I don't want to really stress on that. Just know that 2,4-trimethylpentane is very essential. All these things to follow. This 1, 2, 2, 4, 3, 4. Trimethylpentane. This is correct. This 2,4-trimethylpentane. Alright. So you can see what we are talking about. So this compound is very essential. It resists knocking a lot. Alright, it resists knocking. So a high octane number, in summary, we basically work like it leads to better resistance to knocking. While compounds with octane number that are very low we cause knocking. Alright. Another very key thing you have to know about this octane number is that compounds that are compounds that are branched, hydrocarbons that are branched, alright, and they have like higher octane numbers than those that are those that are straight. There are a lot of branches here. Alright, this is a branch, this is a branch, this is a branch. So basically, hydrocarbons, they are all hydrocarbons that are branched. They basically have resistance to prevent knocking of an engine than those hydrocarbons where they have a low resistance, like those with straight chain, no branches, hydrogen. You understand what I'm saying, right? So that is for that. That is for that, guys. Alright, so let us move further about that. You can see we've talked about octane number, and let us get into other various concepts. Now, another very, very important concept I want to talk about is what we call cracking. We just stressed on octane number system. The fuel will have to contain all of this. So a fuel that has more of higher branches and high octane number will resist knocking than those with lower octane number. You understand what I'm saying, right? So let's talk about cracking. What is cracking, everybody? What is this cracking we are talking about? Guys, can you hear me? If you can hear me, let me know in the comment. What is this cracking we are talking about? What is cracking? People do talk about cracking. Cracking is a very, very important process in this, hydrocarbons, petroleum, and engines or engine. It's very essential. What is cracking? Very easy. There are jam questions that I've asked on cracking. So cheap. Cracking basically is the process whereby you break a large hydrocarbon into smaller ones. Yeah. And this could be done with heat or catalyst. Alright. So it is the process of breaking a long, heavy chain hydrocarbon to a shorter one. So this is a marker, I break it. So in cracking, you form like two or more products. Do you understand what I'm saying? So that is cracking. Cracking could be done with heat or catalyst. So we have what we call catalytic cracking. When it's done with catalyst, they call it catalytic cracking. And when it's done with heat, they call it thermal cracking. Are you there? We have catalytic cracking and what thermal cracking. Why do we need to basically ensure that we break a long, heavy chain hydrocarbon into shorter ones? What is the relevance in this aspect? I'm going to explain the relevance, but I've just told us the types of cracking we have. I'm going to explain the relevance of this thing, all right? But I've told us the type of crack we have: catalytic and thermal, all right? Cracking basically helps to increase the petroleum production, all right? And also it produces now we have heavy hydrocarbons that are less useful. So when they crack it, they will not be useful. They will not form useful product. And what I'm trying to say right now. Also, cracking improves fuel quality. All right, cracking improves fuel quality. So I'm going to tell you three very important relevance of this cracking. Now, one of them is that increases petroleum production. Yeah. For instance, I want to break a very long chain hydrocarbon, like maybe decane, for instance. If I'm going to break decane is very long. then I'll convert it to maybe pentane and pentene rather. Decane and pentene. What is decane? What is the chemical formula of decane? Tell me. What is the chemical formula of decane? Decane is C10H22, right? C10H22, right? So C10H22 to give me what now? C5H12 and also C5H10. You can see what we have formed. This reaction is balanced. I have 10 carbon on the left, 10 carbon on the right, 22 hydrogen on the right, 22 hydrogen on the left. So you can see what is happening. So in decane, you are breaking those heavy hydrocarbons with all these hydrocarbons to shorter ones that will be very useful in production of things that are, because let me tell you something, like we all those are our hydrocarbons, like for instance the alkanes, for instance. I want to tell you something. These are what they use for all those our gas, to fill our gas. You can check your gas in your house, you see some of them. They have liquefied petroleum gas, like that. They're useful in our gas, like that. These are like our gas in our house, like in our houses. Those what do you call it? They use all of these guys we are studying right now. You understand what I'm saying? They use all of these guys we are studying right now. Like for instance now, from methane down to from methane down to butane, they are all gases. Whereby from pentane down to decane, they are liquid. Alright, by state of matter. Alright, so I'm trying to tell you that okay, methane down to butane, they are gases. They are what we use to fill our gas in our house. They burn. Do you understand? So that is that. So we have to basically, you cannot just use decane like that. You have to break decane to form things that are small that can be useful in the house, in household. That's one of the importance of cracking, to make useful products and also to make products that will now be that will have good octane numbers. Alright, when you break a large hydrocarbon, it forms those small hydrocarbons with good octane numbers. Do you understand? And that will also increase the fuel efficiency, because we've established the fact that if the octane number is low, the fuel efficiency will also be low. That the ability for that engine to knock will be high. You understand? If the octane number is low, but if it's high, the ability for that fuel to knock the engine of that car or anything at all will be low. If the octane number is low, if the octane number is high, you understand what I'm saying? Hope you get what I'm saying. So that is for that. So you can see what cracking is. Cracking could be done with heat. Cracking could be done with catalyst. Alright, so that is for that. That is for that. Now another very vital term I want to explain is called reforming. Alright, reforming. What is reforming? In reforming, it is a process of rearranging, the structure of hydrocarbon molecules in petrol to form branched chain, cyclic, or aromatic compounds in order to improve the quality of the petrol. So in summary, cracking and reforming are very essential to improve the quality of your petrol. In our petrol, they have different hydrocarbons. So we've said that we've established the fact that if these hydrocarbons are basically, I'm going to say now, they have good octane numbers, the resistance for that engine to prevent knocking will be high, and also if they are also branched chain, the engine will not knock easily. Do you understand? So in reforming now, it's different from cracking. Cracking will just break heavy hydrocarbons. In reforming, we rearrange structures, maybe straight chain structures to form branched chain structures. Do you understand? In reforming, we are rearranging hydrocarbons to form other forms of hydrocarbons. So specifically, we are rearranging all of those straight chain hydrocarbons to form branched chain hydrocarbons, or not just that, cyclic hydrocarbons or aromatic hydrocarbons, because those ones works better in car engines, our engines. You understand? They burn better. The ones that are branched, we've established that. If you don't know this one as cyclic, those are cycloalkane, they work better too, and your aromatic compounds, they work better in the engines. So the reason for reforming is to basically improve the quality of your engine. You say improve the quality of your engine. That's reforming. That is what reforming means. So reforming basically helps to increase your octane number, and it helps in the conversion of a straight chain hydrocarbon into I will say now what do you call it? Into a straight chain hydrocarbon into a branched chain hydrocarbon. Reforming, there are different types. Listen. When a straight chain hydrocarbon straight chain hydrocarbon is converted into a branched chain hydrocarbon. You know what I mean by straight chain now? If you observe it, we worked on this on isomerism, right? They call it isomerization. I repeat, yes, now we talked about isomers, chain isomerism. You know, we converted those butane to methyl propane. Yes, now. So that's isomerization, when you are basically converting a straight chain hydrocarbon to branch chain, because these ones that are branched, they work better in our car engine. When you also convert a straight chain hydrocarbon, for instance, a straight chain hydrocarbon into a, a cyclic compound, into a cyclic compound, like those cycloalkanes, like that, cyclic compounds, they call it cyclization. All right, cyclization. That is for that. All right, so that is for that. I'm coming. If you are still online, do it to signify so I can move further. When you know, let me just tell you, reforming can also be done with heat and also with catalyst. All right, so just note that if reforming is done with heat, the petrol that are like, the conversion will not work better, like well, than the catalytic. So catalytic is better. You understand? So that is what I want to tell you about the types. If you're online, do I to signify? Good, good, good. Cyclization. Cyclic compound, we call it cyclization. Or if lastly, a straight chain hydrocarbon is converted into an aromatic compound like benzene, then we call this one aromatization. Do you understand what I'm saying? So, so you are starting with straight chain. When you convert it into branch or maybe cyclic compounds or aromatic compounds, then we call this reforming. And reforming helps, you know, to improve the quality of your fuel, maybe in octane number, and you know, so on and so forth. And so on and so forth, guys. Just pay attention. They're very, very easy. They're not hard at all. They're not hard at all, guys. I'm coming. In catalytic reforming, catalysts like platinum, alumina, platinum is used in catalytic reforming, right? And thermal, it works at a very high temperature. No catalyst is used in thermal reforming, all right? So that is for that. So we can move further. So I want to write the board so I can stress on this reforming. So in reforming, not what I want to say right now. For instance, I have maybe butane, which is like this, right? And butane is straight chain. They explain this using chain isomerism. Butane is straight chain, you know, we're seeing it right now. Converting butane into this guy, a branched chain compound like this. You know, they will still have the same chemical formula, that's the sodium. They're still going to have like formula, like the same chemical formula, like 2 methyl. Okay, just listen. This one is branched. This is a branched form of this butane. This one is 2-methyl propane, right? 2-methyl propane. So this one is what now? Isomerization. You understand? I'm converting butane into a straight chain hydrocarbon. So this one that is now formed is now work better in our petrol. When our petrol has these gases, they'll work better. Remember I told us for our alkane, from methane down to butane, they are all gases. From pentane down to decane, they are liquids, right? So that is for that. That is for that. What about the next one, which is converting a straight chain hydrocarbon into a cyclic hydrocarbon? I can literally use this guy. What's this guy? For cyclization. I'll convert C6H12, which is C6H14, which is hexane, to cyclohexane. All right, and there will be liberation of hydrogen gas. Now the reaction is balanced. If I form this reaction is balanced, if you check, we have the same chemical formula. This guy is C3. No, it should be butane. This one should be butane. H, right, and H. So this is butane. We're going to see for H words 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 10, right? Forming this one is what? Is this C for H what? 1, 2, 3, 1, 2, 3, 4, 6, 7, 8, 9, 10. So it's this for H10. So we getting this back, we are saying, oh, this is isomerization. So I can literally still convert a straight chain hydrocarbon to a cyclic compound using hexane. So cyclohexane. Look at it. This is hexane, which is C6H14. So cyclohexane, which is C6H12. What I told us initially, and the liberation of hydrogen gas. Is it reaction balance? Yeah, we will have 6 here, 14, and 14. So this is cyclization. Why is this cyclization? Because we have formed a cyclic compound. I can draw this now. I want to show those stuffs with drainage out. Alright, what about aromatization? When you're forming an aromatic compound like benzene, right? So you're changing, I can literally change hexane to benzene and hydrogen gas. Alright, so in this case, it will not be something like this. From hexane, same hexane, this is a thing. So this is H6 plus hydrogen gas. So what happened? Remember, I have around 6, 6, and 14. So I have 6. So what should I do? I need words. Is it 8? Is it 4? To balance the reaction, tell me, what should I do to balance the reaction? Balance the reaction, guys. Alright, so it's gonna be like 4, right? 4 here. I drew like here, let me 4 times 2, 8. 8 plus 6. What is that? This is aromatization. Forming an aromatic compound like benzene, right? Aromatization, everybody. So you can see how it works. You can see how easy it is, right? Good. So that is for that. Alright, so these are reforming. Reforming should be done with catalyst or normally without catalyst like heat, just you apply heat. So now we are done with all of these things, and alright, we are good to go. So let us start on alkanes properly. Remember, when we talked about alkanes, I told you guys that alkanes are also regarded to be called what? Paraffins, right? We established the fact. So let us start on alkanes right now. Who are alkanes? Let's go. Alkanes are also regarded to be called paraffins. We already know the general formula, which is CnH2n plus 1. Sorry, plus 2. Rather. Let's look at paraffin. The general formula is CnH2n plus 2. We have established this fact. The first member of the alkane is methane. Alright, the first member of the alkene family is methane. And this methane we're seeing here can exist in 2 forms. When methane is found in a burnt vegetation, they call it fire damp. But when methane is found in a swampy area, they call it marsh gas. Guys, note all this, alright? Note all these things I'm saying right now. They are very essential. Why is this thing blurry now? Alright, good. So when methane is found in a burning vegetation, they call it what? Marsh gas. Alright? So no, burning vegetation, fire damp. When it's found in a swampy area, marsh gas. Now, how is methane prepared? Alright, that's what we want to learn right now. Preparation of alkanes generally. So the first member I want to focus on is methane. Alright, let us do it right now. Methane is prepared by what? By reacting an anhydrous sodium ethanoate with an alkali like a base to form sodium carbonate and methane gas. To form sodium carbonate and methane. I'm going to show us the reaction and explain to us how it works. So you have to pay attention to every single process. Pay attention to every single process. So preparation of alkanes generally, where I'm going to prepare the laboratory preparation. So alkanes, right? So look how it works. We prepare these guys by reacting sodium ethanoate. It's not a big compound. Don't be scared of the name. Sodium ethanoate. Don't be scared of sodium ethanoate. And sodium hydroxide, which I believe we're familiar with. And then we're going to form a carbonate and methane gas. This is CH3. Are you aware that this CH3, this one is called ethanoic acid? Are you aware? No, anything that has this thing is called ethanoic acid, right? And this one is 2-carbon ethanoic acid or acetic acid. But when I remove this H and replace it with Na, they call it sodium ethanoate. That's the name. Reacting with sodium hydroxide. So what do we get as our product? That's the question. Very easy. Look at how it works. Look at how it works, guys. This COONA will leave this CH3. Alright? We leave this CH3 and combine with the NaO. Are you there? Just pay attention. You combine with what? NaO. And then we're going to form what? Na2. Now, Na2. Na2. And then CO. How many oxygen? 1, 2, 3. CO3. Alright? Plus the gas. Now, this hydrogen that I said will not combine here, will not come here. That is CH4. Understand? So this is how the gas is formed. So easy in the lab, right? So this is methane gas. You can see how we formed it, right? You can see how it was formed. Very easy. All right. Other alkanes can also be prepared similarly, all right, by this process, but no problem. Let us just move further. What are the physical properties of alkanes generally? Methane, which is what we have prepared. One of the physical properties of these guys is that methane, they are colorless and they are odorless, and they are slightly soluble in water. These are colorless gas, they are odorless gas, and they are slightly soluble in water. They are colorless, they are odorless, and they are slightly soluble in water. Another thing you have to know about them is that they are less dense than air and have no action on litmus paper. Meaning that, acids turn blue, litmus paper red, bases turns red, litmus blue, but methane is an alkane, does not have any business with litmus. Alright, there is no action on litmus. There is no action on litmus. Are you there? Now moving further, let's talk about the chemical properties, saying these alkanes. Now, I want to tell you something. There are some specific. When I talk about chemical properties, I'm talking about the reactions that they undergo. Now, one of the very, very important reactions that alkanes undergo is combustion. All right, combustion reactions. Combustion has to do with an hydrocarbon like alkane reacting with oxygen. When it reacts with sufficient oxygen, it leads to the production of carbon. See, when an hydrocarbon, maybe this guy CH4, react with sufficient oxygen, it is CO2 and water that will be formed. But if, and this one they call it complete combustion, right? They call it complete combustion. Are you there? But if it is same methane gas that reacted with oxygen or limited amount, it comes from CO and water, carbon monoxide, it is incomplete. This is incomplete what? Combustion. Why? Because there is no proper burning occurred. Because combustion is burning. I thought us flame. Combustion is burning. So we have to balance a reaction. At the left, how many carbon? 1. The right 1, how many hydrogen at the left? 4. So I have to put 2 here to balance it. So 2 times 2, 4 hydrogen. How many oxygen at the left? 2. We have 4 here. So I have to put 2 in front because of balance it. So 2 times 2 is 4 oxygen. 4 oxygen. Hydrogen is already 4. Everything is okay. So this is the balance reaction. 1, 4, 4, 4. Everything's okay. What about the incomplete? Let's work it out together. I have 1 carbon, 1 carbon. So I have to put 2 here to make it 4 hydrogen. There we go, 4 hydrogen as well. Doesn't affect the oxygen. Oxygen there is 2. The oxygen is, so I have to put 2, so it will be 4. 2 plus 2, 4. I put 2 here, 4. So this is the, I'm going to say now, this is the incomplete combustion of methane. It forms CO, alright, carbon monoxide, which is not good. So which is carbon monoxide. You can see these are reactions that these guys undergoes. Alkanes generally, not just alkanes, alkenes undergoes this reaction, alkynes undergoes this reaction. Alright. So that is for that. So wasting time, another very vital information that these guys undergo is called substitution reaction. Pay attention. This one is very, very vital. Alkanes undergoes substitution reaction. Let me explain what I mean by that. Alkanes undergo substitution reaction. They don't undergo addition, they don't undergo substitution. This is how it works. Let's say we have ethane here. This is H, this is H, this is H, this is H, and this is H, this is H, right? React, and this happens when they react with chlorine, all those diatomic gases like hydrogen, chlorine gas most times. So they do substitution reaction. They call this reaction chlorination or substitution. It's a substitution reaction when the chlorine now will now be 2, and the chlorine, the one of the chlorine atom will attack one of the hydrogen. You there? I'm not teaching the mechanism. I'm just teaching the basic things that happens. So then this chlorine enters here, substitution pushes this one away, and then the chlorine fits its place. Do you understand? So this one that has been pushed away will now come out with this one. So what becomes a product we're going to get? Just pay attention. H, 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 H. The chlorine is now here, H. Then this one that was pushed away will now come out with this one from hydrochloric acid. Are you there? So let me just, I've displaced it. Alright, I've displaced the hydrogen. So this common line, I've displaced it. You understand what I'm saying? So this is the chlorine entered. So alkanes undergo substitution. Things, they are saturated, and you cannot add things to them. You can only remove and you can only substitute. You understand now, right? Now, what are the uses? Methane is mainly used as fuel. Alright, we talked about that. That's what we use in our house. Fuel and the rest. And methane is used for making hydrogen, carbon black, carbon 4 sulfide, and so many other things. But we should just, take note of all this we have said. So that's for alkanes. Now let's get into alkenes. We established the fact that alkenes are also called olefins, and they have their general formula to be CnH2n minus. Oh, sorry, CnH2n. That's for alkenes. Take note, alkenes undergo substitution. Take note, alkane undergo substitution. Where you substitute things. Now this one will form, they call it chloroethane. That one will form what? Chloroethane. It's not hard. So now, moving further, let's talk about alkenes. Now, alkenes, basically, they have their general formula to be CnH2n. And we've established the fact that, just pay attention, we've established the fact that from ethene, propene, butene, they are all colorless gases. Remember, for alkane, I told us that from member 1, methane to butane, they are all gases. Same applies to these guys. From ethene to butene, which is but1 and but2, you know what I'm talking about, of draw with name compounds. These guys are all gases, and they are colorless gases. All right. Whereby from pentene down to heptene, they are all liquid. While those ones that are higher, they are solids. So in summary, like how am I going to say it now? How am I going to say it now? From this, not heptene, not heptene. So from those guys with one carbon, no, there's not like, so you start from two carbon down to four carbon for the alkenes. They are all colorless gases. From 5 carbon to 17 carbon, they are all liquid, whether 17, whether 18 and above. They are all solids for alkenes. Not it all. They are all solids. They are all solid, guys. They are all solid. Note that. That will help you a lot. They are all solids. So let us move further. Let us move further. When a compound has 17 carbon, they call it hepta. I'm going to call it now. It's called heptadec 1-in or heptadecene. Heptadecene, like, you know, hepta is 7 and dec is 10, so 10 plus 7 is 17. Heptadecene, decene, not decane, no, decene. All right. Now note this: alkenes generally they tend to burn with more luminous flame. All right, meaning that alkenes most times the way they burn is the flame they produce is not a clear flame. You know, when a flame is clear or clean, it is a non-luminous flame. I've established that. If you don't know it from now, when a flame is clear or clean, it is a non-luminous flame. But if it is not clear, smoke is misty, it's cloudy, that flame has color, so it's a luminous flame. A flame with color is a luminous, and that is how alkenes burns. Alkenes burns most times. The way they burn is like, you know, producing non-luminous flame. You understand? Or like they just produce flame that are not even more luminous than that of the alkenes. Now, how do we prepare the first member of the alkenes called ethene? But we are focusing on just their first member. We prepare ethene by heating ethanol with concentrated tetraoxosulfate 6 at a temperature of about 170 degrees Celsius. Now let me show you how it works. All right, you see, preparation of alkenes. Preparation of alkenes. We are on alkene, right? Yeah. So let's prepare alkene. The first member, I want to prepare ethene. I want to prepare what? Ethene. Pay attention. How to prepare ethene? By reacting ethanol. This is ethanol. Do you have me? I've worked on this before many times. This is ethanol. It has 2 carbon. It has 2, and it's null. So it has OH somewhere, right? So I can literally put the OH here and basically put. And this one, it works in the presence of what now? H2SO4. H2SO4. And at a temperature of about 170 degrees Celsius, very high. So what do we get? Pay attention. Very easy. Now let me tell you, from metals, non-metals, I believe I've told you guys that H2SO4 is a dehydrating agent, meaning that it's something that likes to remove water. Something that is dehydrated here removes water. So they will remove water in this compound ethanol. They will form the alkene. You know, when we remove water, look at what happens. When we remove, how can we remove water? We remove water by basically removing H. Look at it down. Remove these two guys. Now this is going to form H2O. Are you there? We have to remove water. So minus H2O. When that happens, what do we get? You know, listen. We don't just, when we remove water, these bonds that you're seeing here, they will not, we remove them, right? Yes, and we remove what they are holding. Not come together. I'm not teaching mechanism. I'm just telling you the basic thing that's happening. So let's rewrite. This bond will now form a double bond. Are you there? And we'll remove the things. Will now come together to form a double bond. Then we have C, bond C. Alright, bond C. So then that bond is to join together to form a double bond. Are you there? And then H will be here, and H will be here, and H will be here, and H will be here as well. So there's nothing left. So what has been lost? Alright, and what made it to happen is the dehydrating agent H2SO4. Alright, so that is for that. So is this reaction balanced? Is okay. It's a balanced one. So that is how it works, guys. That is how you can ask you what is used in the dehydration alcohols to form alkene. Tell them H2SO4. H2SO4. H2SO4, guys. This is just like, and the H2SO4 must be concentrated then. And you know that guy is a gas. What are the physical properties of this ethene we have formed? Number one is that it's a colorless gas. Remember I told you from the ethene down to butene, they are colorless. It's a colorless gas with a faint sweetish smell. It has a sweet smell, faint. It is sparingly soluble in water, not too soluble in water. It is slightly less dense than air. It is sparingly soluble in water. It is slightly less dense than air, and it has no action on litmus as well. It has no action on litmus. This guy also undergo what they call it, combustion, which I've explained so far. But the reactions that are peculiar to these guys is addition reaction. The reactions that are peculiar to them is addition reaction. Addition. How does the addition reaction works? Very easy. So let me basically look at them and break them down. With this same guy we have formed. So let's basically undergo addition. In addition reaction, something called an addendum is added. An addendum can be hydrogen gas. You know, hydrogen gas is of two, right? H and H, right? So then what do we get? Now, in a reaction, you're adding things, you break the bond. This bond is broken now, and that forms this. Alright? You've broken one of the bond. The H remains, right? The H up remains. The H here remains. And then H here, right? So these two hydrogen you are basically, formed. You're adding, you now basically fill this gate. You're cutting the bond into two. This is not reaction mechanism, this is just proper explanation. So whenever alkenes specifically undergoes addition reaction, they form an alkane. This is ethene, right? Yes, this is ethene. And this is what ethene. Do you understand what I'm saying? Whenever they undergo addition reaction, they form an alkane. Alright, that thing they call them addendum. They form an alkane. Alright. So addition reaction, I was saying, hydrogen can be used, halide like halogens can be used. Do you understand? So that is for that. So we are converting that double bond in the alkene to a single bond. Do you understand? And the reaction is balanced. You check it out. The reaction is balanced. We can literally do the same for alkynes. Okay, we can literally do same for alkynes and you see what we are going to get. So I want you to work on some reactions for me, like that of, just pay attention. If it's an alkyne with a triple bond, alkyne will first form, you'll first form an alkene before an alkane. Do you understand? Because three bonds, you break one, two left, so what you're going to form is an alkene. Break it again with another addendum, you're going to form an alkane. You understand? So now, what I'm going to talk about here is what we call polymerization. It's a very important process. What is polymerization? Polymerization is a process whereby two or more simple molecules, two like simple things are joined together, like two monomers are coming together to form a large monomer, right? You're bringing two things together to form something large. Like for instance, now taking many ethene molecules together in the presence of catalyst and pressure and a high temperature, we get what we call polyethene. All right, this is as a result of polymerization. Ethene, you are seeing it there. When you bring many of them, they form what we call polyethene. All right. So what is the use of this ethene we're talking about? Because they have uses like where we talked about the use of methane. Ethene is the main source of many organic compounds. Like your ethane, you can see is a main source. We formed ethane from it. Not just that, ethanol, ethanoic acid, and the rest. Now, ethene is very important in making plastics, like the polyethylene, like the polychloroethylene, also called the polyvinyl chloride. Please note it. Ethene is used for making polyethylene, polychloroethylene, also called polyvinyl chloride, PVC. Do you understand? So that is for that. Ethene is also important in making synthetic rubber. All right, synthetic rubber. And also, it's also very important in agriculture. Low concentration of ethene are used to hasten the ripening of fruit. Low amount of ethene are basically used to hasten the ripening of fruits. Do you understand what I'm saying? So you have to take note of that. So ethene, low concentration are used in hastening the ripening of fruit. So for alkynes, these guys, we already know their general formula, which is CnH2n-2. We've established on that already. All right. And the first member is ethyne, right? And how is ethyne prepared? It is prepared by in the laboratory by the action of cold water on calcium carbide. And also the gas evolved in the first pass in the gas evolved first pass through an acidified copper 2 tetraisosulfate 6 solution to remove any form of phosphine, all right, presence present as an impurity and then collected over water. The process is accompanied by the release of large amount of heat, and the reaction we are talking about right now is performed on heap of a sand inside a flask. All right, it's not something hard. It's just you reacting calcium carbide with water. Then you're going to form calcium hydroxide and the ethene. Do you understand? Let me explain what I mean by this. So in preparation of ethene, which is an elaborate preparation, you basically react calcium carbide, ethane rather, once this calcium carbide with what? Water, you're going to get calcium hydroxide, and then you get this C2H2, which is the ethane, which is the first member of the alkyne. Do you understand? So these ones are just three units. So you're reacting calcium carbide, calcium carbon, calcium carbide. Alright? Calcium carbide is CaC2. Yeah. So there's a reaction from that. The reason why this happens, just notice let's balance together. So we have how many calcium? We have 2 oxygen, 2 hydrogen, so here should be 2. If there's 2, automatically hydrogen will be 2 as well. And here will be 2. And here will be 2, right? Oh my god, I hope we have not done crazy things. Alright. So here will be what? Just let us look at it this way. Alright, so here is how many? Here is 4 hydrogen. 4 hydrogen, everything is okay. The balance reaction, you can look it well. It is balanced. And what are the reactions that these guys undergo? They undergo combustion and addition. We'll talk about how they undergo addition. So they have to break them many times for them to form diethane. First time you break that, they are triple bond. You break one of them, then you're going to form an alkene. You break it again further, you're going to form an alkane. You understand what I'm saying? Now, please, you have to note this very, very vital, which is test for saturation. How do we know if a compound is unsaturated? All right. So that is what I want to basically talk about right now. Now, you have to understand here that, they use what we call the bromine water test. And bromine water is a reddish brown in color. All right. So let me basically explain test for unsaturation now. Test for unsaturation in an organic compound. Test for unsaturation in organic compound. So we use bromine water test. That's very clear. And bromine water is reddish brown, reddish brown in color. So what do? The bromine water is decolorized. Listen, when you basically react an unsaturated hydrocarbon like alkene and alkynes, hope you're aware about that. We've talked about that now. Alkenes, alkynes, they are unsaturated. You react unsaturated compounds with these guys. All right. We react unsaturated compound with this bromine water. The bromine and you listen. Test for unsaturation. So how do you do it? Let's say you have an alkane reacting with bromine water. So when there is no color change, that means it actually gives a no color change. Do you understand? But when it is either alkene or alkynes that reacts with it, color change. right? It will decolorize bromine water. It will decolorize bromine water, making it that reddish brown to colorless. So it now make the bromine water to be colorless water. You understand what I'm saying? So the unsaturated compounds decolorizes bromine water. The unsaturated compounds decolorizes bromine water. So note that. All right. So the other ways we can test for unsaturated compounds, like I'm coming. Just pay attention. So the other test, like using what do you call it? They call it the Bayes test or the potassium permanganate test. Now pay attention to this. For Bayes test, which is potassium permanganate, you basically react potassium permanganate. What potassium permanganate is KMnO4, all right? KMnO4, and it's purple in color, all right? So if there is like no color change after reacting the KMnO4, which is potassium permanganate with a saturated compound, there is no, they call it Bayes test. This is a normal test. Call it Bayes test. Alright, so if the potassium permanganate does not react with if there's no color change when you react with saturated, then that compound is like an alkane. But if there is a color change, the color is usually purple, and change from purple to maybe a brown precipitate, a brown PPT, then you say that there is an unsaturated what do you call it now? Compound. I'm coming, guys, so we can move further. Alright, so we're going to form a brown precipitate. Alright, from purple to brown precipitate. Please note that. So what is the use of ethyne? So we've been able to differentiate between unsaturated and unsaturated compounds. So what is the use of ethyne? It is used sometimes as a fuel in lamp, which is such as miners lamp. So they can ask you which compound is used as a fuel in miners lamp. Alright, those people that mines, they call it ethyne. Alright, ethyne. And ethyne is basically mixed with oxygen to form a very hot, easily controllable flame called oxyethyne flame. Alright, used for cutting metals, or oxyacetylene flame. Alright, so when this ethyne react with oxygen, they form what we call oxyethyne or oxyl. The first member of the I called alkynes acetylene. Like the first member of the alkyne called ethyne is also called acetylene. That's why we just called it based on the first member. So when oxygen reacts with that acetylene, they form what we call the oxyacetylene flame or the oxyethyne flame, which is for welding and cutting metals. You understand? Which is for welding and cutting metals, guys. Which is for welding and cutting metals. So that is for that. So moving further, let's talk about the aromatic hydrocarbons. Who are the aromatic hydrocarbons? They are literally benzene and its derivatives. Right? These are the benzene and its derivatives. These are the benzene and its what? Derivatives. Now, without wasting time, benzene has so many derivatives. Like this is the structure of benzene, right? At every point there is carbon connected with hydrogen. Okay, where we've established that fact. There's a ring inside, differentiating it from a cyclohexane. So let's say, for instance, now benzene is 6 right? So let's say we try another one, like this benzene basically having OH. In one of the places, hydrogen should be, right? So this one now, we're going to have the word C6H5OH, right? OH, they call it hydroxyl, and this is benzene. So yes, now I remove one hydrogen, make it to be 5, and adding with that OH, so it's called hydroxyl benzene, right? Yeah, hydroxybenzene is the name of that compound right now. So this is called hydroxybenzene. Hydroxybenzene. And hydroxybenzene is popularly regarded to be called phenol. Alright, there are other benzene derivatives to note. There are other benzene derivatives to watch out for. And what are these benzene? Now, the structure was brought about by a man called August Kekule. And what are the other benzene derivatives? When a benzene is attached to CH3, they call it toluene. If it's attached to 2CH3, they call it xylene. Right? CH3, they call it toluene. Toluene. If it's 2CH3, they call it xylene. If it's 2CH3, they call it xylene. So that is for that. So when benzene attached to 2CH3 group, it's called xylene. So I can decide to put it anywhere. And I can put it here and here. You understand? So when it has 2CH3, they call it xylene. Alright, so that is for that. That is for that. Alright. Alright, if your phone is low, you can just relax. I'll continue when your phone is charged. Alright, so that's for that. There are other things about benzene you should know. Like, I'm just giving some common derivatives. There's also one, they call it aniline. Benzene that is attached to NH2 group. Called aniline. Aniline. You know, these ones will not be like, for instance, I'm going to see cis H15 CH3, right? These are what C cis H4 CH3 over at the close bracket, 2 outside, we have 2 of it, right? And this one is what? And let me just write here. C6H5NH3. Alright, so that is for that. So without wasting time, let us get into the properties of these guys. Now you should understand here that benzene generally they are colorless, they are liquid, they are colorless liquid with sweet smell. That's why I told you they are colorless liquid with sweet smell, and they are insoluble in water, and they usually have a boiling point of about 80 degrees Celsius. You know, I told you guys it is liquid that boils, so they will have a boiling point. So in as much as a liquid, it should have a boiling point, NH2 rather. NH2, amine. So that is for that, guys. That is for that. So you can see how we've been able to work on these, the properties. Now the reactions that benzene undergo is substitution reaction. If benzene, like substitution, like, yeah, substitution, if it undergo, what do you call it now? If benzene is to undergo addition, the ring will be destroyed. That ring is that will not be destroyed to form a cyclohexane. Alright? If it undergo an addition reaction, it will form a cyclohexane. The reaction that these guys undergo is substitution. Let me show you. The best reaction that benzene undergo is substitution. The other there's a lot of substitution reaction, like the Friday-Craft reaction. But just understand that this is benzene. You know, at every carbon there are hydrogen. So it will react with chlorine in the presence of the catalyst, which is FeCl3. And then what we get, so this guy will basically form 2. Then we'll get a membrane like Cl is substitute 1, pushes this one away, this one comes down. And then enters. Are you there? though there are mechanisms, or not just these things happening, there are mechanisms to all of these reactions. This is all the H, 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 H. So I remove them, so you don't have Cl. This guy will have what Cl in the structure, right? And then we could literally use hydrochloric acid. Or yeah, so the point I'm trying to make here now is that, so what I found is the chlorine, that the hydrogen that left now bind with this other chlorine to form what now? HCl. So now we see this H5Cl is a product, right? And this is a substitution reaction. Is what? A substitution reaction. If you are still online, do what to signify. This is a substitution reaction. If benzene is undergo addition reaction, the ring will be destroyed. So whenever benzene undergo addition, the ring is destroyed. This is benzene. And this addition reaction, something is added, right? And we add, addition reaction, we add things down. They have 3 moles or molecules of hydrogen gas, altogether 6 atoms. Because 3 times 2, 6. The ring is destroyed. This addition destroys the ring, and then now forms a cyclohexane. That one now, where you know that, okay, that's like the waves like this. Whenever benzene undergoes, so it's not suitable for benzene. This reaction is not suitable for benzene. H, 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 and this reaction works in the presence of nickel as a catalyst. Right, technically it works in the presence of nickel as the catalyst. Alright, and at the temperature of about 180 degrees Celsius. Alright, at the temperature of about 180 degrees Celsius. Note that. So these 6 atoms of hydrogen will not fill all this paper. It's not a stable reaction. This is an addition, something was added, right? This one is substitution. That's the best reaction that benzene undergoes. Substitution reaction. What's the use of benzene? Now, benzene generally is used to basically, to make pesticides, detergents, right? So they're used to make nylon. They used to make disinfectant like phenol specifically. They used to make disinfectants, right? They used to make raw materials for plastics in general, right? So they used to make dye and drugs. So that is for that. That is for that, guys. So what will happen right now, we'll get into alcohols. We have been able to talk about the 3 acyclic hydrocarbon and benzene. So let's talk about alcohols now. So we're wiping the bottle with stress on alcohol. So I'll just give you a few minutes, then get back and continue on alcohols. So let's stress on alcohols, guys. Get ready. Get ready, get ready, get ready. Come in, just wait a little bit. If you're online, do what to signify. Just let me know if you're online. If you're online, do what to signify so we can move further. Just say I am active. Just do that. Just give me a few minutes so I can take a break, then continue the class. Just like 1 minute, 2 minutes. Just wait. But if you're online, do what to signify. Alright, so let us get into alcohols. Alcohols. Are you aware that we talked about the general format of the words? Arrow bond OH, right? And the arrow is also called the word CnH2n plus 1 and then bond OH, right? So what's the first member of this family? You know, a compound that has one carbon, the name is met, right? And I told us that since it's an alcohol or alkanol, we simply just add the anol to it, right? So it's called methanol. So the first member is called methanol. And methanol is also regarded to be called wood spirit. Methanol is also called what? Wood spirit. I believe you're following me. So that is for that. Methanol is also regarded to be called wood spirit. On the IUPAC nomenclature, we're already good on that aspect, right? On the IUPAC nomenclature, we are already good on that aspect with stress on everything. Now, let me tell you something. Alcohol could be of three types. Alcohol could be of three types based on the number of OH present in a compound. Relax. I will explain what I mean by that. Relax. I will explain what I mean by that. We have what we call the monohydric alcohol. We have what we call the dihydric and polyhydric alcohol. Now, for instance, this is a compound which I believe you know. Just relax. This is H, this is H, this is H, this is H, and this is OH. Let's just put the OH here and now put the H here. So how many OH seen in this compound? It is one. Hence, this compound is a monohydric alcohol. Are you there? So this is for that. If it is two OH that is seen, for instance, I have another OH here, it is dihydric alcohol. Do you understand? So we can name the compound actually. So it's not a problem. Alright? We can actually name the compound if it has like two OH in it. We can actually name the compound if there's two OH in the compound. We have monohydric, we have dihydric, trihydric, and also polyhydric. Poly means that you have more than 4 OH. More than 4 OH. So let us move further. All right. Pay attention to what I'm about saying is very vital. I'm coming, guys. Okay. You know, normally this guy with one OH is two. It has two carbon now, so it's going to be called ethanol, right? But let's say, for instance, it has two carbon. But let's say now it now has two OH. How would we name this compound? Normally it has one OH. We call it ethanol. Look at the name now. It's going to be called ethane. Now look at the number there. 1 and 2. They were and 1 and 2. So in any direction, 1 and 2 is okay, right? 1 and 2, 1 and 2. So ethane. Look at the name now. It's going to be called ethane 1, 2 diol. Why we have to solve it? That's the name. Alright. So then say for instance now we have like 3 OH, 3 iron. So they have OH, OH, and OH. This is H, this is H, this is H, and this is another H, right? So now the point here is this. This one is a dihydric alcohol. Dihydric now in this case. Because that's 2 OH. Now this one is trihydric. Tri means 3, right? So let's put it here. This one is called propane. 1, 2, 3, triol. Also regarded to be called what? Glycerol. That's a popular name. Glycerol. From 1 to 3 triol is called glycerol. Yes, now. 1, 2, 3, 1, this is called glycerol. I believe you're following me. So alcohols in general could be monohydrate, dihydrate, or polyhydrate. Now, listen and listen well. Now, we've been able to talk about the. Now, we can also classify alcohols based on the position of their OH, not the number now, position of the OH. And this one, they're just the position, even the number of OH. We can classify them. Poly means that you have more than 4. You know, those ones are saying glucose molecule. Like I draw glucose, I'll show you that glucose has like many OH in it. Yeah, this glucose, pay attention. Yeah, glucose, that's what it's called. Glucose is not an alcohol. Do you understand? Glucose is not an alcohol. Glucose is an alkanal. But those ones are just advanced, just leave them alone. Not really advanced though, they're childish as well. Alright, so that is for that. We can also classify alcohols based on the numbers of the specific position the OH are found. Now let me show you three, let me give you 3 types. Let me just explain something to you right now. Let me explain something to you. Trying to form something so I can write it out and then explain to you what I mean by the other classification of alcohols based on the position of the OH. Based on the position of the OH group. Alright, so here is it. Here is H, here is H, and here is C. H3 for instance. What compound is this first of all? That would be the question. Actually, what compound is this? Or maybe I should do it this way. To make sense. This is CH3. This is carbon bonding to OH. Here is H and here is OH. And let me just elongate this one. Alright, so this is one example. This is another. Okay, wait. I have to draw all of them first so I can basically just explain them to you on how they work. I can basically explain everything to you on how they work. Alright, so in this case, here is a H, H, H. Here is H. Yeah, relax. This is H, H3, this is OH, and this is H3, right? Now, what I'm talking about right now is basically classifying alcohols into primary, secondary, and tertiary. When do we say an alcohol is primary? An alcohol is primary whereby the carbon bearing the OH is directly attached to just one carbon. Okay, listen. And if this carbon is directly attached to just one carbon, then we say it's a primary alcohol. But when the carbon atom, listen, I repeat, primary alcohols are alcohols that the carbon atom bearing the OH are directly attached to one carbon atom. So this is for secondary to this carbon bearing OH is directly attached to 2 other carbons. 2. So then this one is a secondary. But when the carbon bearing OH is directly attached to 3 other carbons. You can see what I'm doing, right? Directly attached to 3 other carbons, then it's a tertiary alcohol, right? It is a tertiary alcohol. We can literally name the compound. This first one is called what? Ethane, right? Ethanol. What about this one? The longest continuous carbon chain is where now? Here now. 3. Alright, so this one is propanol. Alright, 2 propanol. It's not hard, look at how it works. You basically do like this. 1, 2, 3. So the OH that's about 2, so 2 propanol. Alright, what about this one? You can literally use this. 1, 2, so 2. This one is now 2 methyl. There is a methyl group. 2 methyl propan 2 ol. Yes, now there is 1, 2. We must ensure our function will have the last number 1, 2. So this is already a branch. This is a branch of is a functional group, right? So this one is 2 methyl propan. It's 3 carbons now propan 2 ol. 2 methyl propan 2 ol is a tertiary alcohol. Are you there? Alright, so that's what that. Alright, so we are good to go about all this explaining all the classification of alcohol based on number of OH and also position of the OH. If it's at the carbon where the carbon is attached to just one carbon, it is a primary. If it's at the carbon that bears the OH is attached to 2 other carbons directly, secondary. If that carbon is attached to 3 other carbons directly, tertiary. So that is for that. Now the way it works is that we can produce ethanol, which is the first member. No, there's methanol, there's ethanol. Ethanol is very essential. Like ethanol can be produced by fermentation. I believe you're aware about that. Ethanol can be produced by the process of what? Fermentation. Note that. What are the properties of ethanol? Ethanol is basically a colorless, volatile liquid with a characteristics, taste, and smell. Alright? It is soluble in water and boiling point is about 78 degrees Celsius. And it has no action on the litmus paper as well. It has no action. Now, since it is an organic compound, hence it will undergo combustion. So alcohols undergoes combustion. Right, alcohols undergoes what? Combustion. Please note what I just said. It will be a lot. Now, alcohols also undergo oxidation. Please note this point. Now, when an alcohol, for instance, undergoes oxidation, now they form what we call. Now, let me explain something. Let me basically tell you something. Incomplete oxidation of alcohols, like for instance, ethanol forms what we call ethanol. Just listen, oxidation, you add oxygen, right? But that's not the point right now. What I'm interested in is just telling you that, okay, note it. Whenever an alcohol is to undergo incomplete oxidation, they form an alkanal. They form an alkanal. Alright, let us move further. Please note what I just said. Whenever an alcohol is to undergo incomplete oxidation or partial oxidation, they form aldehyde. Alright? And this is seen in primary alcohols. So in summary, if primary alcohols, anything that is a primary alcohol like this guy, ethanol is a primary alcohol, undergoes. Now, even if you don't understand what I mean, I'm not showing the process, but note it, if it undergoes primary alcohol undergo oxidation, incomplete, it forms what? What does it form? It forms an alkanal or an aldehyde for primary. Whereas secondary, they undergo incomplete, they form the alkanones or ketones. Are you there? So primary is secondary. Alright? So it undergo oxidation. One undergoes aldehyde or alkyne, so it's undergo forms ketones, right? So that is the point I'm trying to make here. Take note. So what we use for this reaction, they call them oxidizing agent, which in redox I've taught us what oxidizing and reducing agent are. Now take note, tertiary alcohols does not undergo oxidation. Tertiary alcohols does not undergo oxidation. Notice. Tertiary alcohols does not undergo oxidation. That's what I just said. So these are reactions that ethanol or alcohols undergoes. Now we use the oxidizing agent we use is basically K2CR207 or even this guy called H2SO4. Take note. K2CR207. That's the oxidizing agent that is used. Alright, that's the oxidizing agent that is used. Though I'm not showing the mechanism, but you should just know what I'm talking about. At least you can be able to identify an alcohol that is primary, secondary, or tertiary. So you should know your product, all right? And you should, and I believe you're already able to identify aldehydes and ketones, all right? Aldehydes, they are functional groups always outside. Ketones, the functional groups always inside at the inside the compound. Hope you know what I'm talking about. All right, so let's move further. All right, let us move further. All right, let me just tell you something. Whenever a primary alcohol is undergoing complete stress, the oxidation I'm talking about here is incomplete. This incomplete oxidation now, incomplete oxidation that forms all of these guys, right? But the only one that undergo complete is primary. Are you there? The only one that will undergo complete oxidation that will not form a carboxylic acid, because complete oxidation of primary alcohol, I believe you know how to identify them now, forms carboxylic acids. So you just need to go to your option and try to identify the compound that is a carboxylic acid. All these things are not hard. They are all easy, guys. Just I want you guys to note all of these things. They are very essential. Now, other things, other reactions that these guys undergo is esterification. All right. Esterification is a reaction between an alcohol and an alkanoic acid, like alcohol, alkanoic acid to form an ester and water. It's like neutralization, whereby acid and base come together to form salt and water. So the salt is the ester. I'm just trying to tell you. So esterification, basically what happens is that esters esters are formed in esterification. Are you there? Esters are formed in what? Esterification. They're not hard at all. I'll show us what I mean by all this. So another reaction that these guys undergo is esterification to form esters. They react with alkanoic acid. esterification means an alkanoic acid like CH3COH. Hope you know this is an alkanoic acid like this ethanoic acid, 2 carbon reacting with C2H5OH. Okay, let me show you something. Let me tell you how it works. Let me give you guys the now an alkanoic acid which is R bond COOH reacting with R bond OH. So we're going to form what? Stop the question. What are we going to form? Look at what happens. The hydrogen here combines with the OH. So from where the other part joins. Are you there? So we're going to get R bond COO left. This one now compound on R plus water. Are you there? So let us form a product. Let us form an ester. So this is the ester form. Have you forgotten that this is the general form of esters? Okay, I haven't forgotten. So CH3COH ethanoic acid plus R bond plus CH3 plus C2H5OH, which is ethanol. So this one will form water. This one come out of this. It's going to form CH3 bond COO bond C2H5 and the water H2O. Yes, now this is the arrow. The arrow, this is it here. Look at it now first. This arrow now, this one that is the arrow now combine with the OO, COO, you understand? So how do we name this time? Name this last one. Ethyl. How many ethanoids? You understand? The purpose of name esters. So you can see the ester formed after reacting these two guys. So your product, to get your product is not a problem. Alright, to get your product is not a problem. So there's a catalyst used, and the catalyst is H2SO4. Alright, H2SO4 is a catalyst used to power up the reaction. Alright, H2SO4. Catalyst used in this esterification reaction is H2SO4. Alright, it's not hard. It's not hard. So let's get into alkanoic acids right now. Properly on alkanoic acids. Who are these alkanoic acids? Remember, alkanoic acids, they also called carboxylic acid. They have their own general form of the word bond, arrow bond, COOH, or what? CnH2 N plus what 1 COOH. Established on all these initially, right? So that is for that is for that. Now you should understand that we have different members of the alkanoic acid. Like the first member, you know, any compound with mets is called the first member will not be called metanoic acid. Are you there? After metanoic acid, the next member will be ethanoic acid. You understand? So let's get their chemical formula. This is methanoic acid. Met means that number of carbon is 1 in this case, right? So let us work it out together. Just relax and pay attention. Remember, these are general formula, right? So anyway, we see one. Let's get methanoic acid. It's going to be a C1H2. Yeah. Methanoic acid now. Okay, actually on this, let's be very smart. Let me tell you something. Here, methanoic acid. This is methanoic acid. Methanoic acid is this HCOOH. Because the number of carbon here of N will be 0. You know why? Because this methanoic acid. Met means that you have one carbon. If I use 1, for instance, for all these guys, they don't follow that pattern. Whether 1 means met, we are aware. 1 means met. So the N here will not be 1, it will be 0. Let's use 0 to get that thing. So N C 0 H2 into 0 plus 1 minus bond COH. So everything will be C0 means nothing. N times N times 0 is nothing. You understand? So it's already out. 2 times 1 is nothing as well. Alright? Yes, now. 0 plus 1. 0, like, this guy is nothing, right? Look at it. H2 into 0. So this one is out already. So H, 2 times 0, 0 is 0, right? So that is for that. So that hydrogen, that one will not add the hydrogen and bond COOH. So everything will be what? HCOOH. Right? So this is methanoic acid. So for all these guys that have like, because the reason why it doesn't work, it did not work because we already have a carbon there. So the N here will be 0 for meth. For X, the N will be 1. For the ethanoic acid, the N will be 1. Look at it. Using like same guy, C1 H2, 1 plus 1 bond COH. So it's going to be what? C1 H3. 2 times 2. 2 times 1, 3. 2 times 1, 2 plus 1, 3. COH, which is same as what? CH3 COH is ethanoic acid, right? F, we have 2 carbon, ethanoic acid. So you can see how it works. So the N for methanoic acid, the N is 0. N is 0, so that you actually go. So that everything will go well. Hope you are following me. The way it works here is this. 2 times 0 is 0. 0 plus 1, 1. You understand? And that's why, that's what the rest of this H. Because H1 is same as just H. Now, that is for that. I believe you can name any form of alkanoic acid you are given. How is, the first member is methanoic acid, and this methanoic acid, the common name is called formic acid. Whether the common name of ethanoic acid is called acetic acid. Alright, very, very popular. This is what called acetic acid. It's formic acid. Anything that has like OH, OH is an acid. Alright, so that is for that. How is this compound prepared? The first, like the second member called ethanoic acid, which is the most common. Alright, it is prepared by oxidizing, we've said that already now, by complete oxidation of an alcohol. Yes, I told us when the reactions that they undergo is oxidation. When alcohol undergo complete oxidation, specifically primary alcohols, we get alkanoic acid. So that's how we get them, guys. It's not hard. When alcohols, we stress on the primary alcohol undergoing what? Complete oxidation. If it is primary undergoing partial, we get aldehydes. Alright, but if it's complete alkanoic acids, primary, right? For secondary oxidation, be it complete, be it undergo complete or incomplete, it is still going to get that. We are still going to get the ketone or alkanone. You understand? All these things are not hard. They are all very, very easy. Now, moving further, what are the physical properties of these compounds, like ethanoic acid? Number one is that ethanoic acid is a colorless liquid with a characteristic sharp and pungent smell. Alright, it's an acid, so it will have a sour taste. And also it turns blue, it turns red. It's an acid, you understand? And it's a liquid. It has a boiling point of about 118 degrees Celsius. The boiling point is about 118 degrees Celsius and is very, very soluble in water. It is very, very soluble in water. The reaction that it undergoes is esterification, which I've taught us on when I taught about alcohols, where an alcohol and an ethanoic acid will come together to form what? Ester and water. You understand? We've talked about how it works, so not much talks there. And the catalyst uses H2SO4. Alright? Now, moving further, listen and listen well. Now, remember, when we oxidize alcohols, we get alkanoic acid, specifically oxidation, complete oxidation of a primary alcohol. When these guys now are now, they call them, they call this process reduction. On reduction, oxidation, redox have taught us all of these things. So when these alkanoic acids you are seeing here undergoes reduction, they basically form back, the alcohols or alkanols, specifically the primary. So note it. What now forms back the alcohol? It is reduction process of this alkanoic acid. What forms the alkanoic acid? It is oxidation process of primary alcohols. Are you there? So what actually, when these guys alkanoic acid undergo reduction, all right, reduction, reduction basically is removal of oxygen, addition of hydrogen. Yes, I believe you know what I mean by all this, right? Well, that's not the case. Just note that, reduction of these forms alcohol, specifically primary alcohol. But oxidation of alcohol, specifically primary alcohols, forms alkanoic acids. Not all of these points are very vital. They're very essential, all right? Now, what is the use of ethanoic acid? Ethanoic acid are basically used in aspirin production. They are used in making cellulose. They are used in making, artificial silk. They are used for making dyes. Right? So that is what that. They also use for flavoring food. Also, they are used in coagulating rubber latex. Coagulating what rubber latex. For esters, we've worked on esters already, where I told us that esters are formed by reacting an alcohol from an alkanoic acid. Then ester and water will be formed. We worked on all of those things, right? We have worked on all of those things. Those things are not a problem. Now, what are they? We've talked on how they are prepared. No much talks. Now, let me tell you something. In esterification reaction is a double reaction, like it's a reversible reaction, whereby the forward reaction is esterification, the backward reaction is hydrolysis. Look at what I mean. Information of ester. We are on ester right now. Ester is also called alkyne alkanoids. That reaction will form an ester reacting an alkanoic acid like CH3COH, which can really understand the reaction. I'm going to work it out again. Reacting with an alcohol like maybe C2H5OH. Before the reaction backward, he said, before the reaction, we form ester. Now, how does it work? This one combines with this one, right? So this one attack this guy. So it's going to be what now? CH3COO bond C2H5 plus water H2O. So now this one that forms the ester, that they call it esterification. But the one that goes back is irreversible. If you observe now, it is water that's now used to break back this one, they call it hydrolysis. Water is now used to break back. So the reverse of esterification is hydrolysis. Exam question. The reverse for esterification is what? Hydrolysis, forming back, breaking the ester and forming back those products, which is what now the ethanoic acid and alcohol, which is ethanol. Now, what are the physical properties of these guys called esters? Esters, they are, they have pleasant smell. They are colorless, volatile liquid. They have pleasant smell, and their boiling point is about 75 degrees Celsius. Please take note of these values. All right, and they dissolve organic solvents. They dissolve organic solvents. So that is for that. That is for that, guys. So we can move further to other things that are essential. Let us talk about alkanals and alkanones. Do you agree with me that alkanals, alkanones, they are both carbonyl compound? Those, even esters and alkanoic acids, even amides, they are carbonyl. They have those C double and O functional group in them. All right, so you have to take note of that. We already know how we prepare alkanals by oxidation of what primary alcohols, partial, incomplete primary alcohol. When you oxidize primary alcohol by partial oxidation, it forms an aldehyde or an alkanal. But if you oxidize the secondary alcohols undergo oxidation, it forms alkanones. Hope you guys know that all those things are not hard, they're easy. They're easy reactions. Now, there's a test to distinguish between alkanals and alkanones, very, very important. All right. There's a test to differentiate between alkanals and alkanones, a very essential test to note. So what is the test used to differentiate between alkanals and alkanones? Number one, they call it the Tolling's test. Tolling's test, which is just called the silver mirror test. All right. So this Tolling's test, they detect the presence of alkanals. All right. Just pay attention. Let me explain how it works. They are both carbon. You can relate to that and explain that. So number one test to differentiate them, call it Tolling's test. Usually called the silver mirror test. What happens in this test? There is this test detects the presence of alkanals, or not alkanones. Alkanals, how does it work? This Tolling's reagent or Tolling's test is made up of ammoniacal silver nitrate. All right. Take note. Ammoniacal silver nitrate. That's what they test this Tolling's. The compound that it has is made up of what I call it's called ammoniacal silver nitrate. So when you react this guy, ammoniacal silver nitrate with alkanal, it will form like a reaction will occur. You understand? A reaction will occur, like a silver mirror will form on the wall of the glass of the test tube. When you pour an alkanal into the test tube containing this reagent called ammoniacal silver nitrate, a silver substance will form at the wall of the test tube. So this tells alkanals do react with them, but alkanones no reaction occurs. The solution remains colorless. All right, the solution nothing happens, no reaction occurs. You understand? So Tolling's test positive for alkanal. When you react alkanal with them, they will give you positive. So that means the reaction occur, which is a silver mirror on the glass wall of the test tube. But for alkanones, they don't. What about another test to differentiate between them? Now listen. We have what we call the Valency test and the Benedict test. The Valency and the Benedict test. Just note what I'm saying now. It's very, very important now. I'm coming. Now, take note for the Valency test, the Valency solution, they contain copper 2 ions. All right, copper 2 ions. Take note. While the Benedict test or Benedict solution contains copper 2 ion in citrate complex. All right, in citrate complex, and they are literally like same. All right, they're like same test. I'm coming. Now, just listen and listen well. So we're able to differentiate between alkanones using Tolling's reagent. Now, let me tell you something. This test you are seeing right now, which is the Valency test and Benedict test, is that both of them, they are used to tell the presence of aldehyde from ketones. So in general, aldehyde give positive test to these tests or solutions, which are Valency and Benedict. Are you there? Now, when you react these solutions, be it Benedict or Fehling solution, Benedict solution or Fehling solution with this compound, you have the Benedict and also Fehling's solution with this compound, which are alkanes, alkanones. Alkanes react. These guys, they don't react. Alkanones don't react. Do you understand? So alkanal will basically change the color of that solution to be like a red precipitate, form a red precipitate. Do you understand? And both of them, they are literally made up of same. They're made up of copper ions. All right, both tests contain copper ions. And initially, their color is blue. So after reacting with the alkanal, they will now turn a red. They now become red. Right? They will now form what we call copper oxide. Yeah, they form copper oxide, but it's a color you should take note of here. Initially, they were blue, so they will not be red. You understand? What do I mean by what am I saying is blue? I'm saying the solution itself were blue in color, right? Because of the copper is blue. Yeah, we did test our water now. You saw that. So copper is a blue, so it's blue, right? So if you react these tests, both of them, Fehling's Benedict, the presence of that copper ion present in both of them, they will now basically change the color from blue to red. But alkanones will not react with them, they will just stay blue. They will just all stay blue. So that's the difference. This is called copper, the Cu2O, they call it copper 1 oxide. So what happens, both of them has copper ions in them. Alright, so it was blue, red, then become red. Blue, copper is blue, so now become red. But for alkanones, they don't react, they remain blue. So after reacting alkanone inside the test tube, for instance, there's no color change. So it tells you alkanones don't give positive test to Benedict and Tolin's reagent. Benedict, Tolin's, and even the Fehling's reagent. Are you there? So you can see how we've been able to work on it, right? So that is for that to note all what I've said. All these things are very, very essential. All these things are very, very essential, guys. All right, I think we are good to go on all these things. Now, without wasting time, let us talk about polymers. What are polymers? Polymers are substances formed when various monomers comes together. Polymer is a large molecule. Polymer is a large molecule. So when you bring substances together, you form a polymer. All right. So we have different types of polymer. We have natural polymer and synthetic polymer. All right. Now listen very well. Natural polymer and synthetic what polymer? Pay attention. All right. So guys, that's for that. Natural polymers and synthetic polymer, we have two types. What are the synthetic? They are your plastics, all right? They're your plastics. And also we have what we call thermoplastics and thermosets. Thermoplastics and thermosets. What are thermoplastics? Thermoplastics are substances that can be softened repeatedly by heat and remolded. Why thermosets cannot be softened, all right, or melted by heat or remolded. Once they are formed, they are formed. That's why they call thermoset. They're already set for anything. You cannot basically change them anymore. So thermoplastic, you can basically, maybe they're not used for a particular function anymore. You can melt them back and then form what you want to form. Like a good example is polythene, polypropylene, polystyrene. You understand? All these are examples of thermoplastics. All right, polythene, take note of that. Also, so you just know the difference between a thermoplastic and also a thermoset. Very, very vital. The one that you can soften or melt or remold is thermoplastics. Thermoset, as you form them, they're already set. You understand? Like a good example of a polythene is those your water bottle, detergent bottles, plastic shopping bags, all those things, your plastic pipes, all these are examples of thermoplastics. So take note, why examples of thermoset include what we call bakelite. Have you heard about bakelite before? Bakelite is a good example of a thermoset. Alright? Bakelite is a good example of a thermoset. Like for instance, those your switches in your house, handles of cooking utensils, they are bakelite. Alright, they're examples of bakelite. You understand? So it's very hard. But buttons, once they are formed, it's very hard for you to use them with other things. Remote and stuff like that. Alright? So now that is for that. We have two types of polymerization reaction. We have what we call the addition polymerization, and also we have what we call the condensation polymerization. Alright? So take note of that, addition and also condensation polymerization. Addition and condensation polymerization. Take note, they're very, very important. And very, very essential. That is for that, guys. Now, the point here is in addition polymerization, the monomers are, polymerization has to do with you adding monomers together, right? So in addition, you are adding monomers without losing any small molecule. Alright? You're adding monomer without losing anything. While in condensation, you are adding monomers joined with elimination of small molecules. And you are adding things, you are removing in the reaction, things are removed. Alright? So in addition, you are adding and nothing is removed. In condensation reaction, condensation polymerization, you're adding things, but other things are removed. That's just a simple way to learn it. Alright? Take note. In condensation, you're adding things, and things are removed. In addition polymerization, you're adding things, and things are still not removed. Things are not removed. Alright? Just learn it that way, and you are good to go. Alright? You are good to go. The common name of polyethylene is polythene or polyethylene. Take note of that. The common name of polychloroethylene is polyvinyl chloride. Note their common names. The common names of polypropenyl nitrile is polyacrylonitrile. Alright? And the common name of polymethyl 2-methyl propanoate, polymethyl 2-methyl propanoate is what we call perspex. Perspex. Alright, perspex is also an example of what? Is a thermoplast. Perspex is a thermoplast, which is a polymethyl 2-methyl propanoate. That's perspex. These are the name. What is this perspex we are talking about? Alright, what is this perspex we are talking about? And for instance, our window, there are examples of purpose. Alright. So I want to just give you a list of examples of for the thermoplastics. They include polythene, propene, polystyrene, nylon, terylene, and purpose. What are examples of your thermosets? They include bakelite, those are switches in your house, kitchen utensil, bakelite, and also urea methanol. All these are examples of for thermosets. Bakelite and urea methanol. Urea methanol. So that is for that, guys. Not all this, it will help a lot. Not all this, it will help a lot. Not all this, it will help a lot. Now take note, there's something that forms natural rubber. They call it monomer of natural rubber. It's called 2-methyl-buta-1,3-diene. You can draw the structure actually. It's not hard. Take note, though, I know I'm just bringing out this point. The monomer of natural rubber is called 2-methyl-buta-1,3-diene. That's the monomer of natural rubber. While the monomer of synthetic rubber is what? 2-chlorobuta-1,3-diene, also called neoprene. Natural rubber is also called isoprene, whereby synthetic rubber is also called neoprene or 2-chlorobuta-1,3-diene. Note that, or 2-chlorobuta-1,3-diene, or 2-chlorobuta-1,3-diene, guys. So that is for that. That is for that on that. So on the aspect of those carbohydrate, proteins, lipids, they're not hard. They are still in biology as well. Yeah, they're still in biology, understanding the class of food, understanding those for carbohydrates, they are complex, they are polyhydroxy alkanals or alkanones. All these are complex now. We have they are sugars, right? You have three of them: monosaccharide, disaccharide, and polysaccharide. Then we have oligo inside. Mono carbohydrates are made of simple sugars, like starting from the 3 carbon sugars called trioses to eptoses. They have trioses, we have trioses, we have what's next? Tetroses, pentoses, hexoses, and heptoses. What are the trioses? Now, carbohydrate contains 3 elements: carbon, hydrogen, and oxygen, in the ratio 1:2:1. Alright, so what would now be the general formula for the trioses? They have 3 carbons, right? So it's going to be C3H6O3. They're not hard. I use the ratio 1:1. So if my carbon is 3, my hydrogen becomes 6, my oxygen becomes 3 as well. So if I don't work on the tetroses, the general formulas, what is that? The C4H8O4. What about the 5 carbon sugar? C5H10O5. What about 6 carbon sugar? Very common, like glucose, fructose, galactose. They are C6H12O6. What about the 7 carbon sugars? C7H14O11. C7H14O7. You understand what I'm saying? So then going down to disaccharide formation of what now? Monosaccharide together with elimination of water, and it's a condensation reaction. When disaccharides are formed, condensation reaction occurs. Condensation reaction is a reaction that eliminates water. So that's why in condensation polymerization, you are basically trying to add things together, but water is lost. In addition, polymerization, you are bringing things together without the loss of something. Alright, so that's what I say applies to amino acids. The basic unit of amino acids are called proteins. You understand what I'm saying? Protein is a sweet ion. Amino acid basically is a sweet ion containing both positive and negative charges. Same applies to fat and oil. Fat and oil basically also called lipids. You understand what I'm saying? Alright, so guys, with all this said, we've done a lot on organics. And we are done for now, and God bless you all.